Graph embeddings. Graph neural networks, GNNs, operate by iteratively passing and aggregating messages across nodes in a graph. The ultimate goal of this process, particularly for many machine learning tasks, is to generate meaningful graph embeddings. An embedding is a low-dimensional vector representation of a node, an edge, or an entire graph, designed to capture its inherent properties and its relationships within the broader graph structure. The need for graph embeddings. Graphs, by their very nature, represent complex relationships and intricate structures that are not directly compatible with most standard machine learning algorithms. Algorithms like support vector machines, SVMs, logistic regression, or neural networks typically expect input data in the form of fixed-size numerical vectors. Directly feeding a graph structure, e.g., an adjacency matrix, can be problematic due to varying graph sizes, sparsity, and the inability to easily capture relational information. This is where graph embeddings become crucial. They transform the rich relational information of a graph into a compact, numerical format, effectively vectorizing graph components. Why lower-dimensional representations? The transformation into a lower-dimensional vector space offers several significant advantages. 1. Computational efficiency. High-dimensional data is computationally expensive to process, store, and analyze. Lower-dimensional embeddings reduce the number of features, leading to faster training times for subsequent machine learning models and less memory consumption. This helps mitigate the curse of dimensionality, where data becomes sparse and difficult to model in high-dimensional spaces. 2. Compatibility with standard ML algorithms. As mentioned, most classical machine learning algorithms are designed to work with fixed-size feature vectors. Embeddings provide this standardized input, allowing practitioners to leverage a vast ecosystem of well-understood and optimized algorithms. 3. Noise reduction and feature extraction. The embedding process inherently acts as a form of dimensionality reduction and feature engineering. It learns to distill the most salient characteristics of a graph entity, often implicitly filtering out noise and irrelevant information, resulting in more robust and discriminative features. 4. Visualization. High-dimensional data is impossible to visualize directly. By reducing data to 2 or 3 dimensions, embeddings enable visual exploration of graph structures, revealing clusters, outliers, and patterns that would otherwise remain hidden. How embeddings capture graph structure. A well-formed graph embedding captures the intricate structure of the graph by ensuring that entities with similar properties or relationships in the original graph space are mapped to vectors that are close to each other in the embedding space. This proximity in the vector space can signify various types of relationships. Proximity, nodes that are structurally close in the graph, e.g., direct neighbors, or reachable within a few hops, will tend to have similar embedding vectors. This captures the idea that friends of friends might share common characteristics. Structural roles. Nodes that play similar roles in the graph, e.g., central hubs, bridge nodes connecting different communities, peripheral nodes, might also have similar embeddings, even if they are far apart in the graph. For instance, two different influencers in separate communities might have similar embeddings. Attributes/features. If nodes or edges have initial features, e.g., age of a person, type of a product, the embeddings will integrate these attributes along with the structural information. Conceptually, if you project these high-dimensional embedding vectors onto a 2D or 3D plane, nodes that are closely related or share similar characteristics within the graph would appear clustered together. Traditional versus GNN integrated embedding generation. Historically, generating graph embeddings was often a separate, multi-step pre-processing task, distinct from machine learning model training. Traditional approaches. Before the advent of GNNs, various methods were employed to create graph embeddings. Classical graph algorithms. Spectral methods. These methods leverage the eigenvalues and eigenvectors of graph matrices, like the graph Laplacian, to embed nodes into a low-dimensional space. Examples include code snippet or code snippet. are powerful for capturing global graph structure, but can be computationally intensive for large graphs. Random walk-based methods. Algorithms like code snippet and code snippet generate sequences of nodes by simulating random walks on the graph. These sequences are then treated like sentences and fed into word embedding models, e.g., code snippet, to learn node embeddings. These methods are effective at capturing local neighborhood information. Linéaire algebra technique en adjacency matrice. Simple approaches might involve applying dimensionality reduction techniques like code snippet or code snippet directly to the graph's adjacency matrix or feature matrix derived from it. While straightforward, these methods often struggle to capture the complex, nonlinear relationships inherent in graphs. These traditional methods typically involve 1. Graph preprocessing, constructing adjacency matrices, calculating walk sequences, etc. 2. Embedding generation, running a specific algorithm, node 2vec, PCA, to produce fixed embeddings. 3. Model training, using these pre-computed embeddings as input features for a standard ML model. The GNN advantage. GNNs represent a paradigm shift because they integrate the embedding generation directly into the learning process. Instead of a separate, static pre-processing step, GNNs learn to generate context-aware node, or graph, embeddings as part of their forward pass. This end-to-end learning offers several key advantages. Dynamic and contextual embeddings. GNNs generate embeddings that are not static, but are dynamically updated during the training process. This allows the embeddings to be highly specific to the downstream task, e.g., node classification, link prediction, and to capture the local neighborhood information dynamically through the message passing mechanism. Feature and structure integration. GNNs naturally combine both node features, if available, and the graph's topological structure. The message passing mechanism allows information from a node's neighbors and their features to be aggregated, leading to embeddings that represent a node's identity and its role in its local graph context. Inductive capabilities. Some GNN architectures can generate embeddings for unseen nodes or even entire unseen graphs, leveraging the learned aggregation functions. This is critical for real-world applications where graphs are constantly evolving. In essence, a GNN's final layer often outputs these learned embeddings, which are then either used directly as input for a classification/regression head, e.g., a simple linear layer, or further processed for other tasks. Practical applications of graph embeddings. Graph embeddings are foundational to applying machine learning across a wide array of graph-structured data. Their utility spans various tasks. Graph visualization. By embedding nodes into 2D or 3D space, it becomes possible to visualize complex networks. Tools like code snippet or code snip PED are often applied to the high-dimensional embeddings generated by GNNs to project them into a lower-dimensional space suitable for plotting, revealing clusters and relationships. Graph clustering. Similar to traditional clustering of feature vectors, graph embeddings allow for direct application of clustering algorithms, e.g., k-means, disscan, to group similar nodes or subgraphs together based on their embedding proximity. This can reveal communities in social networks or functional modules in biological networks. Predictive modeling on graph data. Node classification, predicting a label or category for individual nodes, e.g., classifying users in a social network, categorizing proteins. Link prediction, predicting the existence of a missing link or the likelihood of a future link between two nodes, e.g., recommending friends, predicting drug interactions. Graph classification/regression, predicting a property for an entire graph, e.g., classifying molecules as toxic/non-toxic, predicting the binding affinity of a protein. Case study. Political book purchases for semi-supervised classification. Consider a dataset of books purchased by individuals, where connections, edges, exist between books that are frequently bought together. Some of these books might be pre-labeled as liberal or conservative based on their content, while many remain unlabeled. This scenario is ideal for semi-supervised classification. In this context, semi-supervised classification means that only a small subset of the data, books in this case, has known labels, while the majority is unlabeled. The goal is to leverage both the labeled and unlabeled data, along with the graph structure, to predict the labels for the unlabeled books. Graph embeddings for each book would capture its content similarity, its purchasing patterns with other books, and its position within the overall network of political literature. Books frequently purchased with known liberal books would likely have embeddings close to those books, and vice versa. Insights gained. By applying a GNN to learn embeddings and then a classifier, one could identify groups of politically aligned books or readers, predict the political leaning of new, unlabeled books, understand how different political ideologies manifest in purchasing behavior, discover bridge books that appeal to both sides or highly polarizing books. Conceptual code example, illustrating dimensionality reduction for graph data. While GNNs integrate embedding generation, understanding the fundamental concept of transforming graph data into a lower dimensional vector space is key. Here, we'll use a very simple example to illustrate how node features could be extracted from a graph and then reduced in dimensionality, conceptually similar to how embeddings aim to compress information. This is not a GNN, but it highlights the why of lower dimensional vectors. First, we'll define a simple graph using code snippet and assign some arbitrary features to its nodes. Code is not spoken. To get code, please see the link in description or bio. In this first part, we create a small graph code snippet with 6 nodes and some edges. We then assign a 5-dimensional feature vector to each node. These feature vectors represent inherent properties of each node, analogous to how a book might have features like genre score, author popularity, reading difficulty, etc. The goal of an embedding is to compress these features while also considering the graph structure. Next, we'll prepare these features into a format suitable for a dimensionality reduction algorithm like PCA. Code is not spoken. To get code, please see the link in description or bio. Here, we convert our dictionary of node features into a number py array, code snippet, where each row corresponds to a node and each column is a feature dimension. This matrix is the input for our dimensionality reduction step. Notice that each node currently has 5 features. Now, we apply code snippet, principal component analysis, to reduce these 5 features down to 2 dimensions. This simulates the compression aspect of embedding generation. Code is not spoken. To get code, please see the link in description or bio. This code snippet uses code snippet to reduce the 5-dimensional feature vectors to 2 dimensions. The code snippet now contains our embeddings, which are 2D vectors for each node. This is a conceptual demonstration of how a higher dimensional representation, our original features, can be compressed into a lower dimensional one, making it easier for visualization or subsequent ML tasks. Finally, we visualize these 2D embeddings to see how nodes are positioned in the compressed space. Code is not spoken. To get code, please see the link in description or bio. This visualization helps us understand the benefit of embeddings. By reducing the data to 2 dimensions, we can plot each node as a point on a 2D plane. Nodes that had similar original features, e.g., and B or C, will likely appear closer together in this 2D space. While this example only uses initial node features and not the graph structure itself, as PCA doesn't inherently understand graph connectivity, it serves to illustrate the concept of transforming complex data into a simplified yet informative vector representation. GNNs extend this by performing a similar transformation but integrating the graph topology directly into the learning process. Creating embeddings with Node 2-Vec. Graph neural networks, GNNs, represent a powerful paradigm for learning on graph-structured data. However, before diving deeper into GNNs, it's crucial to understand how to represent nodes and their relationships in a way that machine learning models can process. This is where graph embeddings come into play. Node embeddings are low-dimensional vector representations of nodes that capture their structural and contextual information within the graph. These embeddings are invaluable for various downstream tasks, such as node classification, link prediction, and clustering. Node2vec is a prominent algorithm for generating such node embeddings. It is inspired by the successful word2vec algorithm for natural language processing, NLP, which learns word embeddings by analyzing sequences of words and text. Node2vec adapts this idea to graphs by generating sequences of nodes through simulated random walks. Node2vec, learning from random walks. The core idea behind Node2vec is to treat sequences of nodes generated by random walks on a graph as sentences and individual nodes as words. Just as Word2vec learns embeddings where words appearing in similar contexts, neighboring words, have similar vector representations, Node2vec learns embeddings where nodes appearing together in random walks have similar representations. This approach allows Node2vec to capture different notions of node similarity. Homophily, nodes that are connected and share similar attributes or roles, e.g., friends in a social network. Structural equivalence, nodes that occupy similar structural positions in the graph, even if they are far apart, e.g., two different bridge nodes connecting distinct communities. Unlike graph neural networks, which learn node representations by aggregating information from a node's immediate neighborhood through message passing, Node2vec is considered a shallow embedding method. It learns fixed embeddings for each node independently of a specific task, using random walks to define node contexts. GNNs, on the other hand, typically learn embeddings tailored to a specific task and can generalize to unseen nodes or graphs. Understanding Node2vec provides a foundational perspective on representing graph data before exploring the more complex, expressive power of GNNs. The role of random walks and parameters, code snippet and code snippet. Node2vec's power lies in its ability to control the characteristics of the random walks it generates. This is achieved through two key parameters, code snippet, return parameter, and code snippet, an out parameter. These parameters influence the probability of a walk traversing certain paths, allowing Node2vec to interpolate between breadth-first search, BFS, like, and depth-first search, DFS, like exploration strategies. Let's consider a random walk that has just traversed an edge from node code snippet to node code snippet and is now deciding the next step, code snippet. C. Code is not spoken. To get code, please see the link in description or bio. The probability of moving to a neighbor code snippet from code snippet depends on its relationship to code snippet. Code snippet, return parameter. This parameter controls the likelihood of immediately revisiting a node. If code snippet is high, e.g., code snippet, the walk is less likely to return to the previous node code snippet. This encourages more outward exploration. If code snippet is low, e.g., code snippet, the walk is more likely to return to the previous node code snippet. This can lead to more localized exploration, potentially capturing microcommunities. Code snippet, an out parameter. This parameter controls whether the walk tends to move towards nodes closer to code snippet, BFS-like, or further away from code snippet, DFS-like. If code snippet is high, e.g., code snippet, the walk is more likely to stay local and explore nodes that are close to code snippet and are also neighbors of code snippet. This promotes a BFS-like behavior, focusing on immediate neighborhood and discovering nodes that are structurally similar in terms of being part of a local community. If code snippet is low, e.g., code snippet, the walk is more likely to move to nodes that are further away from code snippet, i.e., not neighbors of code snippet. This promotes a DFS-like behavior, encouraging exploration of nodes that might be structurally equivalent but are across different parts of the graph. By tuning code snippet and code snippet, Node2vec can generate random walks that emphasize either local structural patterns, BFS-like, useful for identifying communities, or broader structural roles, DFS-like, useful for identifying bridge nodes or hubs. These diverse sequences are then fed into a skipgram model, similar to Word2vec, to learn the node embeddings. Nodes that frequently co-occur within these tailored random walks will have similar vector representations. Practical workflow: generating node embeddings. The typical workflow for generating node 2vec embeddings involves several steps: loading the graph data, initializing the node 2vec model with appropriate parameters, generating the embeddings, and then using them for analysis or visualization. We will use the code snippet Python library, which provides a convenient implementation of the algorithm. For our example, we'll work with the political books dataset, a classic network dataset where nodes represent books about U.S. politics and edges represent frequent co-purchasing. Each book is labeled as liberal, conservative, or neutral. Step 1. Loading and inspecting the graph data. First, we need to load our graph data. The code snippet library is excellent for representing and manipulating graphs in Python. The political books dataset is often available as a GML, graph modeling language file. Code is not spoken. To get code, please see the link in description or bio. This initial code block loads the graph. We first attempt to load the code snippet file, which is the intended dataset. If it's not found, we fall back to the code snippet from code snippet to ensure the code can still run for demonstration purposes. After loading, we print basic statistics about the graph, such as the number of nodes and edges, and check for the presence of node attributes like value, which indicates political leaning in the political books dataset. Step 2. Initializing node 2vec. Now we initialize the code snippet model. This involves setting key parameters that control the embedding process, including the dimensions of the final embeddings, the length and number of random walks, and the code snippet and code snippet parameters we discussed earlier. Code is not spoken. To get code, please see the link in description or bio. In this step, we configure the code snippet object. Code snippet specifies the size of the embedding vector for each node. A higher dimension can capture more information, but requires more computational resources. Code snippet defines the maximum number of steps in each random walk. Longer walks capture broader contextual information. Code snippet determines how many random walks are initiated from each node. More walks lead to a richer set of sentences for the skipgram model, potentially resulting in more robust embeddings. Code snippet and code snippet. These are the critical parameters for controlling the walk strategy, as explained previously. Setting bot. H to code snippet results in a standard random walk. Code snippet allows parallel computation for faster processing. Code snippet ensures that the random walks generated are reproducible across runs. Step 3. Generating embeddings. With the code snippet model initialized, the next step is to generate the embeddings. This involves two main phases within the library. First, generating the random walks, and then training a word 2vec, skipgram, model on these generated walks to learn the embeddings. Code is not spoken. To get code, please see the link in description or bio. The code snippet method executes the random walks and trains the skipgram model. Code snippet. This parameter comes directly from the word 2vec algorithm. It defines the maximum distance between the current node and the nodes in its context that should be considered for learning. A larger window means a broader context. Code snippet. Also from word 2vec, this parameter ignores nodes that appear less frequently than this threshold in the generated random walks. Code snippet controls the batch size for training the word 2vec model. Step 4. Accessing and preparing embeddings. After training, the embeddings are stored within the code snippet object. We can access these embeddings and convert them into a more convenient format, such as a pandas data frame, for further analysis and visualization. Code is not spoken. To get code, please see the link in description or bio. The code snippet object, where code S. Nipet stands for word vectors, holds the learned embeddings. We iterate through all node IDs in our graph and retrieve their corresponding vector from code snippet. It's important to note that the code snippet library stores node IDs as strings, so we convert them using code snippet when accessing. Finally, we create a pandas data frame where each row corresponds to a node and its columns are the embedding dimensions. If the original graph had node attributes, like value for political leaning, We add this as a new column to the data frame for easier visualization and analysis. Visualizing embeddings with UMAP. High-dimensional embeddings are difficult to interpret directly. Dimensionality reduction techniques like UMAP, uniform manifold approximation and projection, are essential for visualizing these embeddings in 2D or 3D space. UMAP is a powerful technique for manifold learning that attempts to preserve both local and global data structure better than older methods like TSNE or PCA, making it excellent for revealing clusters and relationships in complex datasets. Applying UMAP for dimensionality reduction. Code is not spoken. To get code, please see the link in description or bio. Here, we instantiate a code snippet reducer. Code snippet. We want to reduce the embeddings to 2 dimensions for easy plotting. Code snippet for reproducibility. Code snippet and code snippet. These are important UMAP parameters that influence the balance between preserving local var. Global structure. Code snippet controls how tightly clustered points are, while code snippet controls the size of the local neighborhood UMAP considers. We then apply code snippet to our embeddings data frame, excluding the political_leaning column, if present, as it's an attribute, not an embedding dimension. The resulting code snippet array contains the 2D coordinates, which we add back to our code snippet, plotting the 2D embeddings. Finally, we can visualize the 2D embeddings. If our graph has node attributes, like political leaning, we can use these to color the points in the plot, allowing us to visually identify if node 2vec successfully grouped nodes with similar characteristics. Code is not spoken. To get code, please see the link in description or bio. This code uses code snippet and code snippet to create a scatter plot. Each point in the plot represents a node from our graph. If the code snippet attribute is present, we use it to color the points. This allows us to observe if books of similar political leanings cluster together in the embedding space, which would indicate that node 2vec successfully captured this characteristic through its random walks. The expectation for the political books dataset is to see distinct clusters corresponding to liberal, conservative, and neutral books, demonstrating the effectiveness of node 2vec in capturing latent structural and contextual similarities. By following this workflow, you can generate and visualize node embeddings for any graph dataset, gaining insights into the underlying structure and relationships within your network. These embeddings can then be used as features for various machine learning tasks, unlocking the potential of graph data for predictive modeling and analysis. Loading data, setting parameters, and creating embeddings. This section bridges the theoretical understanding of graph embeddings and the node 2vec algorithm with its practical implementation. You will learn how to load graph data, configure the node 2vec model, train it to generate node embeddings, and then extract and prepare these embeddings for further use. 1. Setting up your environment and data. Before diving into the code, ensure you have the necessary libraries installed. The code snippet library is used for graph manipulation, and code snippet provides the node 2vec implementation. Code is not spoken. To get code, please see the link in description or bio. For this practical example, we will use the political books dataset code snippet, a classic graph dataset representing books about U.S. politics sold by Amazon.com. Edges between books indicate frequent co-purchasing by the same buyers. This dataset is commonly used in graph analysis to explore community structures or relationships between items. Ensure that code snippet is accessible to your script. You can place it in the same directory as your Python file or provide its full path. First, we import the required libraries, code snippet for graph operations, and code snippet from the code snippet package. Code is not spoken. To get code, please see the link in description or bio. Next, we load the graph data from the GML file. GML, Graph Modeling Language, is a common file format for graphs. It's crucial to handle potential code snippet if the specified file path is incorrect or the file is missing. Code is not spoken. To get code, please see the link in description or bio. Upon successful loading, it's good practice to inspect the graph to confirm its structure and ensure it loaded as expected. Code snippet provides a summary, including the number of nodes and edges. Code is not spoken. To get code, please see the link in description or bio. This output confirms that the graph has been loaded and gives you an initial understanding of its scale. For the political books dataset, you should see 105 nodes and 441 edges, representing books and their co-purchase relationships. 2. Understanding Node 2vec parameters, guiding the random walks. Node 2vec generates embeddings by simulating biased random walks on the graph, and then applying a word 2vec, like algorithm, specifically skipgram, to these sequences of nodes. The parameters passed to the code snippet constructor primarily control the behavior of these random walks. Code is not spoken. To get code, please see the link in description or bio. Let's break down these critical parameters. Code snippet. This is the code snippet graph object, code snippet in our case, on which the random walks will be performed. Code snippet. This integer specifies the dimensionality of the resulting node embeddings. A higher dimension allows the model to capture more complex relationships, but increases computational cost and the risk of overfitting. Conversely, too low a dimension might not capture enough information. Common values range from 32 to 256. Code snippet defines the maximum length of each random walk. Longer walks allow the embeddings to capture more global structural information about the graph, as nodes further away can be considered context. Shorter walks focus more on local neighborhood information. Code snippet. The number of random walks to generate starting from each node in the graph. More walks provide more training data for the word 2vec model, leading to potentially more robust embeddings, but also significantly increases computation time. Code snippet. Return hyperparameter. This parameter controls the probability of immediately revisiting a node in the walk. If code snippet, the walk is less likely to return to the previous node, favoring outward exploration. If code snippet, the walk is more likely to return to the previous node, favoring inward movement. If code snippet, as used here, there is no bias towards returning to the previous node. Code snippet. In out hyperparameter, this parameter controls whether the walk tends to explore broadly or stay within a localized region. If code snippet, the walk is biased towards exploring nodes further away from the previous node's neighborhood, favoring outward exploration. This leads to embeddings that capture more global graph structure, similar to deep walk. If code snippet, the walk is biased towards visiting nodes that are close to the previous node, favoring inward movement. This makes the embeddings reflect more local neighborhood structure, similar to breadth-first search, BFS. If code snippet, as used here, there is no bias towards exploring or staying local, resembling a standard random walk. Code snippet. This parameter specifies the number of CPU cores to use for parallel processing of the random walks. Generating walks can be computationally intensive for large graphs, and code snippet allows you to leverage multiple cores to speed up this process significantly. A common practice is to set code snippet to the number of CPU cores available on your machine, or slightly less to leave resources for other processes. Code snippet. Setting a code snippet ensures that the random walks generated are reproducible. This is crucial for debugging and ensuring consistent results across multiple runs. Choosing optimal values for code snippet, code snippet, code snippet, code snippet, and code snippet is often an empirical process that depends on the specific graph structure and the downstream task. Understanding their impact on capturing local versus global information is key to effective tuning. 3. Training the embedding model, leveraging word 2vec. Once the code snippet object is initialized, the next step is to train the model. The code snippet method is called on the code snippet object, which internally uses a skipgram model, typically from the code snippet library, to learn the node. Embeddings from the generated random walks. Code is not spoken. To get code, please see the link in description or bio. The parameters for the code snippet method are inherited from the underlying word 2vec implementation. Code snippet. This is analogous to the context window in natural language processing. In node 2vec, it defines the maximum distance between the current node and the context nodes within a random walk that are considered for learning. A larger window means nodes further apart in a walk can influence each other's embeddings, potentially capturing broader contextual relationships. Code snippet. This parameter specifies the minimum frequency a node must have across all generated random walks to be included in the vocabulary for embedding. Nodes that appear fewer times than code snippet are ignored. Setting code snippet, as done here, ensures all nodes are included, which is often desirable for graph embeddings where all nodes are typically important. Code snippet. This parameter controls the batch size for training the skipgram model. It specifies the number of words, nodes, to process in a single batch during the stochastic gradient descent optimization. Adjusting this can influence training speed and convergence. Code snippet. The number of training iterations over the entire corpus of random walks. More epochs can lead to better convergence, but also increase training time. The computational complexity of Node 2vec is primarily driven by two phases. 1. Random walk generation. This phase is proportional to code snippet. Increasing any of these parameters will directly increase the time taken for walk generation. The code snippet parameter helps parallelize this, reducing wall clock time. 2. Word 2vec training. This phase is proportional to code snippet. It's clear that code snippet, and code snippet significantly impact the training time in addition to the walk parameters. 4. Extracting and inspecting embeddings. After the model is trained, the learned embeddings are stored within the code snippet attribute. Code snippet stands for word vectors, a term carried over from natural language processing, where word 2vec was originally applied to words. Each node's embedding is a vector of floating point numbers. Code is not spoken. To get code, please see the link in description or bio. The use of code snippet is a common practice and a best practice when working with code snippet's word 2vec, which node 2vec uses internally. While code snippet can handle various data types for node IDs, integers, strings, etc., code snippet, the type of code snippet, often expects string keys. Converting all node IDs to strings ensures consistency and prevents potential code snippet if some node IDs are integers while others are strings in the original graph. Now that the embeddings are extracted, it's useful to inspect a few samples to understand their structure and confirm their dimensionality. Code is not spoken. To get code, please see the link in description or bio. The output will show a number py array of floating point numbers, representing the 64-dimensional vector for the chosen node. Each number in the vector is a feature that captures some aspect of the node's position and relationships within a graph. 5. Saving embeddings for future use. Once generated, embeddings are valuable assets for subsequent machine learning tasks. It is a best practice to save these embeddings to disk so they can be easily loaded later without needing to rerun the potentially time-consuming Node 2vec training process. Common formats for saving numerical data include NumPy's code snippet format or Python's code snippet module for dictionaries. Code is not spoken. To get code, please see the link in description or bio. Saving your embeddings allows you to load them directly into your machine learning pipelines for tasks like node classification, clustering, or visualization, without recomputing them every time. 6. What's next for your embeddings? Now that you have successfully generated numerical embeddings for each node in your graph, you have transformed complex graph structures into a format readily usable by traditional machine learning algorithms. These embeddings can serve as powerful features for a variety of downstream tasks. Node classification. Predict a label or category for each node, e.g., classifying books by genre based on co-purchase patterns. Node clustering. Group simul. AR nodes together based on their embedding proximity, e.g., identifying communities of politically aligned books. Link prediction. Predict the likelihood of a new edge forming between two nodes. Graph visualization. Reduce the dimensionality of the embeddings further, e.g., using tsine or UMAP, to visualize the graph structure in 2D or 3D space, where similar nodes are clustered together. The subsequent sections will explore some of these applications, demonstrating how these learned representations unlock the power of graph data for predictive modeling and analytical insights. Demystifying embeddings. Graph embeddings are a fundamental concept in modern graph machine learning, serving as the bridge between complex graph structures and traditional machine learning algorithms. At their core, graph embeddings are dense numerical vectors that represent entities within a graph, such as nodes, edges, or even entire subgraphs. We're graph embeddings. Imagine trying to describe a person to a computer. You could list their friends, their hobbies, their job, and so on. This is complex, high-dimensional, and often sparse data. Graph embeddings provide a more digestible format. A graph embedding for a node is essentially a low-dimensional numerical array, a vector, where each number in the array represents a specific, often latent, characteristic or trait of that node. These traits are not directly interpretable in human terms, like age or city, but rather a mathematical distillation of the node's position and role within the graph structure. Consider the alternative, representing nodes using sparse representations, such as one-hot encoding. If you have 10,000 nodes, a one-hot vector for each node would be 10,000 dimensions long, with only one code snippet and 9,999 code snippets. This is computationally inefficient, requires vast memory, and struggles to capture relationships between nodes because every node is equidistant from every other node in this representation. Dense vectors, like embeddings, overcome these limitations. Computational efficiency. They typically have far fewer dimensions, e.g., 64, 128, 256, than the number of nodes, making computations faster and memory usage lower. Generalization. By learning latent features, embeddings can generalize better to unseen data and capture intricate, nonlinear relationships that sparse representations cannot. Relationship capture. The numerical values within a dense vector allow for meaningful mathematical operations. Nodes with similar characteristics or roles in the graph will have numerically similar embedding vectors. Think of an embedding as a digital fingerprint for a node. While you can't look at the numbers and say, oh, this node is about politics, you can compare two fingerprints. If they're very similar, the two nodes likely share similar properties or roles within the graph. The embedding space, quantifying relationships. When we talk about embeddings, we often refer to the embedding space. This is a multidimensional mathematical space where each node's embedding vector is a point. The beauty of this space is that proximity in the embedding space implies similarity in the original graph. For example, if two nodes are close to each other in the embedding space, it means their embeddings are numerically similar, which in turn indicates they share similar structural roles, communities, or attributes within a graph. Conversely, nodes that are far apart in the embedding space are dissimilar. To quantify this closeness or similarity, we use similarity metrics. Two common ones are Euclidean distance, measures the straight-line distance between 2 points in the embedding space. Smaller distance means higher similarity. Cosine similarity measures the cosine of the angle between two vectors. A value of code snippet indicates identical direction, highly similar. Code snippet indicates orthogonality, no relation, and code snippet indicates opposite direction, highly dissimilar. Cosine similarity is often preferred for high-dimensional data, as it focuses on the orientation of the vectors rather than their magnitude, making it robust to differences in vector length. Node 2vec, capturing topological information. Node 2vec, which we explored in previous sections, is a specific algorithm for generating graph embeddings. It primarily captures topological information about the graph. This means it learns representations based on how nodes are connected and how they appear in random walks across the graph. Specifically, Node 2vec generates embeddings such that nodes that frequently co-occur within short, biased random walks will have similar embeddings. If two nodes are directly connected, they are likely to appear in many of the same short random walks, leading to similar embeddings. If two nodes are not directly connected but share many common neighbors, e.g., they are part of the same community, random walks originating from one might frequently pass through the other's neighborhood, again resulting in SI. Millar embeddings. This mechanism allows Node 2Vec to implicitly learn about community structure, roles, e.g., hub nodes versus peripheral nodes, and other network properties. Beyond topology, GNN embeddings, and feature integration. While Node 2Vec excels at capturing topological information, many real-world graphs also have rich node features attributes associated with each node. For example, in a social network, a user node might have features like age, gender, location, or interests. Graph neural networks, GNNs, are a more advanced family of models that can generate embeddings by simultaneously considering both the graph's topology and the node's features. Node 2Vec embeddings primarily encode who you are connected to and how you are connected. GNN embeddings encode who you are connected to, how you are connected, and what are your inherent characteristics, features. For instance, in a GNN, the embedding of a movie node might not only reflect its connections to actor nodes, but also its inherent features like genre, release year, or average rating. This allows GNNs to create even richer and more contextually aware embeddings. Accessing and interpreting node embeddings. After training a Node 2Vec model or any graph embedding model, the primary output is a set of embeddings for each node. Let's see how to access these embeddings. We assume code snippet is a trained Node 2Vec model object from previous sections. First, we can retrieve the embedding F, or a specific node. Code is not spoken. To get code, please see the link in description or bio. The output code snippet is a Python list of floating point numbers. Each number is a dimension of the embedding vector. The length of this list corresponds to the code snippet parameter you set when configuring Node 2Vec, e.g., 64, 128. These numbers, while not directly interpretable as feature X has value Y, collectively define the node's position in the embedding space. For numerical operations, especially within machine learning pipelines, it's standard practice to convert these Python lists into NumPy arrays. NumPy arrays offer significant performance advantages and are the preferred data structure for numerical computation in Python. Code is not spoken. To get code, please see the link in description or bio. The code snippet attribute of the NumPy array confirms its dimensions. For example, code snippet for a 128-dimensional embedding. While retrieving a single embedding is useful for most machine learning tasks, you'll need the embeddings for all nodes. It's common to store these in a structured format like a pandas data frame, where each row represents a node and each column represents an embedding dimension. Code is not spoken. To get code, please see the link in description or bio. This code snippet is now ready to be used as feature input for downstream machine learning tasks. Each row is a node, and the columns code snippet through code snippet are its learned via. Tours. Quantifying similarity in the embedding space. One of the most powerful aspects of embeddings is the ability to quantify similarity between nodes. Let's demonstrate this using cosine similarity. We'll pick two nodes and calculate how similar their embeddings are. For this example, let's assume we have two nodes, Losing Bin Laden and The Big Short, and we want to see their similarity. Code is not spoken. To get code, please see the link in description or bio. A cosine similarity score close to code snippet indicates that the two nodes are very similar in the embedding space, suggesting they share common structural roles or context within a graph. A score near code snippet suggests they are largely unrelated, and a negative score would imply they are in opposite parts of the embedding space. This numerical similarity is the basis for many downstream applications. Practical applications of graph embeddings. Graph embeddings are incredibly versatile and form the backbone of many advanced graph-based applications in machine learning. 1. Exploratory data analysis, EDA, and visualization. By reducing high-dimensional embeddings to 2D or 3D using techniques like TSNE or UMAP, you can visually inspect clusters of nodes, revealing communities or groups that share similar properties. Outliers in the embedding space might indicate anomalous nodes in the graph. 2. Feature engineering for machine learning models. Node classification, the most direct application. Embeddings of nodes can be used as features to train a classifier, e.g., a logistic regression, or random forest, to predict a node's category or label, e.g., predicting the genre of a movie, the political leaning of a user, or if a transaction is fraudulent. For instance, the code snippet embedding could be used as input to a model predicting if the movie is a documentary or drama. Link prediction. Given two nodes, their embeddings can be combined, e.g., element-wise multiplication, concatenation, to predict the likelihood of a link existing between them, e.g., suggesting new friendships in a social network or recommending products based on user purchase history. Graph classification. Embeddings of entire graphs, often derived by aggregating node embeddings, can be used to classify whole graphs, e.g., classifying chemical compounds based on their molecular graph structure. 3. Recommendation systems. Embeddings of users and items, movies, products, articles can be learned. Users can then be recommended items whose embeddings are closest to their own or to items they've previously interacted with. 4. Anomaly detection. Nodes with embeddings far from their neighbors or existing clusters might be flagged as anomalous, which is useful in fraud detection or cybersecurity. 5. Information retrieval and search. If documents or queries are represented as nodes, their embeddings can be used to find the most relevant documents for a given query by searching for closest EMB. Embeddings. By transforming complex, non-Euclidean graph data into a clean, numerical, and dense format, graph embeddings unlock the full power of traditional machine learning algorithms, enabling sophisticated analysis and prediction on graph structure information. Transforming and visualizing the embeddings. Graph embeddings, generated by techniques like Node2Vec, encapsulate complex network structures into high-dimensional numerical vectors. While powerful, these high-dimensional representations, e.g., 64-dimensional vectors, are not directly interpretable by humans. To unlock insights from these embeddings, we must transform them into a lower-dimensional space, typically 2D or 3D, for visualization. This process is crucial for exploratory data analysis, EDA, helping us identify clusters, outliers, and underlying patterns within the graph data. The importance of visualization. Visualizing embeddings allows us to discover latent structures, identify inherent groupings or communities within the graph that might not be obvious from raw graph data, assess embedding quality, determine if the embeddings effectively capture the relationships and similarities between nodes. Well-formed embeddings should group similar nodes together. Gain intuitive understanding. Translate abstract numerical vectors into interpretable spatial arrangements, fostering a deeper understanding of the network's characteristics. Support downstream tasks. Provide visual validation for features used in machine learning models, such as node classification or link prediction. Dimensionality reduction with UMAP. While various dimensionality reduction techniques exist, e.g., principal component analysis, PCA, T-distributed stochastic neighbor embedding, TSNE, uniform manifold approximation and projection, UMAP, has emerged as a particularly effective method for visualizing high-dimensional data, including graph embeddings. UMAP is a nonlinear dimensionality reduction algorithm that aims to preserve both the local and global structure of the data. Local structure preservation means that points that are close to each other in the high-dimensional space remain close in the low-dimensional projection. Global structure preservation means that the overall shape and relationships between distant clusters are maintained. This balance makes UMAP excellent for revealing meaningful clusters and trends in complex datasets. In contrast, TSNE generally excels at preserving local structure but can distort global relationships, while PCA is a linear technique that primarily preserves global variance but may struggle with nonlinear relationships. UMAP offers a compelling compromise, often producing visually appealing and interpretable layouts while being computationally more efficient than TSNE for large datasets. Understanding UMAP parameters. The quality of a UMAP projection heavily depends on its key parameters. Code snippet. This parameter controls how UMAP balances local versus global structure preservation. It represents the number of nearest neighbors UMAP considers when building the high-dimensional graph. A small code snippet value, e.g., 2 to 10, emphasizes local structure, allowing UMAP to focus on fine details and potentially reveal more tightly packed, distinct clusters. However, it might lead to a fragmented global view. A large code snippet value, e.g., 50 to 200, emphasizes global structure, allowing UMAP to capture broader relationships and ensure that the overall layout reflects the general topology of the data. This can sometimes merge smaller, distinct clusters. The default value is typically 15, which often provides a good balance. Experimentation is key to finding the optimal value for your dataset. Code snippet. This parameter controls how tightly UMAP allows points to be packed together in the low-dimensional space. It sets the minimum distance between embedded points. A small code snippet value, e.g., 0.0, allows points to be very close, resulting in dense, compact clusters. This can make clusters appear more distinct but might obscure internal variations. A large code snippet value, e.g., 0.5 or more, forces points to be more spread out, making the clusters looser and potentially revealing more of the manifold's overall shape. This can be useful for seeing subtle gradations or connections between clusters. The default value is typically 0.1, offering a moderate spread. Code snippet. This is the target dimensionality for the reduced space. For visualization, this is almost always set to 2 for 2D plots or 3 for 3D plots. Code snippet. Setting code snippet ensures that the UMAP algorithm produces the same output every time it is run with the same input data and parameters. TH is crucial for reproducibility of your analyses and visualizations. Without it, slight variations in the initial conditions can lead to different layouts, making comparisons difficult. Visualizing node 2vec embeddings with UMAP. Let's apply UMAP to the node 2vec embeddings generated in the previous section. We'll use the political books dataset, which includes a political underscore alignment attribute for each book, allowing us to color code the visualization and observe how political leanings manifest in the embedding space. First, ensure you have the necessary libraries installed. Code snippet, and code snippet. Code is not spoken. To get code, please see the link in description or bio. These imports provide the necessary tools for numerical operations, code snippet, plotting, code snippet, dimensionality reduction, code snippet, graph manipulation, code snippet, and our embedding model, code snippet. Code snippet is used for file operations like saving plots. To effectively visualize and interpret the embeddings, we need not only the embeddings themselves, but also metadata about the nodes, such as their labels, book titles, and attributes, political alignment, which we'll use for coloring the plot. We'll assume the graph code snippet and the code snippet dictionary from the previous node 2vec run are available. Code is not spoken. To get code, please see the link in description or bio. This initial block ensures that we have our graph code snippet and the code snippet dictionary. It then extracts the embedding vectors into a number py array, which is the required input format for UMAP. Crucially, it also prepares code snippet and code snippet by iterating through the nodes, retrieving their code snippet and code snippet attributes from the code snippet graph object and mapping the alignment to a specific color. This code snippet array will be used to color the points in our scatter plot, making the political clusters visible. Now, we initialize and apply the UMAP model. Code is not spoken. To get code, please see the link in description or bio. Here, we instantiate the code snippet class with code snippet and code snippet, which are good starting points for balancing local and global structure. Code snippet specifies that we want a two-dimensional output for plotting. Code snippet ensures that if you run this code multiple times, you'll get the exact same UMAP layout, which is vital for consistent analysis. The code snippet method then applies the UMAP algorithm, reducing our 64-dimensional embeddings to two-dimensional coordinates. Finally, we visualize the transformed embeddings using matplotlib. Code is not spoken. To get code, please see the link in description or bio. This code generates a scatter plot where each point represents a book node. The X and Y coordinates are the two UMAP dimensions. The code snippet argument colors each point according to its political alignment, making it easy to visually identify clusters. A custom legend is created to explain the color mapping. Finally, a small number of nodes are annotated with their titles, which can be very helpful for interpreting specific clusters or outliers. The plot is saved to a file for easy reference. Interpreting UMAP plots of embeddings. When examining the UMAP plot, look for clusters, groups of points, books that are close to each other indicate similarity in their network context. For the political books dataset, you would likely observe distinct clusters corresponding to liberal and conservative books, with neutral or bridging books potentially positioned between them or forming their own cluster. Separation. The degree to which different color groups are distinct from each other. Good separation suggests that the embeddings effectively capture the differences between categories. Outliers. Points that are far from any main cluster might represent unique or anomalous nodes in the network. For instance, a neutral book that appears deep within a conservative cluster might be a book frequently referenced by conservative readers despite its neutral stance. Continuums. Sometimes, instead of distinct clusters, you might see a smooth transition of colors, indicating a spectrum of relationships rather than clear-cut divisions. This could be the case if political alignment is more of a gradient than a strict categorization. By observing these patterns, you can gain insights into how different types of books are connected and how their political leanings influence their position within the network. Direct 2D node 2-vec embeddings for comparison. While UMAP is excellent for visualizing high-dimensional embeddings, an alternative approach is to directly generate two-dimensional embeddings using node 2-vec by setting the code snippet parameter to 2. This bypasses the need for a separate dimensionality reduction step. However, it's important to understand the trade-offs. Node 2-vec is typically optimized for generating higher dimensional embeddings, e.g., 64 or 128 dimensions, as these can better capture the nuances of complex network structures. Reducing to 2 dimensions directly might lead to a loss of information or a less informative projection compared to UMAP applied to higher dimensional embeddings. Let's generate and visualize 2D embeddings directly from node 2-vec. Code is not spoken. To get code, please see the link in description or bio. Here, we instantiate code snippet with code snippet. The code snippet method then trains the model, and code snippet extracts the resulting two-dimensional vector for each node. This code snippet dictionary is then converted into a number py array suitable for plotting. Now, we plot these direct 2D embeddings. Code is not spoken. To get code, please see the link in description or bio. This plot shows the direct 2D embeddings. Compare its appearance to the UMAP plot. You might notice that the clusters are less distinct or more compressed, or the overall struct. UR is not as clear as the UMAP projection. This is a common outcome when forcing complex high-dimensional data into a very low-dimensional space directly, as the model has fewer degrees of freedom to arrange the points while preserving all relationships. Comparing UMAP and direct 2D node 2-vec visualizations. To directly compare the two visualization approaches, it's often helpful to plot them side by side. Code is not spoken. To get code, please see the link in description or bio. This side-by-side comparison visually highlights the differences. You'll often observe that the UMAP plot provides a clearer separation of clusters and potentially reveals more intricate relationships or a more natural flow between groups. The direct 2D node 2-vec plot, while simpler to generate, might appear more compressed, with less distinct boundaries between groups, especially for complex datasets. When to choose which approach. UMAP, from higher dimensional embeddings. Strengths. Generally produces more interpretable visualizations, preserving both local and global structure. Ideal for complex datasets where fine-grained relationships are important. More flexible as it's a post-processing step. Weaknesses. Requires an additional computational step. Parameter tuning, e.g., code snippet, can influence the output significantly. Use when you want the best possible visual representation of complex relationships, even if it adds a processing step. You've already generated higher-dimensional embeddings for other tasks, e.g., machine learning. Direct 2D node 2vec. Strengths. Simpler and faster as it avoids a separate dimensionality reduction step. Weaknesses. May lose significant information compared to higher dimensional embeddings. The 2D projection might not fully capture the true complexity of the graph structure, leading to less distinct clusters or distorted overall layout. Use when you need a very quick, rough visualization, or when computational resources are extremely limited and generating higher dimensional embeddings followed by UMAP is prohibitive. For simple graphs, it might be sufficient. Limitations of 2D visualizations. While 2D visualizations are incredibly useful, they inherently involve a loss of information when projecting from a high-dimensional space. Distortion. Any projection from higher to lower dimensions will introduce some level of distortion. Points that appear close in 2D might be far apart in the original high-dimensional space, and vice versa. Overlapping points. In very dense or complex datasets, points from different clusters might overlap in 2D, obscuring distinct groups. Limited insight. Some complex relationships or structures might simply not be representable in 2 dimensions. For instance, if your data has intrinsic dimensionality greater than 3, a 2D plot will inevitably flatten out important nuances. For these reasons, 2D visualizations should be used as an exploratory tool to generate hypotheses, not as definitive proof of relationships. When deeper insights are needed, consider 3D visualizations. If supported by your tools, a 3D plot can offer an extra dimension for separation. Quantitative analysis. Complement visualizations with quantitative methods like clustering algorithms, e.g., k-means, DISCAN, on the high-dimensional embeddings to confirm visual clusters and identify their members precisely. Interactive plots. Tools like Plotly or Bokeh allow for interactive exploration, including zooming, panning, and hovering to reveal node labels, which can help navigate crowded plots. Leveraging embeddings for downstream tasks. The process of generating and visualizing embeddings is not an end in itself, but a crucial step towards deeper analysis. The embeddings, whether high-dimensional or reduced, can serve as powerful features for various downstream machine learning tasks. Node classification. Use the embedding vectors as input features to train a classifier, e.g., logistic regression, support vector machine, neural network, to predict node attributes like political alignment, user demographics, or protein function. Link prediction. Predict the likelihood of a connection between 2 nodes based on the similarity of their embeddings. Clustering. Apply unsupervised clustering algorithms directly to the high-dimensional embeddings to formally identify communities or groups within the network without prior knowledge of labels. Anomaly detection. Identify UNIS. UAL nodes whose embeddings are far from any dense cluster, indicating potential anomalies or unique entities in the network. By transforming complex graph structures into numerical embeddings, we bridge the gap between graph theory and traditional machine learning, opening up a vast array of analytical possibilities. Beyond visualization, applications and considerations of N2V embeddings. Leveraging Node 2vec embeddings in machine learning tasks. After generating and visualizing Node 2vec N2V embeddings, the next logical step is to harness their predictive power. These dense, low-dimensional vector representations of nodes can serve as powerful features in various downstream machine learning tasks. By converting complex graph structures into numerical vectors, N2V enables the application of standard machine learning algorithms that typically operate on tabular data. The utility of N2V embeddings extends to several common machine learning paradigms. Node classification, predicting the category or label of a node, e.g., classifying a user as a bot or human determining the political leaning of a book, or identifying the function of a protein in a biological network. The embedding of a node acts as its feature vector, which is then fed into a classifier. Link prediction, inferring the existence of a link between two nodes, or predicting future connections, e.g., recommending friends in a social network, suggesting new products to users based on co-purchase patterns. This is often achieved by calculating the similarity, e.g., cosine similarity, product, or concatenation followed by a classifier, between the embeddings of two nodes. Clustering, grouping similar nodes together based on their structural roles and proximity in the embedding space, e.g., identifying communities in A. Social network, segmenting customers with similar purchasing behaviors. Standard clustering algorithms like k-means or DISCAN can be applied directly to the embedding vectors. Recommendation systems, providing personalized suggestions by finding nodes, items, users with embeddings similar to those a user has interacted with or liked. This leverages the principle that nodes with similar embeddings are structurally similar in the graph. Forecasting, predicting future states or behaviors of nodes or the graph itself based on historical embedding patterns. For instance, if embeddings are generated periodically, their evolution might predict future trends. To illustrate how N2V embeddings are integrated into a machine learning pipeline, consider a simple node classification task. We will generate embeddings for a graph and then use them as input features for a standard classifier, such as a random forest. First, we need to load a graph and generate the node 2vec embeddings. For demonstration, we'll use the well-known Zachary's Karate Club graph and assign some arbitrary labels to its nodes to simulate a classification problem. Code is not spoken. To get code, please see the link in description or bio. This initial setup loads a classic graph and assigns illustrated binary labels to its nodes. These labels simulate the target variable we would want to predict in a node classification task. The code snippet library provides a convenient way to access common graph datasets F, or experimentation. Next, we initialize and train the code snippet model on our graph. This process generates the learned embedding vectors for each node by simulating random walks and applying the word 2vec algorithm. Code is not spoken. To get code, please see the link in description or bio. Here, we configure node 2vec with common parameters. The code snippet method trains the underlying word 2vec model on the sequences of nodes generated by the random walks. The resulting code snippet object, code snippet, stores the vector representation for each node, which can be accessed using the node string ID. Once the embeddings are generated, we prepare them for use with a standard machine learning classifier. This involves creating a feature matrix code snippet, the node embeddings, and a target vector code snippet, the node labels. We then split the data into training and testing sets to evaluate the model's generalization ability. Code is not spoken. To get code, please see the link in description or bio. This step is crucial for transitioning from graph data to a format consumable by traditional ML models. Each row in code snippet represents a node's embedding, and the corresponding entry in code snippet is its label. Stratified splitting code snippet is used to ensure that the proportion of labels in the training and test sets is similar to the original dataset, which is good practice for classification tasks, especially with imbalanced classes. Finally, we train a CL classifier using the prepared training data and evaluate its performance on the unseen test set. Code is not spoken. To get code, please see the link in description or bio. This concludes the practical example of using N2V embeddings for node classification. The random forest classifier is a robust choice that often performs well without extensive hyperparameter tuning. The accuracy score and classification report provide insights into how well the model generalizes to unseen nodes from the original graph. The transductive nature of node 2vec. While powerful for many tasks, node 2vec, like many traditional graph embedding methods, e.g., deep walk, line, is inherently transductive. Understanding this characteristic is critical for knowing when and where to apply N2V effectively, and equally important, when to seek alternative approaches. What is transductive learning? In the context of graph learning, a transductive model learns embeddings for a fixed set of nodes within a specific, already observed graph. It memorizes the structural context of each node present during training. This means fixed graph structure. The model is trained on a static snapshot of the graph. It learns a mapping from a specific node ID to an embedding vector. Node-specific embeddings. Each node gets a unique embedding based on its position and connections within that specific graph. These embeddings are directly optimized for the observed nodes. No generalization function. The model does not LIA. RN, a general function that can generate embeddings for any arbitrary node, especially nodes that were not part of the training graph. Think of it like this. A transductive model is like a student who has memorized all the answers for a specific exam, code snippet. If a new question appears, code snippet, that wasn't on the memorized list, they cannot answer it because they haven't learned a general rule or principle. They've only learned specific instances. Limitations for dynamic or unseen graph data. The transductive nature of N2V poses significant challenges when dealing with dynamic graphs or scenarios where new nodes or edges frequently appear. 1. Inability to handle new nodes. If a new node joins the graph, e.g., a new user on a social media platform, a newly published paper in a citation network, N2V cannot generate an embedding for it without retraining the entire model. The model has no mechanism to infer the embedding of an unseen node. Its knowledge is limited to the nodes it saw during training. 2. Sensitivity to graph evolution. Even small changes in the graph structure, such as the addition or removal of edges, can invalidate existing embeddings. A node's context changes, meaning its embedding should ideally change as well. To reflect these changes accurately, a full retraining is often necessary. 3. Computational overhead of retraining. For a large, dynamic graph, retraining the entire N2V model every time new nodes or significant structural changes occur is computationally prohibitive and time-consuming. The process involves generating a large number of random walks across the entire graph, followed by training a Word2Vec model on these sequences. This can take hours or even days for massive graphs with millions of nodes and edges. This makes N2V unsuitable for real-time applications or systems requiring continuous updates, leading to stale embeddings for new users and potentially outdated embeddings for existing ones. Example: consider a continuously growing social media network where millions of new users join daily and existing users constantly form new connections. Retraining Node2Vec constantly would be infeasible, hindering the ability to provide up-to-date recommendations or perform real-time user classification. When Node2Vec's transductive nature is acceptable or advantageous. Despite these limitations, N2V remains a highly effective choice for specific scenarios. Static or slowly evolving graphs. When a graph structure is largely fixed or changes very infrequently, N2V is an excellent choice. Example: analyzing a fixed historical biological interaction network where the structure is considered stable and new entities are not regularly added to the dataset under analysis. The embeddings generated would provide a comprehensive representation of relationships within that fixed dataset. Example: a citation network of academic papers up to a certain publication year. The graph is static for the period of analysis, and new papers are not continuously added to the analyzed dataset. Offline analysis. For one-off analyses, research, or batch processing where computational cost is less of a concern than the quality of embeddings for a fixed set of nodes. Baseline models. N2V often serves as a strong and competitive baseline for comparing more complex inductive graph learning methods, demonstrating the effectiveness of random walk-based approaches. Transition to inductive learning. Graph neural networks, GNNs. The limitations of transductive approaches like Node2Vec for dynamic graphs led to the development of inductive graph learning methods, most notably graph neural networks, GNNs. GNNs represent a fundamental shift in how embeddings are learned and applied, offering greater flexibility and generalizability. Transductive versus inductive, a core distinction revisited. Let's solidify the distinction between these two learning paradigms. Transductive learning, e.g., Node 2 VEC learns embeddings for specific instances, nodes, observed during training. It's like memorizing individual facts. It cannot generalize to unseen instances or adapt efficiently to structural changes. Inductive learning, e.g., GNNs learns a generalizable function that can compute embeddings for any instance, including those not seen during training. It's like learning a general rule or formula. This function allows the model to process new data dynamically. How GNNs achieve inductive capability. GNNs own the transductive limitation by learning an aggregation function rather than individual node embeddings. They operate on the principle of message passing. 1. Local neighborhood aggregation. Each node iteratively aggregates information, often represented as messages or feature vectors, from its direct neighbors. This aggregation step typically involves a permutation invariant function, e.g., sum, mean, max, that can handle varying numbers of neighbors. 2. Feature transformation. These aggregated messages, along with the node's own features from the previous layer, are then transformed, often through neural network layers like MLPs, to update the node's representation. 3. Layered propagation. This process is repeated for several layers. In each layer, information propagates further across the graph, allowing each node to incorporate information from its multi-hop neighborhood, e.g., a 2-layer GNN considers information from a node's 2-hop neighborhood. Crucially, the aggregation and transformation functions are the learned parameters of the GNN model, not the node embeddings themselves. Once trained, these functions can be applied to any node in any graph, even entirely new graphs, to compute its embedding, as long as the node has a local neighborhood structure and features. This ability to apply a learned function across different graph structures is how GNNs achieve their inductive capability. Node features versus topological information. Another key distinction between N2V and GNNs lies in the input information they primarily leverage. Node 2 VEC primarily focuses on capturing topological information, how nodes are connected, their structural roles, and neighborhood similarities through random walks. While it can be extended with external node features by concatenating them with the embeddings, its core mechanism is derived solely from graph structure. Graph neural networks, GNNs, are designed to inherently incorporate both topological information through the message passing mechanism between neighbors and node features, attributes of individual nodes, such as user demographics, document content, or protein properties. This ability to combine structural context with rich attribute data often leads to more expressive and powerful embeddings, especially when node features are informative. Why GNNs for evolving graph data? The inductive nature and inherent ability to leverage node features make GNNs particularly well-suited for dynamic graphs. GNNs can generate embeddings for newly added nodes or adapt to structural changes, new edges, without full retraining of the entire model. They simply apply the learned aggregation function to the new local neighborhoods. Scalability. They can scale more effectively to very large graphs because they don't need to store an embedding for every single node. Instead, they store the parameters of the aggregation functions. Generalizability. A GNN trained on one graph can potentially generalize entirely new, unseen graphs, as long as they share similar underlying structural patterns or node feature distributions. This is vital for tasks like anomaly detection on unseen graphs or transfer learning across different graph datasets. In summary, while Node 2 VEC provides excellent embeddings for static graphs and serves as a foundational concept in graph representation learning, GNNs represent the next frontier for handling the complexities of real-world, dynamic, and feature-rich graph data. The transition from N2V to GNNs is a move from memorizing specific instances to learning generalizable principles of graph representation. Creating embeddings with a GNN. As we move beyond traditional graph embedding techniques like Node2Vec, it becomes crucial to explore more advanced methods that can handle the complexities of real-world graph data. Graph neural networks, GNNs, represent a powerful paradigm shift in this domain, offering significant advantages, particularly their inherent inductive learning capabilities and their ability to leverage rich node features. Inductive versus transductive learning, a fundamental distinction. The most critical difference between methods like Node2Vec and GNNs lies in their learning paradigm. Transductive versus inductive. Understanding this distinction is key to choosing the right embedding strategy for your graph data. Transductive learning, e.g., Node2Vec, a transductive model, learns embeddings for a fixed set of nodes within a specific, predefined graph. It essentially memorizes the embedding for each node based on its position and connections within that particular graph. If a new node is added to the graph, or if the graph structure changes significantly, the entire model typically needs to be retrained from scratch to generate embeddings for the new or altered graph. Node2Vec, for instance, learns a mapping from each unique node ID to an embedding vector. It cannot generate an embedding for a node it has never seen during training. Inductive learning, e.g., GNNs, an inductive model, in contrast, learns a function or a mapping that can generate embed-in. GS for any node, even those not seen during training. Instead of memorizing individual node embeddings, GNNs learn how to aggregate information from a node's local neighborhood, its direct connections, and their features. This learned aggregation process can then be applied to any node in any graph, provided its neighborhood can be defined. It's akin to learning a general rule rather than a specific fact. Why inductive learning matters for dynamic graphs. Many real-world graphs are not static. They're dynamic, constantly evolving with new nodes, new edges, and changing attributes. Consider these scenarios. Evolving social networks. New users join daily. Existing users form new connections, and old connections might dissolve. A transductive model would struggle immensely here, requiring continuous and expensive retraining. E-commerce product graphs. New products are listed, customers write new reviews, and purchase patterns shift. An inductive model can generate embeddings for newly added products or users without a full system overhaul. Scientific citation networks. New research papers are published daily, forming new citation links. Inductive models can provide embeddings for these new papers, allowing for tasks like identifying emerging research topics or influential new authors. In these dynamic environments, GNNs shine because their inductive nature allows them to generate embeddings for unseen nodes or adapt to structural changes without complete recomputation, making them highly scalable and practical. The power of node features in GNNs. Node2Vec, by design, focuses purely on the structural properties of a graph, generating embeddings based on random walks that capture proximity. While effective for structural tasks, it ignores any rich attributes that might be associated with the nodes themselves. Most real-world entities represented as nodes in a graph come with a wealth of descriptive information. GNNs are inherently designed to incorporate and leverage these node features, also known as node attributes or properties, directly into the embedding generation process. How GNNs incorporate node features. The core mechanism through which GNNs achieve this is often referred to as message passing or neighborhood aggregation. Conceptually, for each node, a GNN performs the following steps iteratively across multiple layers. 1. Feature transformation. Each node's own features are transformed, e.g., via a neural network layer. 2. Message generation. Each node generates a message for its neighbors, typically by transforming its own features. 3. Message aggregation. Each node gathers messages from its direct neighbors. These messages are then aggregated, e.g., averaged, summed, or max pooled, into a single representation of the neighborhood's information. 4. Feature update. The aggregated neighborhood information is combined with the node's own, transformed, features to update the node's representation. This process is repeated for several layers, allowing information to propagate across the graph and enabling each node's final embedding to capture information from its wider neighborhood, encompassing both structural patterns and feature interactions. The GNN learns the optimal transformations and aggregation functions during training. Practical applications benefiting from node features. The ability to integrate node features significantly enhances the richness and utility of the generated embeddings, making GNNs suitable for a broader range of applications. Fraud detection. Beyond just knowing who is connected to whom, knowing details like a user's transaction history, IP address, device information, or account age, all node features, can be critical for identifying suspicious patterns. A GNN can combine network patterns with these attributes to identify fraudulent activities more accurately. Drug discovery. Proteins can be represented as graphs where amino acids are nodes and their bonds are edges. Node features might include the type of amino acid, its charge, or its hydrophobicity. GNNs can learn embeddings that capture both the molecular structure and the chemical properties, leading to better predictions of protein function or drug efficacy. Recommendation systems. When recommending products or content, it's not just about what items are similar or what other users bought. Node features like product categories, descriptions, price, or user demographics and past preferences are vital for personalized and accurate recommendations. Conceptualizing GNN operations. Common architectures. While the detailed mechanics of various GNN architectures are beyond the scope of this introductory section, it's helpful to be aware of some commonly used models that implement the message passing paradigm for generating embeddings. Graph convolutional networks. GCNs, these models generalize the concept of convolution from images to graphs. They learn a specific way to aggregate information from a node's direct neighbors, effectively smoothing or propagating features across the graph. GraphSage, standing for Graph Sample and Aggregate. GraphSage is designed for scalability. Instead of processing the entire graph, it samples a fixed number of neighbors for each node and then aggregates their features. This makes it particularly suitable for large graphs and for inductive learning. Both GCNs and GraphSage, among others, learn a parameterized function that maps a node's local computational graph, its neighborhood structure and features, to a low-dimensional embedding vector. This learned function is what makes them inductive. Choosing the right embedding method. GNNs versus Node2Vec. The choice between a GNN-based approach and a method like Node2Vec depends heavily on the characteristics of your graph data and the requirements of your downstream task. Feature/method Node2Vec graph neural networks, GNNs. Learning paradigm, transductive inductive. Node features does not explicitly use node features, naturally incorporates and leverages node features. Dynamic graphs requires full retraining for new nodes/edges, can generate embeddings for unseen nodes. More adaptable. Primary input graph structure, adjacency list/matrix, graph structure plus node features. Complexity generally simpler to implement and understand. More complex architecture requires deeper ML understanding. Robustness, noisy data, can be robust with scarce/noisy label data due to pure structural reliance, may struggle if node features are very noisy or irrelevant. Use cases static graphs, tasks purely dependent on structural proximity, baseline comparisons dynamic graphs, tasks requiring feature-rich embeddings, generalization to new data. While GNNs offer powerful inductive capabilities and the ability to leverage features, Node2Vec still holds its ground in specific scenarios. Its reliance purely on structural patterns can be an advantage when node features are absent, uninformative, or highly noisy. In such cases, Node2Vec's robustness in capturing fundamental structural patterns might make it a competitive or even preferred choice. However, for most real-world applications involving dynamic graphs or rich node attributes, GNNs provide a more comprehensive and adaptable solution for GNRAT. ING high-quality graph embeddings. Constructing the embeddings. The process of generating graph embeddings has evolved significantly. While traditional methods like Node2Vec, N2V treat embedding generation as a distinct, often pre-processing step, graph neural networks, GNNs, introduce a paradigm shift. They learn graph representations integrally as part of solving a specific machine learning task. This section delves into how GNNs achieve this powerful, unified learning process. The paradigm shift, integrated learning with GNNs. Unlike algorithms that first generate a static set of node embeddings, like Node2Vec, and then feed them into a separate classifier or predictor, graph neural networks operate differently. GNNs are designed to learn the optimal node representations, embeddings, directly within the training loop for a downstream task, such as node classification, link prediction, or graph classification. Imagine you're trying to categorize books in a library. With Node2Vec, you'd first measure every book's similarity to every other book based on their connections, e.g., shared authors, genres, and assign each book a fixed numerical fingerprint embedding. Then, you'd use these fingerprints to train a separate model to predict their category. With a GNN, the process is more dynamic. The GNN itself learns to extract the most relevant features, create the embeddings, from the book's connections while simultaneously trying to predict its category. This means the embeddings are not generic. They are tuned specifically to help solve the categorization problem, making them highly task-aware and often more effective. GNN layers, refining node representations. At the core of a GNN's ability to construct embeddings are its layers. Each GNN layer plays a crucial role in refining the representation of a node by aggregating information from its immediate neighborhood. This process is iterative. As information passes through successive layers, a node's embedding becomes richer, incorporating structural and feature information from increasingly distant neighbors. Consider a simple graph where nodes have initial features, e.g., a movie's genre tags. Code is not spoken. To get code, please see the link in description or bio. This code snippet takes an input feature vector, code snippet, for each node and the graph's code snippet, which defines connections. The code snippet module within it performs the aggregation and transformation. After passing through this layer, each node's original feature vector is updated, now incorporating information from its direct neighbors. If you stack multiple such layers, a node's final embedding will implicitly capture information from neighbors 2 hops away, then 3 hops, and so on, depending on the number of layers. This iterative refinement allows GNNs to build powerful, context-rich representations. Message passing, the heart of GNNs. The mechanism by which GNN layers refine node representations is commonly referred to as message passing. It's an intuitive yet powerful concept. 1. Message generation. Each node generates a message based on its current features or embedding. Often, this involves transforming its own representation. 2. Message passing. Sending these messages are then sent along the edges of the graph to neighboring nodes. 3. Message aggregation. Each node receives messages from its neighbors. It then aggregates these incoming messages, e.g., by summing, averaging, or using a more complex attention mechanism. 4. Update. Finally, the node combines the aggregated messages with its own current representation to compute its new, updated embedding. Think of it like a rumor spreading through a social network. Each person hears the rumor, messages from neighbors, processes it based on their own understanding, aggregation, and then updates their own version of the rumor, new embedding, before potentially spreading it further. The code snippet layer we defined earlier implicitly performs this message passing. It takes the node features, code snippet, and the code snippet to know which nodes are neighbors. For each node, it gathers information from its neighbors, message aggregation, and combines it with its own features to produce a new feature vector. Code is not spoken. To get code, please see the link in description or bio. The output code snippet are the refined representations, where each node's vector has been influenced by its direct neighbors through the message passing process. P. Preliminary embeddings from untrained models. A crucial aspect of GNNs is their ability to generate embeddings even when the model has not been fully trained. This might seem counterintuitive, but it highlights the fundamental mechanism of GNNs. Even with randomly initialized weights, the GNN architecture itself defines a series of transformations and aggregations based on the graph structure. When you pass data through an untrained GNN, the network still performs the computations defined by its layers: message passing, aggregation, transformations. The output will be a set of numerical vectors. These are the preliminary embeddings. While these embeddings won't be optimized for any specific task because the weights are random, they demonstrate that the GNN can extract representations from the graph structure. This capability is invaluable for understanding the GNN's feature extraction mechanism and for debugging. Code is not spoken. To get code, please see the link in description or bio. The code snippet are the raw output of the GNN. While they're valid numerical vectors, their values are arbitrary because the model's weights have not been optimized. However, they clearly show that the GNN structure is capable of producing a representation for each node. Optimization, tailoring embeddings for specific tasks. The true power of GNNs comes during training. The preliminary embeddings generated by the GNN are fed into a downstream task-specific head, e.g., a linear lay. R for classification. A loss function then measures how well the GNN's current embeddings help solve that task. During optimization, e.g., using gradient descent, the GNN's internal weights are adjusted to minimize this loss. This process inherently tunes the message passing and aggregation mechanisms, causing the GNN to learn embeddings that are highly discriminative and relevant to the specific task. Code is not spoken. To get code, please see the link in description or bio. This optimization loop is what transforms the preliminary random embeddings into powerful, task-aware representations, making GNNs a versatile tool for a wide range of graph-based machine learning problems. Defining our GNN architecture. Having explored the foundational concepts of graph neural networks, GNNs, and understood their advantages over methods like Node2Vec for generating embeddings, we now transition to the practical implementation. This section guides you through defining a basic graph convolutional network, GCN, architecture using PyTorch, a widely adopted deep learning framework, and specifically its graph extension, PyTorch Geometric. Our goal is to build a model capable of learning rich, context-aware node embeddings from graph data. Building neural networks with code snippet. In PyTorch, the fundamental building block for all neural networks is the code snippet class. When you define a custom neural network, you typically create a new class that inherits from code snippet. This inheritance provides several crucial functionalities. Parameter management. It automatically tracks all trainable parameters, weights, and biases defined within the module, making it easy to manage them during training, e.g., moving to GPU, saving, loading. Submodule registration. It allows you to compose complex networks by nesting code snippet instances within each other. Hooks. It provides mechanisms for extending functionality, e.g., inspecting gradients. Code snippet method enables moving the entire model and its parameters to a specific device, CPU or GPU. Every code snippet subclass typically defines two key methods. 1. Code snippet, the constructor where you define and initialize the layers and components of your network. These layers are usually instances of other code snippet modules, e.g., code snippet, or in our case, code snippet. 2. Code snippet. This method defines the computational graph of the network. It specifies how the input data, code snippet, flows through the layers defined in code snippet to produce the output. PyTorch automatically generates the backward pass for gradient computation based on the operations defined in code snippet. Let's begin by setting up the necessary imports and defining the basic structure of our GNN class. Code is not spoken. To get code, please see the link in description or bio. Here, we import code snippet, aliased as code snippet, and crucially, code snippet from code snippet. This library is an extension of PyTorch specifically designed for building GNNs, providing optimized implementations of various graph convolutional layers. Our code snippet class inherits from code snippet, and its code snippet method takes 3 parameters. Code snippet, the number of input features per node. This will typically be the dimensionality of the raw node features in your dataset. Code snippet, the dimensionality of the node embeddings after the first GCN layer. This also defines the feature space for the intermediate representation. Code snippet, the dimensionality of the final node embeddings produced by the network. For tasks like node classification, this might correspond to the number of classes, but for general embeddings, it's a design choice for the embedding space size. The code snippet call is essential. It ensures that the constructor of the parent code snippet class is properly initialized, setting up the necessary infrastructure for parameter tracking and other functionalities. Defining the GCN layers and components. Our GNN will consist of 2 code snippet layers, separated by a nonlinear activation function, ReLU, and a regularization layer, dropout. Stacking multiple code snippet layers allows the model to aggregate information from nodes further away in the graph, effectively expanding its receptive field and enabling it to learn more complex global patterns. Code is not spoken. To get code, please see the link in description or bio. Here's a breakdown of the layers. Code snippet. This is our first graph convolutional layer. A code snippet layer performs a specific type of message passing. Conceptually, for each node, it aggregates features from its immediate neighbors and potentially itself, and then transforms these aggregated features using learnable weights. The code snippet parameter specifies the dimensionality of the input features to this layer, and code snippet specifies the dimensionality of its output features. Code snippet. This is the second code snippet layer. It takes the code snippet dimensional features from the first layer's output and transforms them into code snippet dimensional features, which will be our final node embeddings. Code snippet. Dropout is a regularization technique commonly used in neural networks to prevent overfitting. During training, it randomly sets a fraction, code snippet, of the input features to 0 for each update. This forces the network to learn more robust features that are not overly reliant on any single input. The code snippet means 50% of the features will be dropped. Defining the forward pass. The code snippet method orchestrates the flow of data through the defined layers. For GNNs, the code snippet pass typically takes 2 main inputs. 1. Code snippet. The node features, usually a code snippet of shape code snippet. Each row corresponds to a node, and each column to a feature. 2. Code snippet. The graph connectivity, typically a code snippet of shape code snippet in COO coordinate format. The first row lists the source nodes of edges, and the second row lists the destination nodes. Code is not spoken. To get code, please see the link in description or bio. Let's trace the data flow. 1. Code snippet. The input node features code snippet and the graph connectivity code snippet are passed to the first code snippet layer. This layer performs the message passing and feature transformation, outputting a new set of node features with code snippet dimensions. 2. Code snippet. The rectified linear unit, ReLU, activation function is applied element-wise to the output of code snippet. ReLU introduces nonlinearity into the mod L, which is crucial for learning complex, nonlinear relationships in the data. Without nonlinearities, stacking multiple linear layers would simply result in another linear transformation, limiting the model's expressive power. 3. Code snippet. The dropout layer is applied. During training, some of the features are randomly set to 0. During inference evaluation, dropout is automatically disabled by code snippet when code snippet is called, and all features are passed through scale by code snippet to maintain the expected output magnitude. 4. Code snippet. The output from the dropout layer is then passed to the second code snippet layer, which further refines the node features, producing the final code snippet dimensional embeddings. 5. Code snippet. The method returns the final code snippet, which now represents the learned node embeddings for each node in the graph. These embeddings incorporate both the node's initial features and structural information aggregated from its neighborhood through the GCN layers. Instantiating and running the model. Now that we have defined our code snippet model, let's see how to instantiate it and perform a forward pass with dummy data. This will demonstrate the expected input and output tensor shapes. Code is not spoken. To get code, please see the link in description or bio. First, we detect if a GPU, CUDA, is available and set the code snippet accordingly. Then, we define some dummy parameters for the number of nodes initial, node features, hidden layer size, and the desired final embedding dimension. Finally, we instantiate our code snippet model with these parameters and move the entire model to the chosen code snippet using code snippet. Printing the model provides a summary of its layers and their parameters. Next, we create dummy input tensors for node features, code snippet, and graph connectivity, code snippet, that match the expected shapes. Code is not spoken. To get code, please see the link in description or bio. Here, code snippet is a tensor of random numbers representing node features, with code snippet rows and code snippet columns. Code snippet simulates graph connectivity with 2 rows, source and target node IDs, and code snippet columns. Both are moved to the same code snippet as the model. Finally, we perform the forward pass and inspect the output. Code is not spoken. To get code, please see the link in description or bio. We set the model to code snippet mode, which disables dropout and batch normalization if present. We also wrap the forward pass in code snippet to temporarily disable gradient computation, which is beneficial during inference as it saves memory and speeds up computations. The code snippet tensor will have a shape of code snippet, where code snippet is the code snippet we specified. Each row of this tensor represents the learned embedding for a corresponding node. Utilizing the learned embeddings, the code snippet generated by our code snippet model are dense vector representations for each node in the graph. Unlike node 2-vec embeddings, which primarily capture structural proximity, these GNN embeddings are richer because they inherently integrate both the node's initial features and the structural context derived through message passing. These learned embeddings can then be used for a variety of downstream machine learning tasks. Node classification. You can pass these embeddings through a simple linear layer, e.g., code snippet, followed by a softmax activation to classify nodes into categories. Link prediction. Embeddings of 2 nodes connected by a potential link can be combined, e.g., concatenated, the product, and fed into a classifier to predict the existence or type of a link. Graph classification. Node embeddings can be pooled, e.g., averaged, summed, to create a graph-level representation, which can then be used for classifying entire graphs. Visualization. Similar to Node 2-vec, these embeddings can be reduced to 2D or 3D using techniques like TSNE or UMAP for visual exploration of node relationships. This code snippet model serves as a foundational component. In subsequent sections, we will build upon this architecture, train it on real-world datasets, and explore its application in various graph-based learning scenarios. Data preparation. Preparing graph data for graph neural networks, GNNs, is a crucial preliminary step that bridges the gap between raw graph structures and the tensor-based operations required by deep learning frameworks. PyTorch Geometric, PyG, provides specialized tools to streamline this process, converting common graph formats into its proprietary code snippet object and facilitating the initialization of node features, which are fundamental inputs for any GNN. The PyTorch Geometric Code Snippet Object. At the heart of PyTorch Geometric's operations is the code snippet object. This object serves as a flexible container for all components of graph, specifically designed to be compatible with PyTorch tensors and GNN architectures. It holds various attributes, but the most essential for GNNs are code snippet, the node feature matrix. This is a code snippet of shape code snippet, where code snippet is the total number of nodes in the graph, and code snippet is the dimensionality of each node's feature vector. Code snippet, the graph connectivity in a COO coordinate format. This is a code snippet of shape code snippet, where the first row contains the source nodes of each edge and the second row contains the target nodes. This format is highly efficient for sparse graph representations. Code snippet, the node-level or graph-level ground truth labels. This can be a code snippet of shape code snippet for node classification or code snippet for graph classification. Other common attributes include code snippet, edge features, code snippet, node positions for geometric graphs, and code snippet, Boolean mask for data splitting. Converting NetworkX graphs to PyTorch geometric. Often, graph data is initially represented using libraries like NetworkX, which provide rich functionalities for graph manipulation and analysis. To use such graphs within a PyTorch geometric GNN, they must be converted into the code snippet object format. PyG offers a convenient utility function, code snippet, for this purpose. First, ensure you have the necessary libraries imported. We'll also create a simple dummy NetworkX graph to demonstrate the conversion process. Code is not spoken. To get code, please see the link in description or bio. This initial setup establishes a basic NetworkX graph, which is a common starting point for many graph analysis tasks. The code snippet creates a simple linear graph with 5 nodes, 0-1-2-3-4. In a real application, code snippet would likely be loaded from a file, such as a GML file using code snippet, as might have been done in previous sections. Now, we convert this NetworkX graph into a PyTorch geometric code snippet object. Code is not spoken. To get code, please see the link in description or bio. The code snippet function intelligently processes the NetworkX graph. It extracts all nodes and their connectivity, populating code snippet and code snippet respectively. Code snippet is AUT, automatically inferred from the largest node index found in the graph. The code snippet is a code snippet of shape code snippet, representing the graph's adjacency list in a compact, efficient format suitable for GNN message passing. Each column code snippet indicates a directed edge from node code snippet to node code snippet. For undirected graphs, code snippet typically creates 2 directed edges for each undirected edge, e.g., code snippet and code snippet. Notice that code snippet is code snippet after the initial conversion. This is because our dummy NetworkX graph did not have any explicit node features assigned. This leads us to the next crucial step, initializing node features. Initializing node features, code snippet. Node features, code snippet, are paramount for GNNs. They provide the initial information that the GNN layers will transform and aggregate. There are 2 primary strategies for initializing code snippet when explicit features are not directly available or when you wish to leverage pre-computed embeddings. Strategy 1. Random initialization with Xavier uniform. When your raw graph data lacks inherent node features, or if you want the GNN to learn features entirely from the graph structure and the task itself, you can initialize code snippet with random values. However, simple random initialization can lead to unstable training, particularly in deeper networks, due to vanishing or exploding gradients. Xavier Glorot initialization is a widely adopted technique that helps mitigate these issues by scaling initial weights or features, in this context, based on the input and output dimensions. Code is not spoken. To get code, please see the link in description or bio. Here, code snippet creates a tensor filled with random numbers drawn from a standard normal distribution. The shape code snippet ensures that each node has a feature vector of the specified code snippet. The choice of 64 dimensions is arbitrary but common in many GNN applications, often balancing model capacity with computational efficiency. It's a hyperparameter that can be tuned. Now, we apply Xavier uniform initialization. Code is not spoken. To get code, please see the link in description or bio. Xavier uniform initialization, and its normal counterpart, scales the initial values such that the variance of the activations remains roughly the same across all layers. This is crucial for stable training, especially in deeper neural networks, because it prevents gradients from becoming extremely small, vanishing, or extremely large, exploding, as they propagate back through the network during backpropagation. 4 node features. Applying Xavier initialization ensures that the initial input to the first GNN layer is well-scaled, contributing to faster convergence and better performance. This is generally preferred over simple random initialization when no meaningful initial features are available. Strategy 2. Using pre-computed embeddings, e.g. N2V. An alternative and often powerful strategy is to leverage pre-computed node embeddings from traditional methods, such as Node2Vec, N2V, as the initial node features for your GNN. This approach allows the GNN to benefit from structural insights already captured by these embeddings, potentially improving performance, especially when the GNN's training data is limited or when the downstream task heavily relies on the graph's topology. Assume code snippet is a list of lists or a number py array containing the embeddings for each node, obtained from a previous step, e.g., from a network X code snippet model. Code is not spoken. To get code, please see the link in description or bio. Using pre-computed embeddings like N2V as GNN input features offers several benefits. Leveraging structural information. N2V embeddings are designed to capture the structural context of nodes within the graph. By using them as initial features, the GNN starts with a rich representation of the graph's topology. This is particularly beneficial when the GNN needs to learn complex structural patterns. Cold start/limited data. In scenarios where the GNN has limited labeled training data, pre-trained embeddings can provide a strong cold start, guiding the learning process and potentially leading to better generalization. Complementary information. Even if the GNN is designed to learn features from scratch, N2V embeddings can provide complementary information, especially if the task benefits from both local struct URL information captured by N2V and global graph patterns learned by the GNN. Conversely, random initialization is suitable when features are expected to be learned. The GNN is designed to learn features entirely from the graph structure and the specific downstream task, without relying on pre-existing representations. No meaningful pre-existing features. When there are no domain-specific features or pre-computed embeddings available, random initialization provides a neutral starting point. Computational constraints. Generating complex embeddings like N2V can be computationally intensive for very large graphs. Random initialization is computationally cheaper. The choice between these two strategies depends on the nature of your graph, the availability of pre-computed embeddings, and the specific requirements of your GNN task. It's often a good practice to experiment with both to see which yields better results. Passing prepared data to the GNN model. Once code snippet, node features, and code snippet, graph connectivity, are properly populated within the code snippet object, they are ready to be fed into your GNN model. The GNN architecture defined in the previous section, such as code snippet, is designed to accept these two primary inputs. Code is not spoken. To get code, please see the link in description or bio. The code snippet tensor serves as the initial feature representation for each node, which the GNN layers will iteratively transform and aggregate BAS. And on the graph's topology defined by code snippet. This process of message passing allows nodes to exchange information with their neighbors, enabling the GNN to learn rich, context-aware node representations for tasks like node classification, link prediction, or graph classification. By meticulously preparing the code snippet object, you ensure that your GNN receives inputs in the correct format and with appropriate initial feature scaling, laying a solid foundation for effective model training and performance. Passing the graph through the GNN. This section bridges the gap between defining a graph neural network, GNN, architecture, and its practical application. Our goal is to demonstrate the forward pass, or inference, of a GNN, which produces node embeddings. This process sets the stage for subsequent training or downstream tasks. We will also prepare these GNN-generated embeddings for visualization, allowing for a direct comparison with the Node2Vec embeddings created in previous sections. Setting up for inference. When working with PyTorch models, it's crucial to distinguish between the training phase and the inference or evaluation phase. Certain layers within a neural network, such as code snippet and code snippet batch normalization, behave differently depending on the mode. To ensure consistent and deterministic predictions during inference, we apply specific PyTorch idioms. Preparing the model for inference, code snippet and code snippet. Two key practices ensure a PyTorch model behaves correctly during inference. Code snippet. This method sets all modules in the model to evaluation mode. Its primary effects are on dropout layers. During training, dropout layers randomly set a fraction of input units to 0 to prevent overfitting. When code snippet is called, dropout layers are disabled, meaning all neurons are active and predictions become deterministic and consistent. Batch normalization layers. During training, batch normalization layers calculate and use statistics, mean, and variance from the current mini-batch to normalize activations. In evaluation mode, code snippet instructs these layers to use the running statistics, mean, and variance accumulated during training rather than batch-specific statistics. This is critical for consistent predictions, especially when batch sizes during inference might differ from training or when processing individual samples. Code snippet. This context manager disables gradient calculation. During the training process, PyTorch automatically builds a computation graph to track all operations on tensors. This graph is essential for calculating gradients via backpropagation, which are then used to update the model's weights. For inference, however, we do not need to update model weights, nor do we need to calculate gradients. Using code snippet prevents PyTorch from building this computation graph, which significantly saves memory by not storing intermediate activations required for gradient computation. It also speeds up computations because PyTorch doesn't need to perform the overhead of tracking operations. Crucially, it prevents accidental modification of model weights, ensuring the model remains static for inference. Let's illustrate the effects of code snippet and code snippet with a simplified example using a dummy PyTorch model. Code is not spoken. To get code, please see the link in description or bio. In this example, if you were to run the code snippet line multiple times, you might observe slight variations due to the random nature of dropout. However, code snippet would be identical on repeated runs with the same code snippet because code snippet is disabled by code snippet. While the effect of code snippet is more evident during actual training and validation cycles, the principle holds. Code snippet and code snippet ensure deterministic and resource-efficient inference, generating untrained GNN embeddings. Now, we'll apply these principles to our code snippet model to generate initial node embeddings. It's important to understand that these embeddings are untrained. This means the GNN's internal weights have not been optimized through a learning process to perform a specific task, like node classification or link prediction. Instead, these initial embeddings primarily reflect the structural information of the graph and the initial node features, code snippet, as propagated through the GNN's layers. Recall from the data preparation section that code snippet represents our node features, e.g., randomly initialized features or pre-computed node 2 vec embeddings, and code snippet defines the graph connectivity. The code snippet parameter, set to 64 in this example, defines the dimensionality of the intermediate layers and the final output embeddings produced by our GNN. This value is often chosen based on several factors. Empirical performance. Common practice for many graph datasets suggests 64 or 128 dimensions often strike a good ball. And it's between expressiveness, ability to capture complex patterns, and computational efficiency. Comparison with other methods. It might be set to match the output dimensionality of other embedding methods, such as Node 2 vec, to facilitate direct comparison. Downstream task requirements. The specific requirements of the subsequent machine learning task might influence the desired embedding dimension. Code is not spoken. To get code, please see the link in description or bio. In this code block, we first instantiate our code snippet model. We derive code snippet from the shape of our input node features, code snippet, and set code snippet to 64. Immediately after instantiation, we call code snippet to prepare the model for inference. The core operation is the forward pass, code snippet. This implicitly invokes the code snippet method of our code snippet, orchestrating the message passing process. How the GNN forms untrained embeddings. Even with randomly initialized weights, the GNN's forward pass is a powerful operation that fundamentally processes graph structure. It performs localized computations that aggregate information from each node's direct neighbors and potentially neighbors of neighbors, depending on the number of GNN layers. During this process, 1. Initial features. Each node begins with its initial set of features, code snippet. 2. Message generation. In each GNN layer, nodes generate messages, transform versions of their own features, to send to their neighbors. 3. Message aggregation. Each node collects and combines the messages it receives from its neighbors. Common aggregation functions include summation, mean, or max pooling. 4. Feature transformation. The aggregated information is then combined with the node's own, transformed, features and passed through a neural network layer, e.g., a linear transformation followed by an activation function. This sequence of message passing, aggregation, and transformation is repeated for each layer in the GNN. Even with randomly initialized weights, this structural aggregation means that nodes that are structurally similar, e.g., share many common neighbors, belong to the same dense community, or are connected via short paths, will tend to have more similar embeddings than nodes that are far apart in the graph. This inherent ability to encode structural context, even without task-specific training, is what makes these initial GNN embeddings intrinsically meaningful. Preparing embeddings for visualization. The code snippet tensor we just generated is a PyTorch tensor. Depending on your hardware setup, it might reside on a GPU. For compatibility with many common data analysis and visualization libraries, such as UMAP or scikit-learn, we typically need to convert this tensor into a number py array and ensure it's on the CPU. Code is not spoken. To get code, please see the link in description or bio. This sequence of calls, code snippet, is a standard and robust practice when preparing PyTorch tensors for use with other Python libraries. Code snippet. This is a critical step. It creates a new tensor that is detached from the current computation graph. If you omit this, PyTorch will try to keep track of the operations on code snippet, which is unnecessary and memory-intensive for visualization or simple analysis. Code snippet. If you're running on a machine with a GPU, code snippet will likely be on the GPU. Most visualization libraries and general-purpose CPU-bound operations require data to be in system RAM. This method safely moves the tensor to the CPU. Code snippet. Finally, this converts the PyTorch tensor, which must be on the CPU, into a number py array. Number py arrays are the foundational data structure for numerical operations in Python's scientific computing landscape. Comparing GNN embeddings with Node 2-vec embeddings. With code snippet now containing the 64-dimensional representations of each node from our untrained GNN, we can compare them to the Node 2-vec, N2V, embeddings generated previously. Visualizing both sets using dimensionality reduction techniques like UMAP, uniform manifold approximation and projection, allows for a qualitative comparison of how each method captures and organizes graph structure. While both N2V and GNNs aim to represent nodes in a low-dimensional space, they achieve this through fundamentally different mechanisms, leading to distinct characteristics in their embeddings. Node 2-vec, N2V, this is a transductive method based on biased random walks. It learns embeddings by preserving various neighborhood relationships, controlled by hyperparameters for BFS-like versus DFS-like walks. Its focus is purely topological. It does not inherently incorporate node features unless they are used to modify the random walk probabilities. N2V generates embeddings for a fixed set of nodes in a given graph. If new nodes are added or the graph changes significantly, the entire embedding process typically needs to be rerun. Graph neural networks, GNNs, these are inductive methods that learn a function, a mapping, from node features and graph structure to embeddings. GNNs explicitly aggregate information from neighbors through message passing. This allows them to incorporate node features directly into the embedding process. A trained GNN can generalize to unseen nodes or even entirely new graphs, provided the feature space is consistent, making it suitable for dynamic or evolving graph structures. Even an untrained GNN leverages this inductive capability to propagate initial feature information across the graph. When visualizing these untrained GNN embeddings and comparing them to N2VEC embeddings using UMAP, you might observe initial GNN clustering. Even untrained GNN embeddings often show some degree of clustering based on structural similarity and the initial code snippet. This is because the message passing mechanism naturally groups nodes that are part of the same local neighborhood or subgraph. PHS. Differences in patterns. N2V embeddings might show very clear, distinct clusters if the graph has strong, well-defined community structures, as it excels at preserving these topological relationships. Untrained GNN embeddings, while also reflecting structure, might show slightly more diffuse or different clustering patterns, especially if the initial code snippet, node features, were random or contained rich information not captured by N2V's purely topological approach. The way GNNs combine initial features with topology can lead to unique representations. For instance, if code snippet contained categorical features, the GNN might begin to group nodes not just by connections, but also by shared feature attributes, even in its untrained state. Using GNN embeddings for downstream tasks. The primary purpose of generating node embeddings is to use them as input for various downstream machine learning tasks. These embeddings capture rich information about the nodes and their context within the graph, making them valuable features. Even untrained embeddings can be surprisingly useful for exploratory analysis or as a baseline for simple tasks, purely based on the structural and initial feature information they encode. For instance, they could be used for node classification, predicting a label or category for each node, e.g., categorizing books by genre based on their connections and initial features. Node clustering, grouping similar nodes together, e.g., identifying immunities of interest in a social network or groups of related products in a recommendation system. For example, untrained GNN embeddings could help identify initial communities of books purely based on their co-citation patterns or shared topics, even before any supervised training. Link prediction, predicting whether a link should exist between two nodes. Anomaly detection, identifying unusual nodes based on their embedding's deviation from typical patterns within the embedding space. Let's demonstrate how these code snippet could be used as input to a simple classifier from scikit-learn. For this example, we'll assume you have some hypothetical code snippet that correspond to your nodes. In a real-world scenario, these labels would be part of your dataset for a supervised learning task. Code is not spoken. To get code, please see the link in description or bio. This example illustrates the fundamental step of using the generated embeddings as features for a machine learning model. While the accuracy with untrained embeddings might be low for complex tasks, as they haven't been optimized for classification, it establishes a baseline and confirms their usability as input features. If the GNN were trained for a specific task, e.g., using a node classification loss function and backpropagation to optimize its weights, its embeddings would become much more discriminative and task-specific. This would lead to significantly better performance in downstream tasks, and clustering observed in UMAP visualizations would also become much tighter and more clearly separated according to the learned task. GNN versus N2V embeddings. The fundamental distinction: inductive versus transductive learning. Graph embeddings are crucial for representing nodes in a low-dimensional vector space, enabling downstream machine learning tasks such as node classification, link prediction, and clustering. While both node 2VEC, N2V, and graph neural networks, GNNs, generate such embeddings, they operate under fundamentally different learning paradigms, transductive and inductive, respectively. Understanding this distinction is paramount for choosing the appropriate embedding technique for a given problem and understanding the implications for model generalization. Transductive learning, Node 2-VEC, N2V. Transductive learning refers to a scenario where a model learns from a fixed set of training data and can only make predictions on those specific data points or points highly similar and present during training. It is not generalized to unseen data. Node 2-VEC is an inherently transductive method. It learns node embeddings by performing biased random walks on a predefined static graph. The algorithm effectively learns a mapping from each specific node ID in the training graph to its corresponding embedding vector. Fixed graph dependency. N2V's embeddings are intrinsically tied to the exact structure of the graph it was trained on. This means the model learns a direct mapping from a node's identity, its position within the specific training graph, to its embedding. No generalization to unseen nodes. If new nodes are added to the graph, or if the graph structure significantly changes, e.g., edges are added or removed, the entire N2-VEC model typically needs to be retrained from scratch. This is because the random walks, and thus the learned neighborhood context, would change for existing nodes, and new nodes would have no pre-computed embedding. N2V cannot generate embeddings for nodes that were not part of its training graph. Purely topological, N2V primarily leverages the graph's topology, connectivity patterns, to generate embeddings. While it can capture complex neighborhood structures based on local, random walks, it does not directly incorporate any intrinsic features associated with the nodes themselves, e.g., user age, document content, molecular properties. Its embeddings are solely based on how nodes are connected. Inductive learning, graph neural networks, GNNs. In contrast, inductive learning refers to the ability of a model to generalize its learned patterns to unseen data. An inductively trained model can make predictions on new, previously unencountered data points, or even entirely new datasets without requiring full retraining. Graph neural networks are inherently inductive models. They learn a function that maps a node's local neighborhood structure and its features to an embedding. This function is learned during training and can then be applied to any node, regardless of whether it was seen during training. Generalization to new nodes, GNNs, AC, have inductive capability through their fundamental message passing mechanism. Instead of learning an embedding for each specific node ID, a GNN learns how to aggregate information from a node's immediate neighbors and their neighbors, depending on the number of layers. When a new node appears in the graph, its embedding can be computed by applying the same learned aggregation function to its neighbors' information, even if those neighbors or the new node itself are not present during the initial training. The GNN learns a rule for computing an embedding, not a lookup table for specific node IDs. Incorporation of node features. A significant advantage of GNNs is their seamless ability to incorporate node features, e.g., attributes of users, properties of molecules, content of documents. The message passing mechanism processes these features along with the graph structure. This allows GNNs to create much richer representations that capture not only the topological role of a node, but also its intrinsic characteristics. For instance, in a social network, a GNN might embed a user based on their connections and their demographic information, leading to more nuanced embeddings than N2V's purely structural approach. Adaptability to dynamic graphs. Because GNNs learn a generalizable function, they are far better suited for dynamic graph environments, such as continually updated social networks, evolving transaction graphs for fraud detection, or biological networks where new proteins or interactions are discovered. When new nodes or edges appear, the GNN can often compute updated embeddings efficiently without extensive retraining of the entire model. How GNNs achieve inductive learning. The message passing paradigm. The core mechanism enabling GNN's inductive power is message passing. Unlike N2V, which relies on global random walks and then trains a shallow neural network on node ID, context, pairs, GNNs build node embeddings iteratively by aggregating information from their local neighbors. At each layer of a GNN, a node's representation, embedding is updated by 1. Collecting messages. Each neighbor of a node generates a message based on its current representation and potentially the edge connecting them. These messages are then sent to the central node. 2. Aggregating messages. The central node collects all messages from its neighbors and combines them using a permutation invariant aggregation function. Permutation invariant means the order in which the neighbor's messages are received does not affect the final aggregated result, e.g., sum, mean, max. This ensures that the GNN learns a general aggregation rule, not one dependent on neighbor order. 3. Updating node representation. The aggregated information, combined with the node's own feature vector from the previous layer, is then transformed, e.g., through a neural network layer, to produce the node's new, enriched representation for the current layer. This transformation often involves nonlinear activation functions. This iterative process can be visualized as a neighborhood information flow. Each node's final embedding is a compressed representation of its local computational graph, which includes its own features and the aggregated features of its neighbors up to a certain hop distance, determined by the number of GNN layers. When a new node is introduced to the graph, as long as it has neighbors, the GNN can apply this same learned aggregation and transformation function to its new local neighborhood to compute its embedding. The model doesn't need to learn about the new node directly. It just needs to apply its existing learned rules for processing graph neighborhoods. This is a crucial distinction that makes GNNs highly adaptable. Practical implications and use cases. The choice between GNN and N2V often boils down to the nature of your graph data and the specific application requirements. Scenarios favoring GNNs inductive. GNNs are particularly well suited for scenarios where generalization to unseen data is critical or where node attributes are important for rich representations. Dynamic graphs. When the graph structure changes frequently or new nodes/edges are added constantly. Example, fraud detection in financial networks. In a transaction graph, new users, nodes, join daily, and new transactions, edges, occur continuously. A GNN can learn to identify suspicious patterns among new users and their connections without needing to retrain the entire model every time a new user registers or a new transaction occurs. The model can quickly adapt to the evolving network. Example, recommendation systems with evolving users/items. For platforms with new users or items frequently entering the system, GNNs can recommend new content to new users by leveraging their initial interactions and features, as well as the features and interactions of their neighbors. This avoids the cold start problem where new entities have no historical data. Leveraging rich node features. When rich node attributes are available and crucial for distinguishing nodes beyond their connectivity. Example, drug discovery and materials science, representing molecules as graphs where atoms are nodes and chemical bonds are edges. Node features might include atomic number, charge, hybridization, and other chemical properties. GNNs can leverage these features along with the molecular structure to predict drug properties, molecular stability, or material characteristics more accurately than purely topological methods. Transfer learning across graphs. When you want to apply a model trained on one graph to a completely different unseen graph, e.g., training on a social network and applying to a citation network, assuming similar underlying patterns. The learned aggregation functions can potentially transfer. Scenarios where N2V might still be preferred, transductive. Despite GNN's inductive advantages, N2V can still be a viable or then preferred choice in specific situations. Static graphs. When a graph is largely fixed and changes are infrequent or negligible. Example, analyzing a historical social network snapshot. If you're analyzing a dataset of a social network at a specific, fixed point in time, N2V can generate highly effective embeddings based on its exhaustive exploration of that static structure. The goal is to understand the existing network, not to predict future changes. Example, fixed protein-protein interaction network. For a well-defined biological network that is not expected to change significantly, N2V can provide robust embeddings for known proteins based purely on their interaction patterns. Computational efficiency for static graphs. For very large static graphs, N2V can sometimes be computationally less demanding to train initially compared to complex GNN architectures, especially when GPU resources are limited or when the graph is sparse. Its random walk generation can be highly parallelized. Scarcity of labeled data. In scenarios where labeled data for a supervised task is extremely scarce, N2V, being an unsupervised embedding method, it learns embeddings without requiring explicit labels, can be a viable initial step to generate representations. These embeddings can then be used as input to a simple downstream supervised classifier. GNNs, while also having unsupervised variants, often shine brightest when some form of labeled data or task-specific objective is available. E for fine-tuning. Simplicity and interpretability. N2V is conceptually simpler, and its random walk mechanism can sometimes offer a more intuitive understanding of how neighborhood contexts are captured compared to the more abstract message passing and nonlinear transformations of GNNs. Extensions to Node 2Vec. It's worth noting that researchers have explored extensions to transductive embedding methods like Node 2Vec to imbue them with some inductive capabilities. For instance, GraphSage, while often categorized as a GNN, was specifically designed to learn a function for generating node embeddings by sampling and aggregating features from a node's local neighborhood, making it inherently inductive. Other approaches involve learning an encoder that maps node attributes to embeddings, which can then generalize to new nodes with similar attributes. However, these methods often borrow heavily from the GNN paradigm, underscoring the inherent advantages of GNNs for inductive tasks. They demonstrate a convergence towards learning generalizable aggregation functions rather than specific node representations. Summary comparison: GNN versus Node 2Vec embeddings. For quick reference, the table below summarizes the key differences and considerations when choosing between GNN and Node 2Vec embeddings. Feature graph neural networks, GNNs, Node 2Vec, and N2V. Learning paradigm: inductive, transductive. New node handling can generate embeddings for unseen nodes without retraining requires full retraining for new nodes/graph changes. Input graph structure plus node features graph structure, purely topological. Embedding basis, aggregated local neighborhood information, plus node features context from biased random walks. Generalization high, learns a function to map neighborhoods to embeddings low, learns embeddings for specific node IDs. Applicability: dynamic graphs, graphs with rich node features, transfer learning static graphs when only topology matters. Representation richer, captures both topology and intrinsic node properties, primarily topological, captures structural roles. Computational cost can be higher for training complex models, but efficient for inference on new nodes, can be efficient for initial training on static graphs, but costly for updates. Common use cases: fraud detection, recommendation systems, drug discovery, semantic parsing, social network analysis, fixed snapshot, fixed knowledge graph analysis. Pros: generalizes well, utilizes node features, adaptable to evolving graphs, simpler, effective for static graphs, unsupervised. Cons: can be more complex to design/train, may require node features for optimal performance, not suitable for dynamic graphs, cannot generalize to unseen nodes, ignores node features. This comparative analysis highlights why GNNs are the predominant method for many modern graph-based machine learning applications, especially those involving dynamic data or requiring rich, attribute-aware representations. Their inductive nature aligns perfectly with the need for models that can adapt and generalize in real-world, ever-changing environments. GNN versus N2V embeddings. Understanding the fundamental differences between various graph embedding techniques is crucial for selecting the most appropriate method for a given task. This section focuses on a direct comparison between graph neural network, GNN, embeddings and Node 2-VEC, N2V, embeddings, highlighting their distinct learning paradigms. Inductive versus transductive. Inductive versus transductive learning. These terms describe how a machine learning model generalizes to unseen data. Transductive learning. The case of Node 2-VEC. Transductive learning models are designed to make predictions only on the specific data points observed during training. They do not learn a general mapping or function that can be applied to new, unseen data points. Node 2-VEC is a prime example of a transductive embedding method. Here's why. 1. Node identity-centric. N2V operates by simulating random walks on the graph, and then using algorithms like Word2-VEC to learn embeddings. Crucially, it learns a distinct, fixed vector representation for each individual node ID present in the graph at the time of training. 2. Fixed embedding space. The embedding space generated by N2V is tied directly to the nodes in the training graph. If a new node is added to the graph, or if the graph structure changes significantly, the N2V model cannot generate an embedding for that new node without being entirely retrained on the updated graph. This retraining process can be computationally expensive and time-consuming, especially for large dynamic graphs. 3. No generalization function. N2V does not learn a function that maps node features or local neighborhood structures to an embedding. Instead, it learns a lookup table where each node ID corresponds to an embedding vector. This means it cannot generalize to nodes it has never seen before. Consider a social network. If an N2V model is trained on a snapshot of the network from yesterday, it has embeddings for all users active yesterday. When new users join today, the N2V model has no mechanism to generate embeddings for them. It lacks the ability to infer representations for these new users based on their attributes or connections to existing users. Inductive learning, the power of GNNs. In contrast, inductive learning models learn a general function or rule from the training data that can then be applied to new, unseen data points to make predictions. These models can generalize beyond the specific instances they were trained on. Graph neural networks, GNNs, embody inductive learning in the context of graph data. 1. Feature and structure-based learning. GNNs learn an aggregation and update function. These functions operate on the features of a node and the features of its neighbors, as well as the local graph structure, how neighbors are connected. They do not learn embeddings based on unique node IDs. 2. Generalizable functions. Because GNNs learn these generalizable functions, e.g., how to aggregate information from neighbor, RS, how to transform node features. They can process any node, even one not seen during training, as long as that node exists within a graph and has a similar feature space. 3. Adaptability to new nodes and graphs. A trained GNN model can generate embeddings for new nodes added to an existing graph, or even for nodes in an entirely new graph, without requiring full retraining. This is a significant advantage for dynamic graph environments. The GNN applies its learned aggregation and update rules to the new node's features and its connections, producing a relevant embedding. When we refer to similar feature spaces for GNN adaptability, it means that the new nodes or graphs must have the same number and type of features as the nodes used during training. For example, if a GNN was trained on nodes with features like code snippet, and code snippet, it can embed new nodes that also have these features, even if the specific values differ or the new node was not part of the training graph. Practical implications and adaptability. The distinction between inductive and transductive learning has profound practical implications, especially for real-world applications involving evolving or dynamic graph data. Dynamic graph scenarios, where GNNs excel. Many real-world graph datasets are inherently dynamic, meaning nodes and edges are constantly being added, removed, or modified. Social networks. New users join daily. Existing users form new connections. An N2V model. Trained yesterday couldn't embed today's new users or account for new connections without being retrained on the entire, updated graph. A GNN, however, could readily process the features of new users and their connections to existing nodes to generate meaningful embeddings. Recommendation systems. In e-commerce, new products are listed and new users sign up constantly. A GNN-based recommendation system can adapt to these changes by learning embeddings for new items or users based on their attributes and interactions, enabling real-time recommendations. Fraud detection. In financial transaction networks, new accounts are opened and new transaction patterns emerge. GNNs can identify suspicious new entities or behaviors by generalizing from learned patterns, making them suitable for real-time anomaly detection. In these dynamic environments, the ability of GNNs to generalize to unseen nodes or even entirely new subgraphs without complete retraining makes them a superior choice. Retraining a large-scale N2V model daily or hourly is often computationally infeasible. Static graph scenarios, where N2V might still be viable. While the inductive nature of GNNs offers significant advantages, there are specific scenarios where transductive methods like N2V might still be considered or even preferred. Historical, fixed datasets. For a historical dataset of protein-protein interactions where no new proteins are expected, or for analyzing a fixed, archive citation network, N2V MIG. HTB sufficient for initial analysis. If generalization to new entities is not a concern, and the focus is purely on understanding the relationships within a static graph, N2V can provide strong local structural embeddings. Focus on fine-grained local structure. Due to its random walk approach, N2V can sometimes capture very fine-grained local structural patterns and community information on a fixed graph, which might be beneficial in specific niche cases where such highly localized insights are paramount and generalization is not required. However, even in static graph analysis, the ability of GNNs to leverage node features, which N2V typically does not directly incorporate into its embedding generation process, beyond using them for node similarity in some variants, often provides richer and more informative embeddings. Key differences: GNN versus N2V embeddings. The following table summarizes the core distinctions between GNN and N2V embeddings. Featured node 2vec, N2V, embeddings GNN embeddings. Learning paradigm, transductive inductive. Adaptability to new nodes, cannot embed new nodes without full retraining, can embed new nodes/graphs without retraining. Requires retraining yes, for any graph structural change, or new nodes no, for new nodes/minor structural changes. Uses node features typey. Kali no, focuses on graph structure via random walks. Yes, integral to the message passing process. Focus learns fixed embeddings for specific node IDs, learns general functions, aggregation, update, that operate on features and local structure. Generalization, poor generalization to unseen data, strong generalization to unseen data/graphs. Primary use case, static graphs, fixed datasets, dynamic, evolving graphs, generalization to new data. Underlying mechanism, random walks plus word 2vec, like skipgram message passing and aggregation over neighborhood. In conclusion, while N2V offers a simple and effective way to generate embeddings for static graphs, the inductive nature of GNNs, their ability to leverage node features, and their inherent adaptability to dynamic graph environments make them a more powerful and versatile tool for a wide range of modern graph-based machine learning applications. This inherent advantage is why subsequent sections of this book will primarily focus on graph neural networks. GNN versus N2V embeddings. Graph embeddings are fundamental for applying machine learning techniques to graph-structured data. They transform nodes, or edges, or entire graphs into lower-dimensional vector representations, making them compatible with standard machine learning algorithms. While various methods exist, node 2vec, N2V, and graph neural networks, GNNs, represent two distinct paradigms for generating these embeddings. Understanding their core differences particularly in their learning mechanisms and feature integration, is crucial for choosing the appropriate method for a given task. Node 2-Vec, a transductive, topology-focused approach. Node 2-Vec is a prominent example of a traditional graph embedding technique that primarily focuses on capturing the topological structure of a graph. It extends the word 2-Vec idea to networks by generating node sentences through biased random walks. At its core, N2V operates by 1. Simulating random walks. Starting from each node, it performs a series of random walks, creating sequences of nodes. The bias in these walks allows for exploring neighborhoods that are either more breadth-first search, BFS, like emphasizing local connectivity, or depth-first search, DFS, like emphasizing structural equivalences further away. 2. Applying word 2-Vec. These generated node sequences are then treated as sentences, and nodes within these sequences are treated as words. A skipgram model, similar to word 2-Vec, is trained to predict cont. EXT nodes given a target node, or vice versa. The resulting node embeddings are the learned representations from this process. Consider a simple graph where we want to generate embeddings. Code is not spoken. To get code, please see the link in description or bio. This initial code snippet defines a small, static graph using the code snippet library. This graph will serve as the input for our conceptual node 2-Vec embedding process. Notice that at this stage, we are only defining the connections between nodes, not any inherent properties or features of the nodes themselves. Code is not spoken. To get code, please see the link in description or bio. Here, we instantiate code snippet with our graph code snippet and specify parameters like embedding dimension, walk length, and the number of walks per node. The code snippet and code snippet parameters control the bias of the random walks, influencing whether the walks prefer to explore locally, BFS-like, or globally, DFS-like. After configuring, we code snippet the model, which internally generates the random walks, and then trains a word 2-Vec skipgram model on these walks to produce the final node embeddings. Crucially, the embeddings are generated for the specific nodes present in the graph at the time of training. The transductive nature of node 2-Vec. The fundamental limitation of node 2-Vec and similar methods, like deep walk or line, lies in their transductive nature. Transductive learning refers to models that learn from and make predictions only on the specific data instances observed during training. They do not learn a generalizable function that can be applied to new, unseen data. What this means for N2V. Fixed graph. N2V learns an embedding for each specific node in the given graph. If a new node is added to the graph, or if existing connections change significantly, the entire node 2-Vec model must be retrained from scratch to generate embeddings for the new or altered graph structure. No generalization. It cannot generate embeddings for nodes that were not present in the training graph. There's no inherent rule or function learned that describes how an embedding should be formed based on a node's local neighborhood. It's more akin to memorizing an embedding for each specific node ID. Illustrative pitfall. Handling new data with N2V. Imagine you're building a recommendation system for a streaming platform using N2V, where nodes are users and movies. Code is not spoken. To get code, please see the link in description or bio. This code block highlights a critical limitation. If a new movie code snippet is added to the platform after the N2V model has been trained, attempting to retrieve its embedding will result in a code snippet. This is because N2V has no mechanism to infer an embedding for a node it has never seen during its random walk generation and word 2-Vec training phase. To get an embedding for code snippet, you would need to add code snippet and its connections to the graph. Then retrain the entire node 2-Vec model, which can be computationally expensive for large dynamic graphs. Graph neural networks, an inductive, feature-aware approach. In contrast to N2V, graph neural networks, GNNs, are inherently inductive models. Instead of learning a fixed embedding for each node, GNNs learn a function that maps a node's local neighborhood structure and its features, and its neighbor's features, to a low-dimensional embedding. This function is typically learned through a process called message passing or neighborhood aggregation. Core mechanism of GNNs. 1. Message passing. Each node iteratively aggregates information, messages, from its direct neighbors. These messages are transformed, e.g., via neural networks, and then combined with the node's own features. 2. Feature integration. A key differentiator is that GNNs naturally integrate node features into the embedding process. The initial input to a GNN layer for a node includes its feature vector. 3. Layered aggregation. This message passing process is typically stacked in multiple layers, allowing information to propagate across larger neighborhoods, i.e., a node's embedding can implicitly capture information from nodes several hops away. Conceptual GNN model structure. Code is not spoken. To get code, please see the link in description or bio. This conceptual GNN layer demonstrates the core principle. It takes code snippet and encode snippet, representing connectivity, as input. Inside the COD eSnippet method, it performs two key operations: aggregating information from neighbors via code snippet with the adjacency matrix, and transforming both the node's own features and the aggregated neighbor features. Finally, these are combined. The output is a new set of embeddings for each node. The crucial aspect here is that the code snippet learns weights, encode snippet and code snippet, that constitute a function for generating embeddings, rather than learning an embedding for each specific node ID. The inductive power of GNNs. The inductive nature of GNNs provides significant advantages, especially for dynamic graphs and real-world applications. Generalization to unseen nodes/graphs. Once a GNN model is trained, it has learned a generalizable function. This function can be applied to new nodes that were not part of the training set, or even entirely new graphs, as long as their nodes have compatible features and their structure can be represented by an adjacency matrix. The GNN can infer embeddings for these new entities by simply applying its learned aggregation and transformation rules to their local neighborhoods. Handling dynamic graphs. In scenarios where graphs evolve rapidly, e.g., new users joining a social network, new transactions in a financial network, GNNs can provide immediate embeddings for new entities without requiring full retraining. Leveraging node features. GNNs inherently incorporate node features into their embedding process. This allows them to capture rich semantic information about nodes in addition to their topological role, leading to more expressive and powerful representations. For instance, in a social network, GNNs can use user demographics, age, location, along with connections to learn better embeddings for tasks like friend recommendation. Illustrative advantage. Handling new data with GNNs. Revisiting the streaming platform example with a GNN. Code is not spoken. To get code, please see the link in description or bio. Here, without retraining the code snippet itself, we can obtain an embedding for the code snippet. We simply provide its features and its new connections, represented in the code snippet, to the already trained GNN. The GNN applies its learned aggregation and transformation rules to the new node's local neighborhood, effectively inferring its embedding. This demonstrates the superior adaptability and generalization capabilities of GNNs in dynamic environments, significantly reducing the computational cost and time associated with incorporating new data. Comparative summary: GNN versus N2V. The following table summarizes the key distinctions between GNN and N2V embeddings, highlighting why GNNs are often preferred for modern, complex graph applications. Feature node 2vec N2V, graph neural networks, GNNs. Learning paradigm, TR. Transductive inductive. Feature integration, no. Purely topology focused. Yes. Inherently integrates node features. Adaptability to new data, poor. Requires full retraining for new nodes/changes. Excellent. Generalizes to unseen nodes/graphs. primary focus capturing topological proximity and structural equivalence via random walks, learning a function to aggregate neighborhood information and node features. Retraining cost for new data high, full retraining often necessary. Low. Inference on new data, no retraining needed. Computational overhead, simpler models, potentially faster for static graphs, more complex models, higher training cost, but efficient inference. Typical use cases: static graphs, baseline models, tasks where only topology matters, e.g., community detection on unfeatured networks. Dynamic graphs, graphs with rich node attributes, tasks requiring generalization, e.g., real-time fraud detection, recommendation systems with new user/items, drug discovery. Choosing between N2V and GNNs depends heavily on the characteristics of your graph data and the requirements of your task. For static graphs with no relevant node features, or when simplicity is paramount, N2V can serve as an effective baseline. However, for evolving graphs, datasets with rich node attributes, or applications requiring generalization to unseen entities, GNNs offer a powerful and often superior solution. GNN versus N2V embeddings. Understanding the fundamental differences between graph neural network, GNN, embeddings, and node 2vec, N2V, embeddings is crucial for making informed decisions in graph-based machine learning tasks. While both aim to represent nodes in a low-dimensional vector space, their underlying mechanisms, assumptions, and suitability for various scenarios diverge significantly. The core distinction: inductive versus transductive learning. The most critical difference lies in their learning paradigms. N2V is inherently transductive, whereas GNNs are inductive. Transductive learning. Node 2vec's fixed scope. Transductive learning refers to models that learn from a fixed set of training data and can only make predictions on those specific data points or a very similar, predefined set. If new data points arrive, the model typically needs to be retrained or recomputed entirely. Node 2vec and similar random walk-based methods like deep walk or line fall into this category. They generate embeddings by exploring the local neighborhood of nodes through random walks. The resulting embeddings are tied directly to the specific graph structure observed during training. Consider a simple representation of how Node 2vec operates. Code is not spoken. To get code, please see the link in description or bio. The code above illustrates that code snippet is instantiated and code snippet on a code snippet. The embeddings generated code snippet are specific to the nodes that exist in the graph at the time of fitting. Now, imagine this graph evolves. A new node is added. Code is not spoken. To get code, please see the link in description or bio. As demonstrated, attempting to retrieve an embedding for a newly added node, code snippet, from the original code snippet fails. This is because code snippet derived its embeddings from random walks on the original fixed graph structure. To obtain an embedding for the new node, the entire code snippet process, including generating random walks and training the skipgram model, must be rerun on the updated graph. This makes N2V less suitable for dynamic or continuously evolving graphs. Inductive learning. GNNs, generalizable functions. Inductive learning models, in contrast, learn a mapping or a function from input features to output predictions or embeddings. This function can then be applied to unseen data points, as long as they conform to the input feature space. GNNs are inductive because they learn generalizable aggregation and update functions. Instead of learning a discrete embedding for each node, a GNN learns how to combine features from a node's neighborhood to produce its representation. This learned function can then be applied to any node, even those not present during training, as long as their local neighborhood structure and features are available. Consider a conceptual GNN layer. Code is not spoken. To get code, please see the link in description or bio. This GNN layer learns a transformation, code snippet, and an aggregation mechanism, code snippet. This code snippet method is a function that can be applied to any set of code snippet and encode snippet, as long as the dimensions match. When a new node appears, a GNN doesn't need to be fully retrained. Instead, its learned aggregation function can be applied to the new node's features and its connections to existing nodes. Code is not spoken. To get code, please see the link in description or bio. This demonstrates the inductive power of GNNs. The trained code snippet can process the features and connections of a new node, code snippet, to produce an embedding without needing to relearn the entire model from scratch. This makes GNNs highly suitable for dynamic graphs, such as constantly growing social networks or evolving knowledge graphs. Feature integration and task-specific optimization. Another key differentiator is how each method handles node features and their ability to optimize for specific downstream tasks. Node 2vec, topology-centric with post-hoc feature concatenation. Node 2vec primarily focuses on capturing structural equivalence and topological proximity. Its embeddings are derived solely from the graph's connectivity patterns, random walks. Node attributes, e.g., user demographics, item descriptions, are generally not directly incorporated into the embedding generation process itself. If node features are important for a downstream task, e.g., predicting a user's age, based on their network and profile information, they are typically concatenated with the node 2vec embeddings after the embeddings have been generated. Code is not spoken. To get code, please see the link in description or bio. This approach means node 2vec embeddings are agnostic to node features. They only reflect connectivity. While powerful for structural tasks, they might miss crucial information encoded in node attributes. GNNs, inherent feature integration and task-specific optimization. GNNs, by design, are built to integrate node features directly into the embedding generation process. The message passing mechanism aggregates features from a node's neighbors, effectively creating a rich, context-aware representation that combines both structural information and attribute data. Furthermore, GNNs are typically trained end-to-end for a specific downstream task, e.g., node classification, link prediction, graph classification. The embedding generation is an intrinsic part of this learning process, optimized to serve the ultimate objective. This allows GNNs to learn highly discriminative embeddings. Code is not spoken. To get code, please see the link in description or bio. In this GNN example, the code snippet are input directly into the code snippet. The model learns to transform and aggregate these features based on the code snippet to produce code snippet that are optimized for the classification task. This tight coupling of features, structure, and task object is a major advantage of GNNs. Adaptability to evolving graphs and unseen data. The inductive nature of GNNs makes them inherently more adaptable to changes in the graph structure or the introduction of new nodes. Node 2vec requires recomputation of embeddings for the entire graph if new nodes or significant structural changes occur. This can be computationally expensive and time-consuming for large, dynamic graphs. GNNs can generate embeddings for new nodes by simply applying the learned aggregation functions to the new node's features and its neighborhood. This is particularly useful in real-world scenarios. Continuously growing social networks. When a new user joins, a GNN can immediately generate an embedding for them based on their profile features and initial connections, enabling immediate recommendations or fraud detection. Evolving knowledge graphs. As new entities and relationships are added, GNNs can update embeddings incrementally without full retraining. Transfer learning across graphs. A GNN trained on one graph dataset, e.g., a specific type of protein interaction network, can potentially be applied to a structurally similar but entirely new graph dataset to generate embeddings or make predictions. Computational trade-offs. While GNNs offer significant advantages, it's important to consider computational aspects. Node 2vec. Pros. Generally simpler to implement and often faster for initial embedding generation on static graphs, especially when the graph is not extremely large. The random walk generation and word 2vec training can be parallelized. CPU-friendly. Cons. Re-embedding for dynamic graphs is expensive. Memory usage can become a concern for very large graphs. particularly if the random walks are long and the resulting corpus for word2vec is vast. GNNs. Pros. Highly parallelizable on GPUs, making training on large graphs feasible. Inference can be very fast once trained. Leverage modern deep learning frameworks. Cons. Training can be computationally intensive, especially for deep models, large graphs, or complex GNN architectures. Requires specialized hardware, GPUs, for efficiency on large datasets. Memory usage can be substantial for storing intermediate activations in deep networks. Strengths, weaknesses, and use cases, a comparative summary. Feature node 2vec, N2V, graph neural networks, GNNs. Learning paradigm, transductive inductive. Feature integration post hoc, concatenated after embedding, inherent, integrated during message passing. Adaptability low, requires recomputation for new nodes/changes. High, can generalize to unseen nodes/graphs. Computational costs simpler, often faster for static graphs. CPU-bound training can be intensive GPU-bound. Inference often fast. Primary focus capturing structural roles, and 2. Topological proximity learning rich, contextual representations for specific tasks. Embeddings derived from random walks/graph topology from node features plus neighborhood aggregation. Optimization unsupervised/self-supervised. Word2vec objective. Supervised/semi-supervised. Task-specific loss. Common use cases: exploratory data analysis, static graphs, baselines, dynamic graphs, rich node features, complex tasks, transfer learning. Limitations: cannot generalize to new nodes. Ignores node features in embedding over smoothing, scalability challenges for very deep models or extremely large graphs. Relies on homophily assumption. Practical applications and decision-making. The choice between N2V and GNNs hinges on the characteristics of your graph data and the specific requirements of your machine learning task. Scenarios favoring node 2vec. Static, well-defined graphs. If your graph structure rarely changes, e.g., a historical citation network, a fixed catalog of products that doesn't update frequently. Exploratory data analysis, EDA, when you need quick, topology-based embeddings to understand structural similarities or identify communities without a specific downstream task in mind. Baseline models. N2V can serve as a strong baseline to compare against more complex GNN models, especially when node features are not a primary concern. Limited computational resources. If you lack GPU access and your graph is not excessively large, N2V might be a more accessible choice. Example: if you're building a recommendation system for a fixed catalog of items that rarely changes, e.g., classic movies, a historical archive, N2V might be a straightforward and effective choice to capture item similarities based on user viewing patterns. Scenarios favoring GNNs. Dynamic or evolving graphs. Social networks. E-commerce platforms with constantly new products or constantly updated knowledge bases where new nodes and edges appear frequently. Rich node features. When node attributes, e.g., text descriptions, images, numerical data, user demographics, are rich and crucial for the task. GNNs inherently leverage these features. Task-specific optimization. When you have a clear downstream task, e.g., predicting fraudulent transactions, classifying protein functions, recommending specific items, and labeled data for training. Need for generalization. When you anticipate applying your learned model to unseen parts of the graph or entirely new, but structurally similar, graphs. Large-scale applications. While training can be intensive, GNN's ability to leverage GPUs and their inductive nature make them robust for very large and complex graph environments where scalability is key. Example: if your e-commerce platform is constantly growing with new items and user interactions, a GNN would be more robust. It can learn to embed a new product based on its features, description, images, and its initial interactions, early purchases, VI. WS, without needing to re-embed the entire product catalog. Similarly, for a fraud detection system on a financial transaction graph, a GNN can learn to identify suspicious patterns by integrating transaction amounts, user demographics, features, and network connections. Limitations of GNNs. While powerful, GNNs are not without their challenges. Oversmoothing. As GNNs go deeper, more layers, node embeddings can become increasingly similar, losing their discriminative power. This happens because information from distant neighbors propagates widely, eventually making all nodes look alike. Scalability for very deep models. While GNNs are generally scalable with GPUs, training very deep GNNs on extremely large graphs can still be memory-intensive and time-consuming, necessitating techniques like neighbor sampling, e.g., graph sage or subgraph training. Homophily assumption. Many standard GNN architectures, like GCNs, implicitly assume homophily, meaning connected nodes tend to be similar. In heterophilous graphs, where dissimilar nodes connect, e.g., predator-prey networks, these GNNs might perform poorly, requiring specialized architectures. Hybrid approaches. Instead of viewing N2V and GNNs as mutually exclusive, consider potential hybrid approaches. Node 2-vec embeddings, or embeddings from other unsupervised methods, can serve as valuable initial node features for a GNN. This can be particularly useful when node features are sparse or non-existent, and you want to inject structural information derived from random walks. You want to combine the strengths of both N2V for robust structural context and GNNs for leveraging additional features and task-specific optimization. Code is not spoken. To get code, please see the link in description or bio. This hybrid approach leverages the best of both worlds. N2V provides a strong, topology-focused initial representation, which the GNN then refines and optimizes for a specific task, integrating it with other node attributes and learning generalizable aggregation functions. Using node embeddings. Node embeddings, whether generated through neighborhood sampling, like Node 2-vec, or graph neural networks, like GNNs, serve as rich, low-dimensional representations of nodes within a graph. While their generation is a significant task, their true utility often lies in their application to downstream machine learning tasks, such as node classification, link prediction, or clustering. This section focuses on node classification, a common semi-supervised learning problem on graphs, where the goal is to predict the label of unlabeled nodes using a small set of labeled nodes and the graph structure. Semi-supervised node classification on graphs. Semi-supervised learning is particularly prevalent in graph data because obtaining labels for all nodes in a large network is often prohibitively expensive or impossible. In this setting, we typically have a graph structure, nodes and edges, features for each node, which can be the embeddings themselves or original node attributes, a small subset of nodes with known labels. The objective is to predict labels for the remaining unlabeled nodes. This setup leverages both the available labels and the underlying graph structure, assuming that connected nodes or nodes with similar neighborhood contexts are likely to have similar labels. Setting up the semi-supervised scenario, data splitting. To simulate a semi-supervised learning environment, we typically split our labeled data into training, validation, and TE/SD sets. The training set comprises the small percentage of nodes whose labels are used during model training. The validation set helps in hyperparameter tuning and early stopping, while the test set provides an unbiased evaluation of the final model's performance on unseen data. Crucially, the model sees the entire graph structure during training, even for unlabeled nodes, but only uses the labels from the training set for computing the loss. Let's illustrate how to create these masks for a dataset. We'll assume we have code snippet, e.g., code snippet or code snippet, and want to use a specific percentage of the labeled data for training and the rest for validation/testing. Code is not spoken. To get code, please see the link in description or bio. This initial code block sets up a synthetic dataset for demonstration. We define code snippet and code snippet, Then simulate code snippet where code snippet denotes an unlabeled node. In a real application, code snippet would be loaded directly from your dataset. Code is not spoken. To get code, please see the link in description or bio. Here, we first identify all nodes that actually have labels. Then, using code snippet from scikit-learn, we partition these labeled nodes into training, validation, and test sets. Stratified splitting code snippet is crucial to ensure that the class distribution in each split is similar to the overall distribution, preventing bias in evaluation. Code is not spoken. To get code, please see the link in description or bio. Finally, we convert the index arrays, code snippet, code snippet, code snippet, into Boolean masks. These masks are essential for filtering nodes during training, validation, and testing, ensuring that loss is only computed for the relevant nodes. And code snippet is also created, which will be used to identify nodes for which we want to make predictions after the model is trained. Classifying nodes with Node 2 vec embeddings and tabular models. Node 2 vec embeddings, being generated via random walks and skipgram, produce a fixed-size vector for each node that captures its local neighborhood structure. These embeddings are essentially node features that can be treated as independent data points in a tabular format. This makes them perfectly suitable for traditional machine learning classifiers that operate on tabular data, such as logistic regression, support vector machines, or, as we will use, random forest. Why random forest for Node 2 vec embeddings? Random forest is an ensemble learning method that constructs a multitude of decision trees during training and outputs the class that is the mode of the class's classification or mean prediction, regression of the individual trees. Its advantages include robustness, less prone to overfitting than a single decision tree. Feature importance, can provide insights into which dimensions of the embedding are most important. Nonlinearity, can capture complex nonlinear relationships within the embedding space. No graph structure needed. It operates purely on the node embeddings, treating them as independent feature vectors, without requiring the graph structure itself during classification. This is a key distinction from GNNs. Implementing random forest classifier. We will use scikit-learn's code snippet. We assume code snippet is a code snippet or code snippet where each row corresponds to a node's embedding. Code is not spoken. To get code, please see the link in description or bio. First, we prepare the data for the random forest classifier. This involves extracting the embeddings, code snippet, and corresponding labels, code snippet, for the nodes identified by our previously created code snippet, and code snippet. Scikit-learn models typically work with number py arrays, so we convert the PyTorch tensors. Code is not spoken. To get code, please see the link in description or bio. We instantiate code snippet with code snippet, number of decision trees, and code snippet for reproducibility. Code snippet is a good practice for multi-class classification where class distributions might be uneven. The code snippet method trains the model on the training data. Code is not spoken. To get code, please see the link in description or bio. After training, we evaluate the model's performance on the validation set to tune hyperparameters, though not explicitly shown here. This is where you'd iterate. Finally, the model is evaluated on the unseen test set using G-common classification metrics like code snippet and code snippet. F1 score is often preferred over accuracy, especially in multi-class or imbalance scenarios, as it's the harmonic mean of precision and recall. Code snippet accounts for class imbalance when computing the F1 score, making predictions with random forest. To predict labels for the initially unlabeled nodes, we simply pass their embeddings to the train code snippet. Code is not spoken. To get code, please see the link in description or bio. This final step demonstrates how to use the trained random forest model to infer labels for nodes that were initially unlabeled. The code snippet helps select only the relevant embeddings. Classifying nodes with GNN embeddings and GCN classifier. While GNNs can be used to generate embeddings, as discussed in previous sections, they can also be directly used as classifiers. When we refer to a GCN classifier, here we mean a graph convolutional network architecture designed for node classification, which inherently leverages the graph structure during the classification process. This is fundamentally different from a random forest, which treats embeddings as standalone features. Why a GCN classifier for GNN embeddings in the graph? A GCN classifier is particularly suited for tasks where the graph structure is critical for classification. Leveraging graph structure, unlike tabular classifiers, a GCN propagates information across the graph, allowing a node's classification to be influenced by its neighbors and their features/labels. This is crucial for tasks where the model needs to leverage relational information. End-to-end learning. When used as a classifier, the GCN can learn the optimal features for classification directly from the graph structure and initial node features, which could be raw node attributes or pre-trained GNN embeddings. Transductive versus inductive. Traditional GCNs are often transductive, meaning they learn embeddings for all nodes in the given graph during training, even unlabeled ones. However, more advanced GCN architectures can be made inductive. When using pre-generated GNN embeddings, the GCN classifier can build on these, or even refine them, by incorporating further graph-aware layers. Implementing a GCN-based classifier. For a GCN classifier, we typically define a neural network architecture that includes graph convolutional layers. We'll use PyTorch Geometric, PYG, for this, as it simplifies GNN implementation. We assume code snippet are available, or the GCN will learn directly from initial node features. For simplicity, we'll assume the GCN classifier takes the original node features and the graph adjacency matrix as input and outputs class probabilities. If we want to use pre-generated GNN embeddings as input, we'd pass them as code snippet. Let's define a simple two-layer GCN model for classification. Code is not spoken. To get code, please see the link in description or bio. This setup simula has a code snippet object, which is the standard way to handle graph data in PYG. It includes node features, code snippet, edge connectivity, code snippet, and the masks we created earlier. The code snippet is derived from the actual labels. Code is not spoken. To get code, please see the link in description or bio. Here, we define a simple two-layer GCN model. Code snippet is the core graph convolutional layer provided by PYG. The code snippet method defines the data flow. Code snippet dash code snippet activation dash code snippet for regularization dash code snippet. The output code snippet represents the raw logits for each class, which will be passed to a loss function like code snippet. Code is not spoken. To get code, please see the link in description or bio. We initialize the GCN model, an atom optimizer, and code snippet for the classification task. Code snippet is a form of L2 regularization to prevent overfitting by penalizing large weights. Training the GCN classifier, semi-supervised. The training loop for a GCN classifier in a semi-supervised setting is unique because the loss is only computed on the labeled nodes in the training set, even though the forward pass involves all nodes to leverage the graph structure. Code is not spoken. To get code, please see the link in description or bio. These helper functions encapsulate the training and evaluation logic. In code snippet, notice that code snippet and code snippet are used to calculate the loss, meaning ONL. Why the labeled training nodes contribute to gradient computation. Code snippet calculates accuracy on a given mask, validation, or test set. Code is not spoken. To get code, please see the link in description or bio. This is the main training loop. It iterates for a fixed number of code snippet. Inside the loop, code snippet is called to perform one optimization step, and code snippet is called to monitor performance on the validation set. We implement a simple model-saving logic to keep the best model based on validation accuracy, which helps prevent overfitting to the training data. Finally, the best model is loaded and evaluated on the test set, reporting accuracy, F1, score, precision, and recall. Making predictions with GCN classifier. Similar to the random forest, making predictions on unlabeled nodes with a GCN involves running a forward pass on the entire graph and then extracting the predictions for the nodes in the code snippet. Code is not spoken. To get code, please see the link in description or bio. This final code block demonstrates how to obtain predictions for the unlabeled nodes using the trained GCN model. The model is set to evaluation mode, code snippet, and gradients are disabled, code snippet, for efficient inference. Evaluation metrics for node classification. For classification tasks, particularly multi-class and semi-supervised ones, it's crucial to use appropriate metrics beyond simple accuracy. Accuracy, the proportion of correctly classified no-d. While intuitive, it can be misleading for imbalanced datasets where one class significantly outnumbers others. Precision, the proportion of true positive predictions among all positive predictions for a given class. High precision means fewer false positives, e.g., few non-fraudulent accounts flagged as fraud. Recall, sensitivity, the proportion of true positive predictions among all actual positive instances for a given class. High recall means fewer false negatives, e.g., catching most fraudulent accounts. F1, score, the harmonic mean of precision and recall. It provides a balanced measure, especially useful when there is an uneven class distribution. For multi-class, code snippet, as used in the examples, is common, which calculates metrics for each label and finds their average, weighted by the number of true instances for each label. Other options include code snippet, aggregates contributions of all classes to compute the average metric, and code snippet, calculates metric for each class, and then averages across classes, treating all classes equally. The choice of average depends on whether you want to treat all samples equally, code snippet, or all classes equally, code snippet. Hyperparameter tuning considerations. Both random forest and GCN classifiers have hyperparameters that significantly impact performance. Tuning these is an iterative process, often guided by performance on the validation set. Random forest. Code snippet, the number of trees in the forest. More trees generally improve performance but increase computation time. Code snippet, the maximum depth of the individual trees, controls model complexity and helps prevent overfitting. Code snippet, minimum number of samples required to split an internal node or to be at a leaf node, respectively. These control the granularity of the trees. Code snippet, important for imbalanced datasets, as it assigns different weights to different classes during training. GCN classifier. Code snippet, the number of neurons or features in the hidden layers, affects model capacity and ability to learn complex patterns. Code snippet for optimizer controls the step size during optimization. A too high rate can lead to instability, while a too low rate can slow down convergence. Code snippet, L2 regularization, a regularization term that penalizes large weights, helping to prevent overfitting. Code snippet, a regularization technique where a fraction of input units are randomly set to 0 at each update during training. This prevents complex co-adaptations on training data. Number of GCN layers. Deeper networks can capture more complex dependencies but are harder to train and prone to issues like oversmoothing, where node representations become indistinguishable. Hyperparameter tuning is typically done using techniques like grid search, exhaustive search over a defined parameter grid, random search, random sampling from parameter distributions, or more advanced methods like Bayesian optimization, often guided by performance on the validation set. Real-world applications of semi-supervised node classification. The techniques demonstrated in this section are widely applicable across various domains. Fraud detection. Identifying fraudulent accounts or transactions in financial networks, where only a small percentage of known fraud cases are available for training. Social network analysis. Classifying users into communities, predicting political leaning, or identifying influential users, given limited labeled profiles in social graphs. Bioinformatics. Predicting protein functions or classifying molecules in biological networks, where experimental labeling is costly and graph structures, e.g., molecular graphs, are inherent. Recommendation systems. classifying items or users based on their interactions and attributes to provide personalized recommendations, leveraging user-item interaction graphs. Knowledge graphs, completing missing information in large knowledge graphs by classifying entities, e.g., type of entity or relationships, where only a subset of facts is known. By understanding and applying these methods, you can leverage the power of graph structure and learned embeddings to solve complex prediction problems in network data. Data pre-processing for node classification. Before applying machine learning models to graph data, a crucial step is to prepare and pre-process the data. This involves transforming raw graph attributes and generated embeddings into a structured format suitable for model training and evaluation. In the context of node classification, this often means extracting node labels, converting them into a numerical format, and then intelligently splitting the dataset into labeled and unlabeled subsets, especially for semi-supervised learning scenarios where labeled data is scarce. Extracting and encoding node labels. Many real-world graph datasets, like the political books dataset, contain categorical labels as node attributes. Machine learning models, however, typically require numerical input. Therefore, the first step is to extract these categorical labels and map them to unique integer representations. The political books dataset, loaded as a NetworkX graph code snippet, stores political alignment as a node attribute. We can access this attribute for each node and create a mapping from string labels to integers. Code is not spoken. To get code, please see the link in description or bio. The initial setup imports necessary libraries and creates dummy graph and embedding data. In a real application, code snippet, and code snippet or a code snippet object will be the outputs from preceding sections, such as graph loading and embedding generation. Code is not Spock. To get code, please see the link in description or bio. This code block iterates through every node in the code snippet. The code snippet method is crucial here. It yields a tuple for each node, where the first element is the node identifier, e.g., an integer or string, and the second is a dictionary containing all its attributes. For the political books dataset, the relevant attribute is code snippet, which holds the categorical political alignment, code snippet, or code snippet. We then use a predefined code snippet dictionary to convert these string labels into numerical integers, code snippet, which are appended to a list. Finally, this list is converted into a number py array, code snippet, a standard format for machine learning inputs. Implementing the semi-supervised data split. Semi-supervised learning is particularly valuable in graph machine learning because obtaining fully labeled graph datasets is often challenging and expensive. For instance, in social networks, manually classifying every user's political leaning or every product category is impractical. Semi-supervised approaches allow models to learn from a small set of labeled data while also leveraging the vast amount of unlabeled data. To simulate this scenario, we perform a data split where only a small percentage of nodes, e.g., 20%, are designated as labeled for training, while the rest are unlabeled. Code is not spoken. To get code, please see the link in description or bio. Setting a code snippet is a best practice for any process involving randomness. It ensures that if you run the code multiple times with the same seed, the random operations, like sampling nodes for the labeled set, will produce identical results. This is vital for debugging, sharing code, and ensuring experiments are reproducible. We set seeds for both Python's code snippet module and NumPy's code snippet module to cover all potential random operations. Code is not spoken. To get code, please see the link in description or bio. Here, we calculate the number of nodes that will form our labeled set based on the code snippet. The code snippet function is then used to select code snippet unique indices from code snippet. These code snippet represent the nodes for which we know the ground truth label and will use for model training. Code is not spoken. To get code, please see the link in description or bio. Boolean masks are highly efficient for selecting subsets of data in number py. We initialize two Boolean arrays, code snippet and code snippet, with code snippet for all elements. Then, for every index present in code snippet, we set the corresponding position in code snippet to code snippet. The code snippet is simply the logical inverse code snippet of the code snippet, indicating nodes for which we do not have labels or will not use for supervised training. These masks are fundamental for preparing our training data. They allow us to easily select the features, embeddings, and labels for the nodes that are part of our labeled training set. Code snippet, code snippet. The code snippet is equally important for later stages, such as evaluating the model's performance on unseen data, or for specific semi-supervised learning techniques that leverage unlabeled data during training. Preparing embeddings for training. With labels extracted and the data split defined, the next step is to prepare the feature vectors, node embeddings, for the machine learning model. This involves aligning the embeddings with their corresponding labels based on the code snippet. A critical distinction arises here between Node 2vec and GNN embeddings due to their generation processes. GNN embeddings, order preservation. Graph neural networks, GNNs, typically process the entire graph structure in a single pass. The resulting node embeddings, e.g., from a code snippet or code snippet layer, are usually outputted in an order that directly corresponds to the input node order of the graph. This means if node code snippet was the first node processed by the GNN, its embedding will be the first row in the code snippet tensor. Code is not spoken. To get code, please see the link in description or bio. For GNN embeddings, preparing the training data is straightforward. Since code snippet, a PyTorch tensor, is assumed to be in the same order as the code snippet array, we can directly apply the code snippet to both. This operation efficiently selects ONL, while the embeddings and labels corresponding to the nodes designated for the label training set. The labels are also converted to a PyTorch tensor with code snippet type, which is standard for classification targets in PyTorch. Node 2vec embeddings, explicit alignment. Node 2vec, on the other hand, generates embeddings for each node based on independent random walks. While the code snippet library's code snippet model, which Node 2vec typically uses, stores these embeddings, it does so in a way that doesn't inherently preserve the original graph's node order. The embeddings are often stored in a dictionary-like structure where node IDs, often converted to strings, are keys. Therefore, to align Node 2vec embeddings with our code snippet array, we must explicitly fetch each node's embedding in the original graph's node order. Code is not spoken. To get code, please see the link in description or bio. This segment addresses the crucial alignment step for Node 2vec embeddings. We iterate through the code snippet in their original order. For each code snippet, we convert it to a string code snippet, because Node 2vec's code snippet model typically uses string representations of node IDs as keys in its internal vocabulary, e.g., code snippet, code snippet, code snippet. We then retrieve the corresponding embedding vector from our code snippet dictionary and append it to code snippet. This ensures that the list of embeddings is now in the same order as our code snippet and the GNN EMB. Headings. Finally, this list is converted to a number py array code snippet. Code is not spoken. To get code, please see the link in description or bio. After ensuring the Node 2vec embeddings are correctly ordered, we can apply the code snippet to obtain code snippet, the Node 2vec features for the labeled training set. The code snippet labels are identical to code snippet as they come from the same code snippet array, masked by code snippet. Practical considerations. The unlabeled mask and future use. The code snippet created during the data splitting phase is not immediately used for supervised training, but is vital for subsequent steps. It can be used to create a test set. If you want to evaluate your model on unseen, unlabeled data, e.g., code snippet, semi-supervised techniques. Some semi-supervised learning algorithms, e.g., label propagation, self-training, explicitly leverage the unlabeled data during training to improve performance. The code snippet would be used to select these samples. Code is not spoken. To get code, please see the link in description or bio. This snippet demonstrates how the code snippet can be used to prepare a test set. This test set would then be used after model training to evaluate the model's generalization capabilities on data it has not seen during the supervised training phase. Implications of fixed data splits. The 20% fixed labeled data split is a common practice for demonstration, but in real-world SCE scenarios, the choice of split percentage and method can significantly impact model performance and evaluation. Representativeness. Ensure the labeled subset is representative of the entire dataset's class distribution. If one class, e.g. neutral in the political books dataset, is much smaller, a purely random sample might result in very few or zero samples of that class in the labeled set, leading to class imbalance issues during training. Stratified sampling. For imbalanced datasets, stratified sampling is often preferred. This ensures that the proportion of each class in the labeled and unlabeled split roughly matches its proportion in the original dataset. While Code Snippet doesn't directly support stratification, you could manually sample from each class. Graph-specific splits. For graph data, splits can also be performed in a more sophisticated manner, such as edge-wise splits, training on certain edges, testing on others, or subgraph splits, training on one part of the graph, testing on a disconnected part. However, for node classification, node-wise splits are typical. Handling class imbalance. If, after the split, certain classes like neutral in our example have very few samples in the labeled training set, it can lead to a biased model that performs poorly on underrepresented classes. Strategies to mitigate this include weighted loss functions. Assign higher weights to samples from underrepresented classes during model training. Oversampling/undersamp. Ling. Techniques like SMOTE, synthetic minority oversampling technique, can generate synthetic samples for minority classes. Data augmentation. For graph data, this might involve perturbing graph structure or node features to create more training examples. By carefully considering these pre-processing steps and their implications, you can build a robust foundation for training effective graph machine learning models, especially in resource-constrained semi-supervised settings. Random forest classification. This section marks a pivotal point in our exploration, with a theoretical understanding of graph embeddings culminates in a practical application, semi-supervised node classification. We will leverage the node 2vec, N2V, and graph neural network, GNN, embeddings generated in previous sections as input features for a traditional machine learning model, the random forest classifier. This allows us to directly compare the efficacy of different embedding approaches for a downstream task. Why random forest for node classification? Random forest is an ensemble learning method that constructs a multitude of decision trees during training and outputs the class that is the mode of the classes, classification, or mean prediction, regression, of the individual trees. Its popularity stems from several key advantages that make it well suited for this task. Robustness. It is less prone to overfitting compared to single decision trees, thanks to the averaging effect of multiple trees. Nonlinear relationships. Random forest can effectively capture complex, nonlinear relationships within the data, which is crucial as graph embeddings often represent intricate structural and semantic patterns. Feature importance. It can provide insights into which features, embedding dimensions, are most important for classification, though this is less critical when all dimensions of an embedding are equally relevant. Handles tabular data. Critically, graph embeddings. Transform complex graph structures into fixed-size numerical vectors, essentially converting graph data into a tabular format that traditional machine learning models like random forest can readily process. Strong baseline. Random forest often serves as a robust and high-performing baseline for many classification tasks, providing a solid point of comparison for more complex deep learning models. In our semi-supervised setting, we will use the embeddings of the labeled nodes as training features and their corresponding political leanings, left, right, neutral, as target labels. The goal is to train a model that can then accurately predict the political leaning of unlabeled nodes based on their embeddings. Setting up and training the classifiers. Before we begin, ensure you have the necessary libraries imported. Code snippet is the primary library for machine learning in Python, providing the code snippet and various evaluation metrics. Code is not spoken. To get code, please see the link in description or bio. These import statements bring in the core components we'll need. Code snippet for creating our model instances, and code snippet, and code snippet for assessing how well our models perform. Now, we will instantiate and train two separate random forest classifiers, one for the GNN embeddings and another for the N2V embeddings. This allows for a direct, unbiased comparison of their performance. We assume that code snippet, PET, and code snippet have been prepared from the previous data pre-processing steps, where code snippet represents the embeddings, features, and code snippet represents the corresponding numeric labels, 0, 1, 2, 4 left, neutral, right respectively. The code snippet parameter ensures reproducibility of the results. Code is not spoken. To get code, please see the link in description or bio. This first block initializes a code snippet named code snippet. The code snippet ensures that if you run this code multiple times, the internal randomness, e.g., how decision trees are built, will be consistent, leading to identical results. The code snippet method then trains the model using the GNN embeddings, code snippet, as input features and their corresponding labels, code snippet. Next, we repeat the process for the node 2vec embeddings. Code is not spoken. To get code, please see the link in description or bio. Similar to the GNN model, code snippet is initialized and trained. It's crucial to understand that these are two independent models, each trained on different sets of embeddings, allowing us to directly compare the quality of the embeddings themselves for this classification task. Making predictions. Once the models are trained, their primary purpose is to make predictions on unseen data. In our semi-supervised context, this unseen data typically refers to the nodes that were initially unlabeled but for which we have generated embeddings. We use code snippet and code snippet, which represent the embeddings of these unlabeled nodes, and code snippet, which are their true labels, if available for evaluation purposes. Otherwise, it would be code snippet embeddings. Code is not spoken. To get code, please see the link in description or bio. The code snippet method takes the test features, code snippet, and outputs an array of predicted class labels, code snippet. These predictions will be integers, 0, 1, or 2, corresponding to the political leanings. Code is not spoken. To get code, please see the link in description or bio. Similarly, code snippet stores the predictions generated by the random forest model trained on node 2vec embeddings. Evaluating model performance. After making predictions, the next critical step is to evaluate how well our models performed. For classification tasks, several metrics are commonly used. Here, we will focus on accuracy and F1 score. Understanding classification metrics. Accuracy. This is the most straightforward metric, representing the proportion of correctly predicted instances out of the total instances. $text accuracy equals \frac text the number of correct predictions \text total number of predictions Pros: easy to understand and interpret. Cons: can be misleading in the presence of class imbalance. For example, if 90% of your data belongs to one class, a model that always predicts that class will have 90% accuracy, but it's not a useful model. F1 score. The F1 score is the harmonic mean of precision and recall. Precision: the proportion of positive identifications that were actually correct. It answers, of all items predicted as positive, how many are truly positive? Recall: sensitivity, the proportion of actual positives that were identified correctly. It answers, of all true positive items, how many do we correctly identify? $text F1 score equals 2 times \frac text precision times text recall text precision plus text recall. Pros: provides a better measure of a model's performance than accuracy, especially when dealing with imbalanced datasets. It balances the trade-off between precision and recall. A high F1 score means low false positives and low false negatives. Cons can be less intuitive to understand than accuracy. In a multi-class classification problem like ours, 3 political leanings, the F1 score is often calculated as a weighted average code snippet. This means the F1 score for each class is calculated independently and then averaged, weighted by the number of true instances for each label. This accounts for class imbalance. Recall that our numeric labels map to code snippet left, code snippet neutral, code snippet right. Let's calculate and print these metrics for both models. Code is not spoken. To get code, please see the link in description or bio. Here, we use code snippet and code snippet from code snippet. For code snippet is crucial for multi-class problems with potential class imbalance. Code is not spoken. To get code, please see the link in description or bio. This provides the summary metrics for the Node 2 VEC model, allowing for a direct comparison with the GNN model's performance. For a more detailed breakdown of performance per class, precision, recall, F1 score for each of left, neutral, right, we can use code snippet. Code is not spoken. To get code, please see the link in description or bio. The code snippet provides a comprehensive summary, including precision, recall, and F1 score for each class, along with support, the number of true instances for each class in the test set. This is invaluable for understanding how well the model performs on individual categories. Code is not spoken. To get code, please see the link in description or bio. By examining both classification reports, you can gain deeper insights into which classes are well predicted and which might be more challenging for each embedding type. Comparing N2V and GNN embeddings for classification. Upon reviewing the accuracy and F1 scores, you might observe nuanced differences between the models trained on N2V and GNN embeddings. For instance, N2V might yield slightly higher accuracy, while GNN might achieve a marginally better F1 score, or vice versa. Why these differences? The performance difference stems from how each embedding technique captures graph information. Node 2 VEC and 2V focuses on learning embeddings that preserve neighborhoods true. Tour, typically defined by random walks. This makes it excellent at capturing local proximity and community structure. If the political leaning is strongly correlated with immediate neighbors and short-range connections, N2V might perform very well. Graph neural networks, GNNs, learn embeddings by iteratively aggregating information from a node's neighbors. This process can capture more complex, multi-hop structural patterns and can integrate node features, if available. GNNs are inherently inductive, meaning they can generalize to unseen nodes, which is a significant advantage for dynamic graphs. If the political leaning depends on broader structural roles or aggregated information from distant neighbors, GNNs could have an edge, particularly in capturing more abstract or nuanced relationships. Accuracy versus F1 score trade-off. If you observe a scenario where one model has higher accuracy but lower F1 score, it often points to class imbalance. If, for example, the neutral class is very small, a model might achieve high overall accuracy by correctly classifying the majority left and right classes, but perform poorly on the neutral class, leading to a lower F1 score, which is more sensitive to performance on minority classes. In such cases, the F1 score is generally a more reliable indicator of overall model quality. The empirical results from this classification task provide a tangible way to compare the utility of different graph embedding approaches for SPE. Specific application, advanced considerations, and best practices. While a simple train/test split is demonstrated here, for more robust model evaluation, especially on smaller datasets, K-fold cross-validation is highly recommended. Cross-validation involves splitting the dataset into K-folds, training the model K times, each time using a different fold as the test set and the remaining K1 folds as the training set, and then averaging the performance metrics. This provides a more reliable estimate of the model's generalization performance. Additionally, hyperparameter tuning can significantly impact a random forest model's performance. Key hyperparameters include code snippet, the number of trees in the forest, code snippet, the maximum depth of each tree, and code snippet, the minimum number of samples required to be at a leaf node. Techniques like code snippet or code snippet from code snippet can systematically search for the optimal combination of these parameters. Practical applications. The ability to classify nodes based on their embeddings has numerous real-world applications. Content moderation. Automatically categorizing online content, e.g., social media posts, articles, based on predicted leaning or sentiment derived from a network of interactions. Recommendation systems. Recommending books or products with similar predicted political leanings to users, enhancing personalized experiences. For example, if a user frequently buys left-leaning books, the system could recommend others predicted to be in that category. Fraud detection. Identifying anomalous or suspicious entities, nodes, in a transaction network by classifying them into fraudulent or legitimate categories. Disease spreading prediction. Classifying individuals in a contact network as infected or susceptible based on their network interactions. Customer segmentation. Grouping customers based on their purchasing behavior in a co-purchase graph. To illustrate how you might use a trained model to predict the class of a single new book represented by its embedding, consider the following. Code is not spoken. To get code, please see the link in description or bio. This example demonstrates the final step of deployment, taking a new embedding, representing a new node, and feeding it into the trained classifier to obtain a prediction. This capability forms the backbone of many real-world semi-supervised graph applications. Embeddings in an end-to-end model. Previous sections explored static graph embeddings, such as those generated by Node2Vec, and demonstrated their utility as features for traditional machine learning models like random forest. This approach involves a two-stage process. First, generating embeddings, and then using these fixed embeddings for a downstream task. While effective, this method does not allow the embeddings to adapt specifically to the nuances of the prediction task. This section introduces a fundamental paradigm shift, end-to-end learning with graph neural networks, GNNs. In this approach, graph embeddings are not pre-computed, but are dynamically learned and continuously refined as an integral part of the overall model training process. This allows the GNN to optimize the node representations specifically for the target task, leading to potentially more accurate and contextually relevant predictions. The power of end-to-end learning. In an end-to-end GNN, the embedding generation mechanism, the GNN layers, and the prediction head, e.g., a linear layer for classification, are trained simultaneously. This joint optimization offers several key advantages. Task-specific optimization. The embeddings are no longer generic. They are learned in a way that minimizes the error for the specific classification or regression task at hand. This means the GNN learns features that are most discriminative for the labels. Adaptability. As the model trains, the embeddings evolve. If the underlying data distribution shifts or the task requirements change slightly, the GNN can adapt its embedding generation process to reflect these changes. Simplified pipeline. The need for a separate, often computationally expensive, embedding generation step is eliminated. The entire process, from raw graph data to final prediction, is handled within a single, unified framework. Potential for higher performance. By optimizing embeddings directly for the task, end-to-end GNNs often achieve superior performance compared to methods relying on static, pre-computed embeddings, especially for complex graph prediction tasks. While end-to-end learning offers significant benefits, it also demands a deeper understanding of deep learning training workflows, including loss functions, optimizers, and monitoring performance. Modifying the GNN architecture for classification. To enable an end-to-end classification task, our GNN model needs to be extended. Previously, a GNN might have simply outputted embeddings. Now, it must output both the embeddings for analysis and a predictive output suitable for classification. For multi-class classification, this typically involves a final linear layer followed by an activation function like code snippet. Let's modify a code snippet class to include this classification head and provide dual outputs. We'll assume a basic GNN structure using code snippet layers from message passing. First, we need to import the necessary PyTorch and py. Torch geometric modules. Code is not spoken. To get code, please see the link in description or bio. These imports provide the foundational tools for building GNNs, code snippet, handling graph data, code snippet, and performing visualization, code snippet. Next, we define our code snippet class. Notice how the code snippet method now produces two outputs, the intermediate node embeddings and the final classification logits. Code is not spoken. To get code, please see the link in description or bio. In this code snippet class, the code snippet method defines two code snippet layers and a final code snippet layer, which serves as the classification head. Code snippet is the dimensionality of input node features. Code snippet is the size of the hidden layers. Code snippet is the dimensionality of the final node embeddings, and code snippet is the number of possible output categories for classification. The code snippet method applies the graph convolutional layers sequentially. After the first layer, code snippet introduces nonlinearity, and code snippet helps prevent overfitting by randomly setting a fraction of input units to 0 during training. The output of the second code snippet layer, code snippet, represents the learned node representations. These are the dynamic embeddings we are interested in. These code snippet are then passed through the code snippet linear layer. The output of this linear layer is then passed through code snippet. Code snippet is preferred over code snippet when paired with code snippet, negative log likelihood loss, because it improves numerical stability, especially for large models or probabilities very close to 0. Crucially, the code snippet method now returns two tensors, code snippet and code snippet. This allows us to both train the model for classification and extract the intermediate embeddings for analysis. Setting up the end-to-end training process. Training an end-to-end GNN involves the standard deep learning workflow, preparing data, instantiating the model, defining a loss function, choosing an optimizer, and running an iterative training loop. For demonstration, let's create a synthetic dataset using code snippet. In a real scenario, this code snippet object would come from your pre-processed graph data. Code is not spoken. To get code, please see the link in description or bio. This code creates a code snippet object with random features, edges, and labels, along with code snippet and code snippet to split the data for training and evaluation. Next, we instantiate our model, define the loss function, and set up the optimizer. Code is not spoken. To get code, please see the link in description or bio. Here, we initialize code snippet with appropriate dimensions. Code snippet is chosen because our model's final layer uses code snippet, making them compatible for multi-class classification. The code snippet optimizer is a popular choice for its efficiency and good performance across various deep learning tasks. Implementing the training and evaluation loop. The training loop iteratively updates the model's parameters to minimize the loss. The evaluation loop assesses the model's performance on unseen data. We'll define separate code snippet and code snippet functions for clarity. Code is not spoken. To get code, please see the link in description or bio. Key aspects of these functions. Code snippet and code snippet. These modes are crucial. Code snippet enables features like dropout, if used, and batch normalization updates. Code snippet disables these, ensuring consistent behavior during inference. Code snippet clears old gradients. PyTorch accumulates gradients by default, so this is necessary at the start of each training step. Code snippet computes gradients of a loss with respect to all trainable parameters. Code snippet updates the model's parameters using the computed gradients. Code snippet essential for evaluation. It disables gradient computation, which saves memory and speeds up calculations, as we don't need to update parameters during testing. Accuracy calculation. The code snippet function calculates the accuracy by comparing the predicted class, the class with the highest log probability, with the true labels for the test set. Now, let's run the main training loop. Code is not spoken. To get code, please see the link in description or bio. This loop runs for specify d number of code snippet, calling the code snippet and code snippet functions. It prints the loss and test accuracy periodically, allowing you to monitor the training progress. We also capture the code snippet before training and code snippet after training, which are crucial for our next step, studying embedding evolution. Studying embedding evolution and performance. A key advantage of end-to-end GNNs is that the embeddings are optimized for the task. We can observe this optimization by visualizing the embedding space before and after training. If the model is learning effectively, we should see nodes belonging to the same class clustering together more distinctly in the post-training embedding space. We'll use UMAP, Uniform Manifold Approximation and Projection, for dimensionality reduction, as it's excellent for visualizing high-dimensional data while preserving local and global structures. First, define a helper function for UMAP visualization. Code is not spoken. To get code, please see the link in description or bio. This code snippet function takes the high-dimensional embeddings and their corresponding labels, applies UMAP to reduce them to 2 dimensions, and then creates a scatter plot. The code snippet argument colors the points based on their class labels, making it easy to visually inspect clustering. Now, let's visualize the embeddings. Code is not spoken. To get code, please see the link in description or bio. By comparing the 2 UMAP plots, you show LD observe. Initial embeddings. Nodes from different classes will likely be highly intermingled, as the initial embeddings are essentially random or based on simple graph structures without task-specific optimization. Final embeddings. After training, you should see distinct clusters forming for each class. This visual separation indicates that the GNN has learned discriminative features, embeddings, that effectively separate the classes, demonstrating the power of end-to-end learning. The better the clusters are separated, the more effective the GNN is at its classification task, saving and loading the model. For practical applications, it's essential to save your trained model and load it later for inference or further training. PyTorch provides straightforward ways to do this. Code is not spoken. To get code, please see the link in description or bio. Code snippet saves only the learned parameters, weights, and biases of the model, making the file size smaller. To load it, you must first instantiate an empty model with the exact same architecture, and then code snippet will populate it with the saved parameters. Real-world applications of end-to-end GNNs. The principles demonstrated in this section extend to a vast array of real-world applications where graph structure data is prevalent and task-specific embeddings are beneficial. Recommendation systems. Predicting user preferences for items by modeling user-item interaction graphs. GNNs can learn embeddings for us. Errors and items simultaneously, leading to personalized recommendations. Drug discovery. Predicting properties of molecules, graphs of atoms and bonds. End-to-end GNNs can learn molecular representations optimized for tasks like predicting drug-target interactions or toxicity. Fraud detection. Identifying fraudulent transactions or accounts in financial networks. GNNs can learn embeddings that highlight anomalous patterns in transaction graphs, leading to better fraud detection. Social network analysis. Predicting political leaning, interests, or influence of individuals in social networks. The GNN learns node embeddings that capture social connections and attributes relevant to the prediction task. Knowledge graphs. Answering complex queries by reasoning over large knowledge graphs. GNNs can learn embeddings for entities and relations that facilitate inferencing. In all these scenarios, the ability of end-to-end GNNs to dynamically learn task-optimized representations from graph structure and node features makes them a powerful tool for complex prediction problems. Embeddings in an end-to-end model. This section marks a pivotal shift in our approach to utilizing graph embeddings. Previously, we explored generating static graph embeddings, like Node2Vec, and then using these pre-computed embeddings as features for traditional machine learning models, such as a random forest classifier. While effective for demonstrating the utility of embeddings, This approach separates the embedding generation from the downstream task. Here, we transition to an end-to-end learning paradigm with graph neural networks, GNNs. In an end-to-end GNN model, the process of learning meaningful node representations, embeddings, and performing the specific task, e.g., node classification, are integrated into a single, unified neural network architecture. The GNN dynamically learns and refines these embeddings during its training process, optimizing them directly for the prediction task. This contrasts with static embeddings, where the embeddings are fixed before the classification model sees them. This integrated approach often leads to superior performance because the GNN can learn task-specific features, adapting its representation learning based on the labels available and the model's objective function. It allows the model to learn features that are most discriminative for the given task, rather than relying on generic topological features. Preparing graph data for PyTorch geometric. To feed our graph data into a PyTorch geometric PYG GNN model, we must see: convert our graph representation into PYG's native code snippet object format. This code snippet object is a fundamental structure in PYG designed to hold all necessary graph components: node features, code snippet; edge indices, code snippet; and optionally, node labels, code snippet, among other attributes. We will continue using the code snippet graph, which represents co-purchasing patterns of political books. Assuming code snippet is a NetworkX graph object, the conversion to a PyTorch geometric code snippet object is straightforward using the code snippet utility function. Code is not spoken. To get code, please see the link in description or bio. The code snippet function automatically extracts the graph topology, nodes and edges, and stores it in code snippet and code snippet, respectively. However, it does not automatically create initial node features, code snippet. This is a crucial step that we must handle explicitly, as node features are the primary input for GNNs to learn from. Node feature initialization strategies. The initial features assigned to code snippet are critical because they provide the starting point for the GNN's learning process. The GNN's message passing mechanism aggregates and transforms these features to create more sophisticated representations. We will explore two common strategies for initializing node features: random initialization and using pre-computed node 2vec embeddings. Strategy 1. Random initialization with Xavier uniform. When no meaningful inherent node features are available, e.g., for a simple graph where nodes only have identifiers, or when we want the GNN to learn all representations from scratch purely based on graph topology, random initialization is a viable strategy. A common pitfall with simple random initialization, e.g., with code snippet, is that it can lead to issues like vanishing or exploding gradients during training, especially in deep neural networks. To mitigate this, we often employ more sophisticated initialization schemes like Xavier, Glorot, uniform initialization. Xavier initialization aims to keep the variance of activations consistent across layers. This helps in maintaining a healthy flow of gradients through the network, allowing for more stable and efficient training. It samples weights from a uniform distribution within a specific range, scaled by the input and output dimensions of the layer. For initializing node features, which can be thought of as the input to the first layer of the GNN, applying Xavier initialization ensures that the initial feature values are appropriately scaled. Code is not spoken. To get code, please see the link in description or bio. In this code snippet creates a tensor where each node has a code snippet size vector of random numbers. Then, code snippet modifies these values in place according to the Xavier uniform distribution. This ensures that the initial feature vectors are balanced, providing a better starting point F, or the GNN to learn from. Strategy 2. Using pre-computed node 2vec embeddings. If we have already computed meaningful topological embeddings using methods like node 2vec, as covered in previous sections, we can leverage these as the initial node features for our GNN. This approach allows the GNN to build upon existing insights about the graph structure, potentially accelerating convergence or improving performance. especially if the Node 2-vec embeddings are highly informative for the downstream task. Recall that Node 2-vec embeddings capture local and global neighborhood information. By using them as initial features, we are essentially giving the GNN a head start with rich, pre-learned representations of each node's context within the graph. Assuming code snippet is a number py array containing the Node 2-vec embeddings for all nodes, where each row corresponds to a node and each column is an embedding dimension. Code is not spoken. To get code, please see the link in description or bio. Here, we convert the number py array code snippet into a code snippet and directly assign it to code snippet. The GNN will then take these pre-computed embeddings as its input features and further refine them through its message passing and aggregation layers. Comparing initialization strategies and their trade-offs. The choice between random initialization with proper scaling like Xavier and using pre-computed embeddings as initial features depends on several factors. Availability of feature. If a graph inherently lacks descriptive node attributes, e.g., a simple social network graph where nodes are just IDs, random initialization is often the only practical choice for code snippet. Computational cost. Generating good quality pre-computed embeddings, like Node 2-vec, can be computationally intensive, especially for very large graphs. Random initialization is computationally cheaper. Learning capacity of the GNN. Random initialization forces the GNN to learn representations from scratch, primarily leveraging the graph's topology and the semi-supervised labels. This can be powerful if the GNN architecture is deep and expressive enough to capture complex patterns. It's suitable when the GNN is expected to implicitly learn what features are relevant from the graph structure itself. Pre-computed embeddings provides the GNN with a strong prior, accelerating learning and potentially leading to better performance, especially if the pre-computed embeddings are highly informative. This strategy is beneficial when you want to explicitly leverage existing knowledge about the graph structure or when the GNN might struggle to learn rich representations solely from topology. Task specificity. Node 2-vec embeddings are general purpose and capture structural similarity. If the downstream task, e.g., node classification, aligns well with this structural similarity, using Node 2-vec as initial features can be very effective. An end-to-end GNN, starting with random features might learn features that are more specifically tailored to the classification task at hand, potentially discovering more discriminative features than general-purpose embeddings. In practice, it's often a good idea to experiment with both strategies to see which performs better for your specific dataset and task. For the political books dataset, using Node 2-vec embeddings as initial features is a sensible choice, as they provide a rich, topologically aware starting point for the GNN. The role of node features in GNNs. Regardless of how code snippet is initialized, these node features are fundamental to how a GNN operates. In a GNN, the core mechanism is message passing, where information is exchanged between neighboring nodes. Each node's feature vector is updated by aggregating information from its neighbor's feature vectors. For instance, in a graph convolutional network, GCN, layer, a node's new representation is typically a function of its own previous features and the aggregated features of its neighbors. If code snippet is initialized randomly, the GNN will learn to extract meaningful patterns from these random starting points, guided by the graph's connectivity and the training labels. If code snippet is initialized with Node 2-vec embeddings, the GNN starts with rich, structural information and then refines it further through the message passing process to optimize for the specific prediction task. In a semi-supervised learning setting, where only a subset of nodes VE labels code snippet, the GNN learns to propagate label information and feature representations across the graph, even to unlabeled nodes. The initial code snippet provides the base information that gets transformed and propagated throughout the network, ultimately influencing the predictions made for all nodes. Embeddings in an end-to-end model. Traditional machine learning workflows often involve distinct stages: feature extraction, then model training. In graph machine learning, This might mean pre-computing graph embeddings, e.g., using Node 2vec or deepwalk, and then feeding these static embeddings into a separate classifier like a random forest. While effective for certain tasks, this approach has limitations. It assumes the pre-computed embeddings are optimal for the downstream task, and it separates the embedding generation from the prediction process, potentially losing task-specific signal. The shift to end-to-end learning. End-to-end learning in graph neural networks, GNNs, represents a powerful paradigm shift. Instead of generating embeddings as a separate, fixed step, the GNN itself learns to produce task-specific embeddings as part of the training process for the ultimate prediction task. This means the GNN's layers are optimized not just to create good general-purpose embeddings, but specifically to create embeddings that are most effective for, say, node classification or link prediction. Why end-to-end? Task specificity. Embeddings are dynamically tailored to the specific prediction goal. For example, embeddings optimized for classifying political leaning might be different from those optimized for predicting academic citations. Simplified pipeline. The entire process, from raw graph features to final predictions, is handled by a single, unified neural network MO. DEL, reducing complexity and potential for error in multi-stage pipelines. Joint optimization. The embedding generation and the prediction head are optimized simultaneously through backpropagation, allowing for more effective learning and often leading to superior performance. Efficiency. For very large graphs, pre-computing and storing embeddings can be memory-intensive and time-consuming. End-to-end models compute embeddings on the fly, as needed. Introducing code snippet, a unified architecture. To demonstrate this end-to-end approach, we will modify a basic GNN architecture, similar to the code snippet introduced previously. This new class, code snippet, will not only process graph data to generate node embeddings, but will also integrate a classification head to produce predictions directly. Crucially, its code snippet method will be configured to return both the final node embeddings and the classification probabilities, allowing for flexible use in various downstream tasks like visualization or direct classification. This modified GNN will learn refined node representations that are directly optimized for the classification task at hand. Dissecting the code snippet class. The code snippet class, inheriting from code snippet, encapsulates the entire neural network logic. It consists of an initialization method, code snippet, where the layers are defined, and a forward pass method, code snippet, that dictates the computational flow. Code snippet, setting up the lay. RS. The constructor code snippet is responsible for defining the building blocks of our GNN. In this model, we utilize two code snippet layers, which are fundamental for message passing in graph neural networks. Code is not spoken. To get code, please see the link in description or bio. In this code snippet method, code snippet ensures that code snippet's constructor is called, setting up the basic functionalities required for a PyTorch neural network. Code snippet is our first code snippet layer. It takes the original input features, code snippet, of each node and transforms them into a code snippet dimensional space. This layer learns to aggregate information from immediate neighbors. Code snippet is the second code snippet layer. It takes the output from code snippet, which is already in code snippet dimension, and further transforms it into code snippet dimensions. The output of this layer can be directly interpreted as the refined node embeddings, specifically tailored for the classification task, where code snippet represents the number of possible categories. It's important to note that this model, as defined, has two code snippet layers. Code snippet, the data flow and dual outputs. The code snippet method defines the sequential computation that happens when the model is called. It specifies how input features, code snippet, and the graph structure, code snippet, are processed through the layers to produce the final outputs. Code is not spoken. To get code, PLE, see the link in description or bio. In the first part of the code snippet pass, the input node features code snippet and the graph's code snippet, representing connectivity, are fed into code snippet. The output of code snippet then passes through the code snippet activation function. ReLU introduces nonlinearity, enabling the model to learn more complex relationships than it could with only linear transformations. Code snippet is applied as a regularization technique. During training, it randomly drops out, sets to 0, a fraction of the neuron activations. This prevents co-adaptation of neurons and helps the model generalize better to unseen data. The code snippet argument is crucial. Code snippet is a Boolean flag managed by PyTorch. Code snippet sets it to code snippet. Code snippet sets it to code snippet, ensuring dropout is only active during the training phase. Now, let's look at the second part of the code snippet pass, where the final embeddings and predictions are generated. Code is not spoken. To get code, please see the link in description or bio. In the latter part of the code snippet pass, the output from the first GCN layer, after ReLU and dropout, is fed into code snippet. The result of this operation, code snippet, represents the refined node embeddings learned by the GNN. These embeddings are designed to capture structural and feature information relevant to the classification task. Code snippet is applied to convert these raw code snippet into log probabilities for multi-class classification. Why code snippet? While code snippet directly outputs probabilities, values between 0 and 1 that sum to 1, code snippet outputs the logarithm of these probabilities. This is particularly useful when combined with PyTorch's code snippet, negative log likelihood loss. Code snippet expects log probabilities as input, and using code snippet helps in numerical stability by avoiding potential underflow issues when dealing with very small probabilities, especially in deep networks. What code snippet means? In a tensor of shape code snippet indicates that the code snippet operation should be applied independently to each row, i.e., for each node, ensuring that the log probabilities across the code snippet dimension sum to 1 when exponentiated. Finally, the code snippet method returns two tensors, code snippet, the raw node representation from the last GCN layer, and code snippet, the log probabilities for classification. This dual output provides flexibility, allowing users to either use the embeddings for downstream tasks, e.g., visualization, clustering, or directly use the predictions for classification. Implementing code snippet. Let's put the class definition together and then demonstrate how to instantiate and use it with dummy data. Full class definition. Code is not spoken. To get code, please see the link in description or bio. Instantiating and making a forward pass. To test our code snippet model, we need to instantiate it and provide some dummy input data. PyTorch geometric models typically expect node features, code snippet, and edge connectivity, code snippet. Code is not spoken. To get code, please see the link in description or bio. This code snippet sets up synthetic input data, code snippet and code snippet, that mimics real graph data. Code snippet provides features for 100 nodes, each with 128 features. Code snippet defines 500 random connections between these nodes. The code snippet is then instantiated with the specified dimensions. Now, let's perform a forward pass and inspect the outputs. Code is not spoken. To get code, please see the link in description or bio. After executing the code snippet call, we receive two tensors. Code snippet. This tensor has a shape of code snippet. It contains the refined feature representations for each node, learned by the GNN, which are directly suitable for the classification task. Code snippet. This tensor also has a shape of code snippet. It holds the log probabilities for each node belonging to each of the code snippet. These are the direct outputs used for calculating classification loss. Basic training loop snippet conceptual. In a real scenario, the code snippet would be used to calculate a loss against true labels, and the code snippet could be used for other analyses. Here's a conceptual snippet of how code snippet would fit into a training loop using code snippet. Code is not spoken. To get code, please see the link in description or bio. This snippet illustrates the core steps of a training iteration. Code snippet puts the model in training mode, enabling features like dropout. Code snippet clears old gradients. The forward pass calculates code snippet. Code snippet. We only calculate loss on the code snippet for nodes designated for training, using a code snippet. Code snippet computes the loss. Note that code snippet is specifically designed to work with code snippet outputs and integer class labels. Code snippet computes gradients of a loss with respect to all model parameters. Code snippet updates the model's weights based on these gradients. Interpreting predictions. After training, you'll want to evaluate your model. This involves setting the model to evaluation mode and then converting the log probabilities into actual class predictions. Code is not spoken. To get code, please see the link in description or bio. In evaluation, code snippet puts the model in evaluation mode, turning off dropout and other training-specific layers. Code snippet, a context manager that disables gradient computation, which is unnecessary during inference and saves memory. Code snippet. This is how you convert the log probability outputs into discrete class predictions. For each node, it finds the index, which corresponds to a class, that has the highest log probability. Practical considerations and applications. The code snippet model exemplifies the power of end-to-end learning in GNNs. Task-specific embeddings. The embeddings generated by code snippet are not generic graph embeddings. They're specifically learned to be discriminative for the classification task. This often leads to better performance than using pre-computed, task-agnostic embeddings. Unified pipeline. The entire process from feature input to classification output is contained within a single neural network, simplifying deployment and reducing potential inconsistencies between separate stages. Flexibility with dual outputs. Returning both code snippet and code snippet offers significant flexibility. Classification. The code snippet are directly used for calculating loss and determining class labels. Visualization. The code snippet can be extracted and reduced in dimensionality, e.g., using TSNE or UMAP, to visualize the learned node representations in 2D or 3D space, providing insights into the model's understanding of node relationships and clusters. Downstream tasks. The code snippet can serve as powerful features for other machine learning tasks that might benefit from graph-aware representations, even if they are not directly handled by the GNN's classification head. By understanding and implementing end-to-end GNNs like code snippet, you gain a critical tool for building sophisticated graph-based machine learning solutions that are both powerful and efficient. The core of any deep learning model's lifecycle is the training loop. This iterative process refines the model's parameters by repeatedly feeding it data, calculating prediction errors, and adjusting parameters to minimize these errors. For graph neural networks, GNNs, this process includes specific considerations for handling graph structure data and often operates in a semi-supervised setting, where only a subset of nodes have known labels. The purpose of the training loop. A training loop orchestrates the learning process over multiple iterations, known as epochs. Each epoch typically involves a sequence of standard deep learning steps. 1. Forward pass. The model processes input data, node features, and graph structure to generate predictions for all nodes. 2. Loss computation. A loss function quantifies the discrepancy between the model's predictions and the true labels. Crucially, in a semi-supervised GNN context, loss is only computed on the labeled subset of nodes. 3. Backward pass. Backpropagation gradients of a loss with respect to the model's learnable parameters are computed. These gradients indicate the direction and magnitude for parameter adjustments needed to reduce the loss. 4. Parameter update. An optimizer uses these gradients to update the model's parameters, moving them towards values that minimize the calculated loss. This iterative process continues for a predefined number of epochs, gradually improving the model's ability to make accurate predict. Tie-ins. Essential components for training. Before we dive into the loop itself, we need to define and initialize a few critical components: the optimizer, the loss function, and our prepared graph data. Initializing the optimizer and loss function. The optimizer is the algorithm responsible for updating the model's parameters based on the computed gradients. A widely favored choice for many deep learning tasks, including GNNs, is the Atom optimizer due to its adaptive learning rate capabilities and generally robust performance. The code snippet code snippet, is a crucial hyperparameter that dictates the size of the steps taken during parameter updates. A smaller learning rate leads to slower but potentially more stable convergence, while a larger one can speed up training but risks overshooting the optimal solution or diverging. The loss function quantifies the error between the model's predictions and the true labels. For multi-class node classification, code snippet is a standard and robust choice. It internally combines the code snippet operation, which converts raw model outputs into log probabilities, and code snippet, negative log likelihood loss, into a single, numerically stable function. Code is not spoken. To get code, please see the link in description or bio. In this setup, we first import necessary PyTorch modules and define a placeholder code snippet class for a complete example. We then create a dummy code snippet object to simulate the code snippet struct. Which holds our graphs features, code snippet, connectivity, code snippet, all true labels, code snippet, and the crucial code snippet. Code snippet is a Boolean tensor where code snippet indicates a node that has a known label and will be used for computing the training loss. We extract code snippet by applying this mask to code snippet. Finally, we initialize our code snippet model, the code snippet optimizer with a learning rate of code snippet, and the code snippet function. A specific point of clarification, code snippet is used in the code snippet's forward pass. The code snippet argument is critical because it ensures that the softmax operation is applied across the feature dimension, which corresponds to the class probabilities for each node, rather than across the node dimension. This is essential for multi-class classification, as it ensures that for each node, the sum of probabilities across all classes, after exponentiation from log probabilities, equals 1. Understanding code snippet. Before each forward pass and backpropagation step within the training loop, it is imperative to call code snippet. Code is not spoken. To get code, please see the link in description or bio. PyTorch, by default, accumulates gradients. This means that if you perform multiple code snippet calls without clearing the gradients, the new gradients will be added to the existing ones. While this can be useful for advanced techniques like gradient accumulation over mini batches, for a standard per epoch or per batch update, clearing them is necessary. Failing to call code snippet would lead to incorrect and ever-increasing parameter updates, preventing the model from converging properly. Implementing the training loop. Now, let's assemble the training loop. This loop iterates for a specified number of code snippet, performing the forward pass, loss calculation, backpropagation, and parameter updates in each iteration. Code is not spoken. To get code, please see the link in description or bio. The loop begins by iterating up to code snippet times. Inside, code snippet is called to ensure the model is in training mode, e.g., enabling dropout layers. Then, code snippet is called first to ensure gradients from the previous iteration do not interfere. The code snippet is then called with code snippet, node features, and code snippet, graph structure. The code snippet is crucial for GNNs as it defines the graph's connectivity, allowing message passing operations within layers like code snippet to aggregate information from neighbors. The output code snippet contains raw predictions, log probabilities due to code snippet and code snippet for all nodes in the graph. Semi-supervised loss computation. In a semi-supervised setting, we only have labels for a subset of nodes. We must ensure that our loss calculation only considers these labeled nodes to avoid propagating errors from unlabeled data. This is achieved efficiently using a Boolean mask, code sni. Pet. Code is not spoken. To get code, please see the link in description or bio. Here, code snippet performs a crucial indexing operation. It filters the code snippet tensor, retaining only the rows, node predictions, where code snippet is code snippet. This code snippet tensor then contains predictions solely for the labeled training nodes. The code snippet then compares these code snippet predictions with their corresponding code snippet to calculate the error. Backpropagation and parameter update. Once the loss is computed, the model needs to learn from this error by adjusting its internal parameters. Code is not spoken. To get code, please see the link in description or bio. Code snippet triggers the backpropagation algorithm, which calculates the gradients of the loss with respect to every trainable parameter in the code snippet. These gradients are stored in the code snippet attribute of each parameter. Finally, code snippet uses these stored gradients to update the parameters according to the optimizer's algorithm, e.g. atom. The code snippet statement provides periodic logging of the current epoch and loss, converting the code snippet tensor to a scalar using code snippet for cleaner printing. Evaluating model performance during training. Monitoring only the loss provides an incomplete picture of model performance. It's often beneficial to track actual classification metrics, such as accuracy, on both the training and, if available, validation sets. This helps identify issues like overfitting, low training loss, high validation loss, or underfitting, high loss on both. Code is not spoken. To get code, please see the link in description or bio. By adding this evaluation block, we gain insight into how well the model is classifying the training data. We switch the model to code snippet mode to disable features like dropout, which are only active during training. Code snippet prevents gradient computations, saving memory, and speeding up evaluation. We then get the code snippet by taking the code snippet, the index of the maximum log probability, which corresponds to the predicted class, along code snippet, the class dimension. Finally, we compare these predictions on the training mask with the true code snippet to compute accuracy. Remember to switch the model back to code snippet mode before the next training iteration. For a real-world scenario, you would typically evaluate on a separate code snippet and code snippet to get an unbiased estimate of generalization performance. Saving and loading the model. Once training is complete, you'll want to save your trained model for future use or deployment. PyTorch models are typically saved by storing their code snippet, which is a Python dictionary containing all the learnable parameters, weights, and biases. This method is generally preferred over saving the entire model object because it's more flexible. You can load it into a different machine or a slightly modified architecture as long as the parameter names and shapes match. Code is not spoken. To get code, please see the link in description or bio. When loading, you first instantiate an empty model with the same architecture, then load the code snippet into it. It's good practice to set the loaded model to code snippet mode if you're using it for inference, as this deactivates training-specific layers like dropout, making predictions on unlabeled nodes, inference. The ultimate goal of training a semi-supervised GNN is often to leverage the learned graph structure and labeled data to predict labels for the nodes that were unlabeled during training. Code is not spoken. To get code, please see the link in description or bio. For inference, the model is set to code snippet mode, and gradient computation is disabled using code snippet. A forward pass is performed on the entire graph, code snippet, code snippet. The output code snippet contains the log probabilities for all nodes, and code snippet converts these into the most probable class for each node. This allows you to obtain predictions for any node in the graph, regardless of whether it was labeled during training. Hyperparameter tuning and best practices. The choices made for hyperparameters like learning rate, number of epochs, and optimizer type significantly impact model performance and the training process. Effective hyperparameter tuning is crucial for achieving optimal results. Learning rate schedules. While a fixed learning rate works, for many cases, using a learning rate schedule can further optimize training. A scheduler adjusts the learning rate over time, often reducing it as training progresses. This can help the model converge more effectively in later stages, allowing for larger steps initially and finer adjustments closer to the optimum. Code is not spoken. To get code, please see the link in description or bio. Common schedulers include code snippet, reduces LR by a factor every few epochs. Code snippet reduces LR when a monitored metric, like validation loss, stops improving, and code snippet anneals the LR following a cosine curve. Other critical hyperparameters. Number of epochs. Training for too few epochs can lead to underfitting. The model hasn't learned enough from the data. Too many can lead to overfitting. The model memorizes the training data, but performs poorly on unseen data. Monitoring validation loss and accuracy helps determine an optimal stopping point. Early stopping, where training halts if validation performance degrades for a certain number of epochs, is a common and effective technique. Dropout rate. The code snippet layer in our code snippet applies regularization by randomly setting a fraction of input features to 0 during training. The dropout rate, e.g., 0.5, is a hyperparameter. Tuning it can significantly prevent overfitting by making the model less reliant on any single feature or neuron. Optimizer choice. While Atom is robust, other optimizers like SGED, with momentum, RMSprop, or specialized optimizers for sparse data might perform better on specific datasets or architectures. Experimentation is key. Model architecture. The number of GCN layers, the hidden dimensions of these layers, and the choice of activation functions are critical architectural hyperparameters that directly influence the model's capacity and ability to learn complex patterns. Hyperparameter tuning often involves systematic approaches like grid search, exhaustively trying combinations, random search, randomly sampling combinations, often more efficient for high-dimensional spaces, or more advanced methods like Bayesian optimization, which intelligently explore the hyperparameter space. Visualizing embeddings post-training. Just as we might visualize initial, random embeddings to understand the raw data distribution, it's highly informative to visualize the embeddings after training. A well-trained GNN should produce embeddings where nodes of the same class are clustered together and different classes are distinctly separated in the embedding space. This provides qualitative evidence of how the GNN has learned to group nodes based on their features and graph structure to facilitate classification. Techniques like UMAP, Uniform Manifold Approximation and Projection, or TSNE, T-Distributed Stochastic Neighbor Embedding, are invaluable for dimensionality reduction, allowing us to project high-dimensional embeddings into 2D or 3D for visual inspection. While detailed code for visualization is beyond this section's scope, understanding its purpose is key. It offers a powerful way to interpret the learning process and confirm that the GNN has successfully captured meaningful relationships within the graph data. GNN results. Randomized versus N2V node features. This section presents a comprehensive comparison of graph neural network, GNN, classification performance when initialized with different node features, randomly initialized features versus pre-computed node 2vec, N2V, embeddings. This evaluation is critical for understanding the impact of initial node representation quality on the effectiveness of an end-to-end GNN model for semi-supervised node classification tasks. Initializing node features. A recap. Before diving into the results, it's important to briefly recap how the initial node features were prepared for the GNN models. The choice of initial features significantly influences how a GNN learns and performs. Randomized feature initialization. When using randomized features, each node's initial representation is essentially a vector of random numbers. This is a common baseline approach, particularly when no meaningful intrinsic node attributes are available or when the goal is to allow the GNN to learn all representations from scratch. Code is not spoken. To get code, please see the link in description or bio. In this setup, the GNN must learn meaningful representations for each node solely based on the graph structure and the random starting points. While conceptually simple, this puts a greater burden on the GNN to perform both representation, learning, and classification simultaneously. The code snippet approach is often preferred as it allows these initial random vectors to be updated during the training process, becoming more meaningful as the GNN learns. Node 2vec feature initialization. Node 2vec features, on the other hand, are pre-computed embeddings that capture structural proximity and community information within the graph. These embeddings are generated by simulating random walks on the graph and applying a skipgram model, similar to Word 2vec. Code is not spoken. To get code, please see the link in description or bio. When a GNN is initialized with Node 2vec features, it starts with a rich, structurally aware representation for each node. The GNN's role then shifts from learning fundamental structural representations to refining these pre-existing embeddings and adapting them specifically for the downstream classification task. This often leads to faster convergence and superior performance. GNN architectures for comparison. To understand the impact of initial features, two different GNN architectures were used, a 2-layer GNN and a 4-layer GNN. Both models are based on the Graph Convolutional Network, GCN, architecture, which aggregates information from a node's immediate neighbors. 2-layer GNN architecture. A 2-layer GNN is a common and often effective starting point for many graph tasks. It allows each node to aggregate information from its 2-hop neighborhood. Code is not spoken. To get code, please see the link in description or bio. This architecture processes information through 2 convolutional layers, typically, followed by activation functions like ReLU and dropout for regularization. The code snippet would be the dimension of the initial features, e.g., 64 for N2V or randomized, code snippet an intermediate dimension, and code snippet the number of classes. 4-layer GNN architecture. A 4-layer GNN allows for aggregation of information from a larger neighborhood, up to 4 hops away. While deeper networks can capture more complex relationships and broader structural context, they also risk issues like oversmoothing, where node representations become indistinguishable or increase computational cost. Code is not spoken. To get code, please see the link in description or bio. This code snippet extends the concept by simply stacking more code snippet layers. Each intermediate layer typically maintains the code snippet dimension, allowing for progressive refinement of node representations. The final layer maps to the code snippet number of classes. The decision to use a deeper network often depends on the complexity of the graph structure and the task at hand. For this comparison, it helps illustrate how different initial features interact with model depth. Experimental setup and evaluation metrics. The comparison was conducted on the political books dataset, a common benchmark for semi-supervised node classification. The goal is to classify books into political ideologies based on their connections within the network. The primary evaluation metrics used were accuracy, the proportion of correctly classified nodes. While intuitive, accuracy can be misleading in datasets with imbalanced class distributions. F1 score, the harmonic mean of precision and recall. F1 score provides a more balanced measure, especially when dealing with imbalanced classes, as it penalizes models that perform well on the majority class but poorly on minority classes. A higher F1 score indicates a more robust and reliable classification performance across all classes. Performance comparison, randomized versus node 2-vec features. The results consistently show that initializing GNNs with node 2-vec features leads to significantly better classification performance compared to randomized features. Model configuration accuracy, approximate. F1 score, approximate. 2-layer GNN, randomized, 60 to 70%, 55 to 65%. 2-layer GNN, node 2-vec, 80 to 90%, 75 to 85%. 4-layer GNN, randomized, 60 to 70%, 55 to 65%. 4-layer GNN, node 2-vec, 85 to 95%, 80 to 90%. Note, exact percentages vary based on specific hyperparameters and training runs, but the trend is consistent. Why node 2-vec features provide a significant boost? The substantial performance improvement with node 2-vec features can be attributed to several key factors. 1. Pre-computation of structural priors. Node 2-vec captures intrinsic graph properties like community structure, roles, and proximity before the GNN even starts training. It generates embeddings, where nodes that are structurally similar, e.g., frequently co-occur in random walks, are close in the embedding space. 2. Informed starting point for GNN. The GNN, when initialized with these rich N2V embeddings, doesn't have to learn these fundamental structural patterns from scratch. Instead, It can focus its learning capacity on refining these already informative representations to optimally suit the classification task. This is akin to providing a deep learning model with pre-trained image features, e.g., from ImageNet, rather than random pixels. 3. Efficiency in learning. With better initial features, the GNN often converges faster and requires less labeled data to achieve high performance. The search space for optimal parameters is effectively narrowed. 4. Robustness to limited labeled data. In semi-supervised settings, where only a small fraction of nodes are labeled, the strong structural priors from Node 2 VEC are invaluable. They provide a rich context that helps the GNN generalize better to unlabeled nodes, even when the labeled data is sparse. Impact of network depth. The comparison also highlights the interaction between initial features and network depth. Deeper networks benefit from good features, while a 4-layer GNN with randomized features doesn't significantly outperform its 2-layer counterpart, and might even perform worse due to over-smoothing or increased training difficulty. A 4-layer GNN with Node 2 VEC features often achieves the highest performance. This suggests that deeper GNNs can leverage the rich, pre-computed structural information from Node 2 VEC more effectively to capture complex, multi-hop relationships relevant to the classification task. Over-smoothing with randomized features. For deeper GNNs initialized with random features, the risk of over-smoothing increases. Without strong initial signals, the repeated aggregation of neighbor information can cause node embeddings to converge to similar values, making them indistinguishable and hindering classification. Trade-offs and practical considerations. While Node 2 VEC features offer clear advantages, it's important to consider practical trade-offs. Computational overhead of Node 2 VEC pre-computation. For very large graphs, generating Node 2 VEC embeddings can be computationally expensive and time-consuming. This pre-processing step might be a bottleneck, especially if the graph structure changes frequently. Training time differences. GNNs initialized with Node 2 VEC features often converge faster during training because they start from a more optimized feature space. This can lead to shorter overall training times, even accounting for the pre-computation. Scenarios for randomized features. There are specific situations where randomized features might still be preferred or necessary. Extremely large graphs, when Node 2 VEC pre-computation is infeasible due to scale. Rich intrinsic node attributes. If nodes already possess highly informative attributes, e.g., textual descriptions, numerical data, that the GNN can learn from directly, the benefit of Node 2 VEC might be less pronounced. The GNN can then focus on integrating these attributes with structural information. Pure representation learning. If the goal is for the GNN to be a pure end-to-end representation learner without external priors, this can serve as a strong baseline to understand the inherent representational power of the GNN itself. When the GNN must learn from scratch, in specific research or application contexts where the model is expected to derive all necessary information from the raw graph structure and minimal input. In most practical scenarios, if feasible, combining the strengths of pre-computed embeddings like Node 2 VEC with the adaptive learning of GNNs provide the powerful approach to graph machine learning. Beyond classification, downstream applications of learned embeddings. The embeddings learned by the GNN, whether initialized randomly or with N2V, are not solely useful for the classification task they were trained on. These refined, task-aware node representations can be highly valuable for a variety of other downstream graph machine learning tasks. Link prediction. Predicting the existence of missing or future edges between nodes. The similarity between the learned embeddings of two nodes can be used as a score for potential linkage. Anomaly detection. Identifying unusual nodes or subgraphs. Nodes with embeddings that are outliers in the learned embed. ING space might indicate anomalous behavior or properties. Node clustering. Grouping similar nodes into clusters based on their learned embeddings. This can reveal hidden communities or organizational structures within the graph. Visualization. projecting the high-dimensional learned embeddings into 2D or 3D space using techniques like UMAP or TSNE. This allows for visual inspection of node relationships and cluster separation, offering insights into how the GNN has structured the graph's information. For instance, visualizing embeddings after training would likely show distinct, well-separated clusters for Node 2 VEC initialized models, while randomized initialized models might show less clear separation, even after GNN refinement. The versatility of these learned embeddings underscores the power of end-to-end GNN models in generating general-purpose representations of complex graph data. Results: GNN versus random forest. This section serves as a crucial empirical validation, bringing together the concepts of graph embeddings, end-to-end graph neural networks, GNNs, and semi-supervised learning. We will quantitatively compare the performance of GNN models against traditional machine learning classifiers, specifically random forest, for node classification on graph structure data. The focus will be on understanding the impact of different node feature initialization strategies, randomized versus Node 2 VEC embeddings, and GNN architectural choices, 2-layer versus 4-layer GNNs, on classification performance. Recap of experimental setup. To provide context for the results, let's briefly recap the experimental setup used for the semi-supervised node classification task on the political books dataset. The political books dataset consists of approximately 105 nodes, books, and 441 edges, representing co-purchases. Each node is labeled as left-leaning, right-leaning, or neutral. The semi-supervised setting implies that only a subset of nodes have known labels during training, and the models must classify the remaining unlabeled nodes. We compared two main categories of models. 1. Random forest classifier, a traditional ensemble learning method that does not inherently understand graph topology. For this classifier, node features were extracted and flattened. We explored two types of features. Randomized node features, simple, randomly initialized vectors for each node, serving as a baseline to see how well a model performs without any structural information. Node 2 VEC embeddings, pre-computed, low-dimensional embeddings generated by the Node 2 VEC algorithm. These embeddings capture structural similarity in the graph, providing a richer feature set. 2. Graph neural networks, GNNs models designed specifically for graph structured data, leveraging message passing to learn node representations that incorporate neighborhood information. We investigated GNN with randomized node features, a GNN trained end-to-end, starting with simple randomized features. The GNN itself is responsible for learning meaningful representations through message passing. GNN with Node 2 VEC embeddings, a GNN that takes Node 2 VEC embeddings as its initial node features. This allows the GNN to refine and generalize from these pre-computed structural embeddings. Varying GNN depth. We tested both 2-layer and 4-layer GNN architectures to assess the impact of network depth on learning more complex, multi-hop neighborhood patterns. A 2-layer GNN typically captures information from a node's 2-hop neighborhood, while a 4-layer GNN can capture information from a 4-hop neighborhood. Interpreting classification performance metrics. When evaluating classification models, especially in multi-class or imbalanced scenarios, it's crucial to look beyond simple accuracy. We primarily focus on accuracy, the proportion of correctly classified instances out of the total instances. While intuitive, it can be misleading if classes are imbalanced. For example, if 90% of books are neutral, a model predicting all books as neutral would achieve 90% accuracy, despite being useless for left or right classification. Precision. Out of all instances predicted as a certain class, how many were actually correct? High precision for left-leaning books means that when the model says a book is left-leaning, it's very likely to be correct. Recall. Sensitivity out of all actual instances of a certain class, how many were correctly identified by the model? High recall for left-leaning books means the model successfully finds most of the truly left-leaning books. F1, score. The harmonic mean of precision and recall. It provides a balanced measure that considers both false positives and false negatives. A high F1 score indicates that the model has good precision and good recall, making it a more robust metric for evaluating performance across different classes, especially in imbalanced datasets. The political books dataset, while not severely imbalanced, benefits from F1 score analysis to ensure that minority classes, e.g., specific political leanings, are not overlooked. Let's consider a practical example using Python's code snippet to simulate and interpret these metrics. We'll set up some dummy prediction data for illustration. Code is not spoken. To get code, please see the link in description or bio. This initial code block sets up mock true and predicted labels for a multi-class classification problem. The code snippet function from code snippet is a powerful tool that automatically calculates precision, recall, and F1 score for each class, along with overall accuracy and macro/weighted averages. This allows us to quickly assess a model's performance across all categories. Code is not spoken. To get code, please see the link in description or bio. By comparing the code snippet outputs for code snippet and code snippet, which in our actual scenario represent random forest and GNNs, respectively, we can directly observe which model performs better for specific classes or overall. For instance, if code snippet shows a higher F1 score for the left class, it implies it's more effective at identifying left-leaning books accurately and comprehensively. Comparative performance analysis, GNNs versus random forest. The empirical results consistently demonstrate the superior performance of GNN models over traditional machine learning classifiers like random forest for semi-supervised node classification on graph data. Why GNNs generally outperform random forest? The fundamental reason for the GNN's advantage lies in its ability to inherently leverage the graph's topological structure. Random forest and other traditional ML models, when applying random forest to graph data, the graph structure is typically flattened into node features, e.g., node 2-vec embeddings or simple randomized features. The random forest model then treats each node's feature vector independently. It makes predictions based solely on these features, without any explicit knowledge of how nodes are connected or how information flows through the graph. This means it cannot capture relationships like nodes connected to a certain type of node are likely to belong to a specific class. Graph neural networks, GNNs, through their message passing mechanism, are designed to aggregate information from a node's local neighborhood. Each GNN layer effectively learns to combine features from a node's immediate neighbors, propagating information across the graph. This allows GNNs to learn rich, context-aware node representations that implicitly encode structural patterns. For example, a GNN can learn that a neutral book often has co-purchase links to both left-leaning and right-leaning books, a pattern a random forest would struggle to discern from flattened features alone. In essence, random forest is like analyzing individual ingredients of a dish, while a GNN is like analyzing the entire recipe, understanding how ingredients interact and contribute to the final flavor. The graph structure provides crucial contextual information that GNNs are uniquely positioned to exploit. To illustrate how we might load and compare results from different models, consider the following simulated data loading. In a real-world scenario, code snippet would retrieve actual saved predictions from trained models. Code is not spoken. To get code, please see the link in description or bio. This code simulates the process of loading prediction results for various models and then calculates their accuracy in F1 macro scores. The code snippet function is a placeholder that, in a real project, would load actual saved predictions from disk. The output code snippet would then mirror the kind of comparison table typically found in research papers or tutorials, allowing for direct comparison of different approaches. Impact of node features. Randomized versus node 2-vec embeddings. The choice of initial node features significantly impacts GNN performance. Randomized node features. When GNNs start with randomized features, they must learn meaningful representations from scratch, solely relying on the graph structure and the limited training labels. This is a more challenging task. Node 2-vec embeddings. Node Node2Vec provides a strong, structurally informed prior. It generates embeddings by simulating random walks on the graph, capturing a node's local and global neighborhood context. When these rich Node2Vec embeddings are fed into a GNN, the GNN doesn't have to discover basic structural relationships. It can instead focus on refining these embeddings and learning how to best combine them through message passing for the specific classification task. This often leads to a substantial boost in performance, as the GNN has a much better starting point for its learning process. Essentially, Node2Vec pre-processes T. He graphs topology into a dense vector space that is easier for the GNN to digest and build upon. While Node2Vec itself is a transductive method, meaning it needs to be rerun if new nodes are added to the graph, using its output as input features for an inductive GNN allows the GNN to leverage this strong structural information while still maintaining its ability to generalize to unseen nodes during inference, if trained appropriately, e.g., using node features that can be generated for new nodes. Impact of GNN depth, 2-layer versus 4-layer GNNs. Increasing the depth of a GNN, i.e., adding more layers, allows it to aggregate information from larger neighborhoods around each node. 2-layer GNN. Each node aggregates information from its one-hop neighbors in the first layer, and then from its two-hop neighbors, neighbors of neighbors, in the second layer. This captures local structural patterns. 4-layer GNN. A 4-layer GNN can aggregate information from up to 4-hop neighbors. This enables the model to capture more global structural patterns and longer-range dependencies within the graph, which can be crucial for complex classification tasks where a node's label might depend on distant nodes. For the political books dataset, deeper GNNs, particularly the 4-layer architecture with Node2Vec features, often show a better F1 score. This suggests that understanding the broader context of a book's co-purchase patterns, e.g., not just who bought this book, but who bought books related to those who bought this book, is beneficial for accurate classification. However, increasing depth also brings challenges like increased computational cost and the potential for over-smoothing, where node representations become indistinguishable across the graph due to excessive message passing. Careful tuning and regularization are essential for deeper GNNs. Transductive versus inductive learning, a revisited perspective. The comparison between Node2Vec features and GNNs also highlights the distinction between transductive and inductive learning paradigms. Transductive learning, e.g., Node2Vec learns embeddings for all nodes present in the training graph. If a new node is added or the graph structure changes significantly, the entire embedding process needs to be rerun. Node2Vec is excellent for capturing fixed structural information. Inductive learning, e.g., GNNs learns a function that maps node features and graph structure to predictions. Once trained, an inductive GNN can make predictions on unseen nodes or even entirely new graphs, provided it can generate features for these new nodes. In our setup, using Node2Vec features as input to a GNN creates an interesting hybrid. The Node2Vec component is transductive, providing a static, structurally rich feature set. The GNN, however, is inductive, learning how to process these features and propagate information. This combination allows us to leverage the strong structural prior from Node2Vec while retaining the GNN's ability to generalize its learned function. This is particularly useful in scenarios where the graph structure is relatively static for embedding generation, but new nodes might appear for classification. Practical implications and best practices. The insights gained from this comparative analysis are highly valuable for real-world graph machine learning applications. Prioritize GNNs for graph data. For classification tasks on graph structure data where topological information is relevant, GNNs generally offer superior performance compared to traditional machine learning models that treat nodes as independent entities. Feature engineering matters. Investing in rich node features, such as those derived from graph embedding techniques like Node2Vec, can significantly boost GNN performance. These pre-computed embeddings provide a strong foundation for the GNN to build upon. Consider GNN depth. Deeper GNN architectures can capture more complex, long-range dependencies, potentially leading to better F1 scores, especially when a classification task requires understanding broader network contexts. However, always balance depth with computational cost and the risk of oversmoothing. Balanced evaluation. Always use a combination of metrics like accuracy and F1 score, macro or weighted, to get a comprehensive understanding of a model's performance, especially in multi-class or imbalanced datasets. Beyond political books, these findings are transferable to numerous domains. Drug discovery, predicting properties of molecules, nodes, based on their atomic structure, edges, and functional groups, features. Fraud detection, identifying fraudulent transactions, nodes, by analyzing their connections in a financial network. Social network analysis, classifying users, nodes, based on their connections and interactions. Recommender systems, predicting user preferences by modeling user-item interaction graphs. This section provides a strong empirical foundation, demonstrating the power of GNNs and the importance of informed feature engineering and architectural choices in tackling real-world graph-based classification challenges. 2.1 Understanding Graph Embeddings. Transductive versus inductive learning. At the heart of modern graph machine learning lies the concept of graph embeddings, which transform complex graph structures and node attributes into a lower-dimensional, continuous vector space. These embeddings serve as rich, learned features that can then be used by standard machine learning models for tasks like node classification, link prediction, or clustering. However, the way these embeddings are generated dictates a fundamental characteristic of the learning process, whether it is transductive or inductive. This distinction is crucial for understanding the capabilities and limitations of different graph embedding techniques, particularly when dealing with evolving graphs or unseen data. 2.1.1 Transductive learning. Fixed data, fixed embeddings. Transductive learning refers to a machine learning paradigm where the model learns directly from and makes predictions only on the specific data points observed during training. In the context of graphs, a transductive model computes embeddings for all nodes present in a given fixed graph. These embeddings are intrinsically tied to the exact topology and features of that specific training graph. The primary characteristic of transductive learning is that it does not learn a generalizable function that can be applied to new, unseen data. Instead, it learns representations for the specific instances provided. If new nodes or edges are added to the graph, or if the graph structure changes significantly, the entire embedding process typically needs to be rerun from scratch to generate consistent embeddings for the updated graph. This can be computationally expensive and inefficient for dynamic graphs. Node2Vec is a prime example of a transductive graph embedding method. It processes a fixed graph to learn node representations that capture structural equivalences within that graph. Limitations of transductive learning. Node generalization cannot directly generate embeddings for new nodes or subgraphs that were not part of the training data. Retraining cost requires full retraining or re-embedding of the entire graph when new data arrives, leading to significant computational overhead for dynamic graphs. Static assumption, best suited for static graphs where the structure remains largely unchanged over time. 2.1.2 Inductive learning, generalizable functions for evolving data. In contrast, inductive learning aims to learn a generalizable function or a set of rules from the training data that can then be applied to make predictions on any new, unseen data. For graph-based tasks, an inductive model learns a function that can compute a node's embedding based on its local neighborhood structure and features, regardless of whether that node was present during training. The key advantage of inductive learning is its ability to generalize. Once an inductive model is trained, it can efficiently generate embeddings for new nodes, new edges, or even entirely new graphs without requiring a complete retraining process. This makes inductive methods highly suitable for dynamic graphs, where nodes and connections are constantly changing, or for scenarios where you need to apply a learned model to a completely different graph. Graph neural networks, GNNs, are the quintessential example of inductive graph embedding methods. They learn how to aggregate and transform information across a node's local neighborhood, effectively learning a recipe for generating embeddings. Advantages of inductive learning. Generalization can generate embeddings for new, unseen nodes, edges, or even entire graphs. Scalability for dynamic graphs. Efficiently handles evolving graph structures without extensive retraining. Feature integration naturally incorporates node features, attributes, into the embedding process, leading to richer representations. 2.2 Node 2vec, capturing topology with random walks. Node 2vec is a transductive algorithm designed to learn low-dimensional, continuous feature representations, embeddings, for nodes in a network. Its core idea is that nodes that appear in similar neighborhoods within the graph should have similar embeddings. Node 2vec achieves this by simulating a series of biased random walks on the graph, and then applying a skipgram model, similar to Word 2vec, to these sequences of nodes. 2.2.1 The mechanism of biased random walks. A random walk is simply a sequence of nodes visited by. Why starting at a random node and then moving to a randomly chosen neighbor, and so on, for a specified number of steps. Node 2vec enhances this by introducing biased, random walks, which allow for a flexible exploration of a node's neighborhood. These biases are controlled by two parameters. Code snippet, return parameter, influences the probability of immediately revisiting the previous node. A high code snippet discourages immediate revisits, making the walk less back and forth. Code snippet, in-out parameter controls whether the walk prefers to explore nodes close to the starting node, BFS-like behavior with code snippet, or nodes further away, DFS-like behavior with code snippet. By adjusting code snippet and code snippet, Node 2vec can generate node sequences that capture different notions of neighborhood, effectively blending local, BFS-like, and global, DFS-like, structural information. Consider a simple graph represented as an adjacency list. Code is not spoken. To get code, please see the link in description or bio. This dictionary code snippet maps each node to a list of its direct neighbors. Now, let's conceptualize how a single biased random walk might be generated. Code is not spoken. To get code, please see the link in description or bio. This code snippet function demonstrates the basic iterative process of extending a walk. In a true Node 2vec implementation, the code snippet step will be replaced by a weighted choice based on code snippet and COD. E-snippet parameters, which influence the transition probability to the next node given the previous node in the walk. This allows the algorithm to explore neighborhoods in a flexible manner, capturing both local, BFS-like, and global, DFS-like, structural information. For instance, if we start a walk from node, code is not spoken. To get code, please see the link in description or bio. This line calls our simplified function to generate a walk of length 5, starting from The output code snippet is one possible sequence of nodes visited. 2.2.2 Generating embeddings with skipgram. Once numerous such random walks are generated from every node in the graph, they form a corpus of node sequences. Each sequence can be thought of as a sentence, and each node as a word within that sentence. The skipgram model, famously used in Word 2vec, is then applied to this corpus. The skipgram model's objective is to predict the context, neighboring nodes in the walk, given a target node. By training a neural network to perform this prediction, the model learns dense vector representations, embeddings, for each node. Nodes that frequently appear together in the random walks, i.e., are part of similar neighborhoods, will have similar embeddings. Node 2vec's transductive nature. The random walks are performed on the entire fixed graph. If a new node is added, or the graph structure changes, the random walks must be regenerated across the entire updated graph and the skipgram. Model must be retrained to obtain new embeddings that reflect these changes. This is why it's considered transductive. 2.3 Graph neural networks. Integrating information via message passing. Graph neural networks, GNNs, represent an inductive approach to learning node embeddings. Unlike Node 2vec, which relies on sampling node sequences, GNNs learn a function that can aggregate information from a node's local neighborhood to compute its representation. This mechanism, known as message passing, is the cornerstone of most GNN architectures. 2.3.1 The mechanism of message passing. Message passing in GNNs can be intuitively understood as a process where information flows or spreads through the graph. Each node iteratively aggregates information, messages, from its direct neighbors and then updates its own representation based on these aggregated messages and its previous state. This process is typically repeated for several layers, allowing information to propagate further into a node's multi-hop neighborhood. Consider it like a social network where gossip spreads. Each person, node, hears gossip from their friends, neighbors, synthesizes it with what they already know, and then forms their own updated understanding. This updated understanding then becomes part of the gossip they pass on to their friends in the next round. The message passing process for a single GNN layer can be broken down into 3 conceptual steps. 1. Message generation. Each neighbor of a target node creates a message based on its own current features or embedding. This message often involves a transformation, e.g., a linear layer of the neighbor's information. 2. Message aggregation. The target node collects all messages from its neighbors and combines them into a single, fixed-size vector. This aggregation function must be permutation invariant, meaning the order in which messages are received does not affect the aggregated result, e.g., sum, mean, max. 3. Node update. The target node updates its own embedding by combining its previous embedding or initial features with the aggregated message. This often involves another transformation, e.g., a neural network layer and an activation function. Let's illustrate these conceptual steps with simplified Python-like functions. Code is not spoken. To get code, please see the link in description or bio. These classes, code snippet and code snippet, encapsulate the core transformations. Code snippet represents how a neighbor's information is prepared to be sent, while code snippet shows how a node combines its own information with what it received. Now, let's put these together in a conceptual message passing loop for one layer. Code is not spoken. To get code, please see the link in description or bio. The code snippet function illustrates the iterative nature. For each node, it gathers messages from its neighbors, aggregates them, and then updates the node's embedding. This process is repeated for multiple layers, allowing information to flow from increasingly distant neighbors. 2.3.2 How message passing enables inductive learning. The inductive power of GNNs stems directly from the message passing paradigm. Unlike Node 2vec, which learns a fixed embedding for each node in a given graph, a GNN learns the functions for message generation, aggregation, and node update. Because these functions, e.g., code snippet and code snippet, are learned during training, they can be applied to any node, even those not seen during training, as long as their local neighborhood structure and features are available. When a new node appears in the graph, the trained GNN model can simply apply its learned aggregation and update functions to that new node's neighbors to compute its embedding. This is a fundamental difference. The GNN learns how to compute an embedding, not just what the embedding is for specific nodes. This function learning aspect is what allows GNNs to generalize effectively to new nodes, edges, or even entirely new graphs, making them indispensable for dynamic real-world applications. 2.4 Node 2vec versus GNNs, a comparative analysis. The choice between Node 2vec and GNNs depends heavily on the specific characteristics of your graph data and the requirements of your machine learning task. While GNNs offer significant advantages in many modern applications, Node 2vec still holds its ground in particular scenarios. Here's a summary table comparing key aspects. Feature/aspect, Node 2. Vec, transductive, graph neural networks, inductive. Learning paradigm, transductive, learns fixed embeddings for observed nodes. Inductive, learns a generalizable function for embedding generation. Feature utilization primarily uses graph topology, ignores node features unless explicitly preprocessed, directly integrates, and leverages node features, attributes, alongside topology. Generalization cannot generalize to new/unseen nodes. Requires retraining, generalizes well to new nodes, edges, and even new graphs. Retraining for new data, full re-embedding/retraining of the model on the updated graph is typically required efficient inference for new nodes. Model retraining only for significant concept drift. Computational cost high for dynamic graphs due to frequent retraining. Can be efficient for static graphs. Training can be resource intensive. Inference is generally efficient. Typical use cases: static social networks, fixed knowledge graphs, historical data analysis, dynamic recommendation systems, fraud detection, drug discovery, evolving social networks. Primary mechanism: biased random walks plus skipgram message passing. Aggregation plus update. Complexity: relatively simpler to implement and understand more complex architectures. Requires deeper understanding of neural net 2. Works 2.4.1 when to choose Node 2vec. Despite the general advantages of GNNs, Node 2vec remains a viable and sometimes preferable option in specific situations. Static graphs with no node features. If your graph is relatively stable, e.g., a historical social network from a specific year, and nodes do not possess rich attributes, Node 2vec can be highly effective. It excels at capturing purely structural similarities. Simplicity and efficiency for pre-computation. For very large, static graphs where embeddings can be pre-computed once and then used for various downstream tasks, Node 2vec can be computationally efficient. The embeddings are generated offline and then used as fixed features. Baseline performance. Node 2vec often serves as a strong baseline model due to its simplicity and effectiveness in capturing topological information. It can quickly provide insights into graph structure. Example scenario for Node 2vec. Imagine you are analyzing a fixed academic citation network from 2005. You want to group papers with similar citation patterns. Node 2vec will be a good choice here as the graph is static, and its focus on structural neighborhoods aligns well with finding papers that are cited by or cite similar sets of other papers. 2.4.2 When to choose GNNs. GNNs are generally the go-to solution for more complex and dynamic graph problems. Dynamic graphs. When the graph structure changes frequently, e.g., new users joining a platform, new transactions occurring, GNNs. Inductive capabilities are crucial. They can generate embeddings for new entities without needing to retrain the entire model. Presence of rich node features. If your nodes have meaningful attributes, e.g., user profiles, product descriptions, chemical properties, GNNs can seamlessly integrate these features into the embedding process, leading to more informative representations. End-to-end learning. GNNs can be trained end-to-end for specific tasks, e.g., directly predicting a node's class or a link's existence, allowing the embeddings to be optimized directly for the downstream objective. Complex relational reasoning. For tasks requiring a deeper understanding of multi-hop relationships and how information propagates through the network, e.g., drug discovery, recommendation systems, GNN's iterative message passing is highly effective. Example scenario for GNNs. Consider a real-time fraud detection system for an online payment platform. New users register, new transactions occur constantly, and fraudulent patterns might involve complex chains of transactions. A GNN could learn to identify suspicious nodes, users, or transactions by aggregating information from their neighbors, e.g., transaction partners, connected accounts, even for newly created entities. 2.5 Practical implications and computational considerations. Understanding the transductive versus inductive distinction has significant practical implications, especially concerning computational resources and mod. El deployment. 2.5.1 Computational implications. Node 2vec, transductive. Pre-computation. The embeddings for all nodes are typically pre-computed offline. This could be time-consuming for very large graphs, as it involves generating many random walks and then training the skip-gram model. Retraining cost. The most significant computational hurdle is retraining. If the graph structure changes, new nodes/edges, the entire node 2-vec process, random walk generation, and skip-gram training needs to be repeated to ensure consistent embeddings. This makes it impractical for highly dynamic graphs. GNNs inductive. Training cost. Training a GNN model, learning the aggregation and update functions, can be computationally intensive, especially for deep GNNs or very large graphs, often requiring specialized hardware like GPUs. Inference efficiency. Once trained, generating embeddings for new or existing nodes is very efficient. You simply pass the node's local neighborhood and features through the learned GNN layers. This is a major advantage for real-time applications or dynamic environments. 2.5.2 Real-world scenarios and unseen nodes. Let's consider a concrete example of a new, unseen node to highlight the operational differences. Scenario. A new user joins a social network. Node 2-vec approach. 1. A new user, node X, joins the social network and connects with existing users, A, B, C. 2. To get an embedding for node X, you would theoretically need to add node X and its connections to the entire graph. 3. Then, you would need to rerun the random walk generation process across this updated, larger graph. 4. Finally, you would retrain the skip-gram model on the new set of random walks to get updated embeddings for all nodes, including node X. This is computationally expensive and slow for every new user. GNN approach. 1. A GNN model has been trained on the existing social network. It has learned functions for message passing. 2. When a new user, node X, joins and connects with existing users, A, B, C, the GNN can immediately generate an embedding for node X. 3. The GNN would collect the features/embeddings of node X's neighbors, A, B, C, aggregate them using its learned aggregation function, and then apply its learn update function to compute node X's embedding. This happens directly, without needing to reprocess the entire graph or retrain the model. This example clearly illustrates why inductive models, like GNNs, are indispensable for applications involving continuously evolving data, such as recommendation systems, online fraud detection, or evolving biological networks. Representations and embeddings. Understanding and processing graph structure data is fundamental in many modern applications, from social networks and biological systems to transportation grids and knowledge graphs. However, graphs, with their intricate connections and varying structures, pose unique challenges for traditional machine learning algorithms, which typically operate on structured, tabular data or fixed-size feature vectors. This is where the concept of graph representations and, more specifically, graph embeddings becomes crucial. Understanding graph data. A graph fundamentally consists of two components: nodes, or vertices, and edges, or links, that connect pairs of nodes. This structure can be incredibly rich, capturing complex relationships that are often lost when data is flattened into conventional tables. Traditional graph representations. Historically, graphs have been represented in computers using structures like adjacency matrices and edge lists. While these are effective for storing the graph's topology, they come with significant limitations for machine learning tasks. Adjacency matrix. An adjacency matrix is a square matrix where rows and columns correspond to nodes in the graph. An entry code snippet is typically 1 if there's an edge from node code snippet to node code snippet, and 0 otherwise. For weighted graphs, code snippet might store the weight of the edge. Let's consider a very small, conceptual graph with 3 nodes: Alice, Bob, and C. Errol. Alice is connected to Bob, and Bob is connected to Carol. Code is not spoken. To get code, please see the link in description or bio. This conceptual matrix clearly shows the direct connections. Code snippet is 1, indicating an edge from Alice to Bob. Edge list. An edge list is a more straightforward representation, simply listing each edge as a pair of connected nodes. For weighted graphs, the weight might be included. Code is not spoken. To get code, please see the link in description or bio. The edge list is compact, especially for sparse graphs with relatively few edges compared to the number of possible edges. Limitations of traditional representations for machine learning. While these representations are structurally sound, they present several challenges for machine learning. 1. Scalability issues. Adjacency matrices for large graphs, e.g., millions or billions of nodes, become prohibitively large, often sparse, and inefficient to store and process. Even edge lists, while more compact, can still be massive. 2. Inability to capture rich information. These representations primarily capture direct connectivity. They struggle to inherently represent more subtle topological details, such as a node's role within a community, its centrality, or the semantic meaning of its connections. For instance, two nodes might not be directly connected, but share many common neighbors, indicating a strong implicit relationship that's not immediately obvious from a simple E0 or 1 in a matrix. 3. Incompatibility with standard ML algorithms. Most classical machine learning algorithms, e.g., logistic regression, support vector machines, random forests, and even standard neural networks, are designed to work with fixed-size, numerical feature vectors. They cannot directly process a graph structure or a variable-sized adjacency matrix. To use these algorithms, graph data must first be transformed into a compatible format. The need for graph embeddings. To bridge the gap between complex graph structures and the requirements of machine learning models, we need a way to transform graph data into a format that is both concise and informative. This is precisely the role of graph embeddings. Imagine you have a high-resolution photograph. While it contains a vast amount of pixel data, for certain tasks like identifying the subject, you might only need a compact description. A person smiling, wearing a blue shirt, standing in a park. This compact description retains the essential features without needing all the pixel-level detail. Similarly, graph embeddings aim to reduce the complexity of a graph while preserving its most crucial structural and relational information. They do this by representing each node, edge, or even an entire subgraph as a low-dimensional vector in a continuous numerical space. For example, instead of representing Alice as a row in adjacency matrix, we might represent her as a vector like code snippet. This simple array of numbers, despite its small size, is designed to encapsulate complex information about Alice's position in the graph and her relationships. What are graph embeddings? A graph embedding is a mapping from a graph, or its components, to a low-dimensional vector space. The goal is that nodes or edges/subgraphs that are similar in the graph structure or semantics should have embedding vectors that are close to each other in the vector space. Closeness is typically measured using distance metrics like Euclidean distance or cosine similarity. Retaining essential information. When we talk about essential structural and relational information being retained, what exactly does that mean? Graph embedding algorithms learn to capture various facets of a node's identity and its context within the graph, including node similarity, nodes that play similar roles or have similar connections, e.g., two friends in a social network or two genes involved in the same biological process, should have similar embeddings. Community structure. Embeddings can reveal natural groupings or clusters of nodes within the graph. Nodes belonging to the same community will often have embeddings that cluster together. Node roles/positions. Embeddings can differentiate between nodes based on their structural role, such as central hub, bridge node, or isolated node. Local neighborhood information. The immediate connections and characteristics of a node's neighbors. Global position. Information. A node's overall placement and influence within the larger graph structure. Condensing graph complexity. A conceptual example. Let's revisit our tiny graph of Alice, Bob, and Carol. Alice is connected to Bob. Bob is connected to Carol. Code is not spoken. To get code, please see the link in description or bio. Instead of representing this as an adjacency matrix or edge list, an embedding process would transform each node into a vector. While the actual numbers are learned through complex algorithms, conceptually, they might look like this. Code is not spoken. To get code, please see the link in description or bio. In this conceptual example, notice how Bob's vector code snippet is between Alice's code snippet and Carol's code snippet in terms of numerical values. This reflects Bob's intermediate position in the simple chain graph. If we were to plot these vectors in a 2D space, Alice, Bob, and Carol would appear in a sequence, reflecting their connectivity. The key takeaway here is that these small vectors, despite being just numbers, encapsulate the structural relationships. Machine learning models can then readily consume these fixed-size numerical vectors, making them compatible with a wide range of algorithms. The power of embeddings for machine learning. Graph embeddings unlock the potential to apply powerful machine learning techniques to graph-structured data, enabling standard ML algorithms. Once nodes, or edges/subgraphs, are represented as GNNs, low-dimensional vectors, they can be directly fed as input features into standard machine learning models. This includes traditional classifiers like support vector machines, SVMs, logistic regression, and random forests, as well as deep learning architectures like multi-layer perceptrons, MLPs. Dimensionality reduction and feature engineering. Embeddings serve as a powerful form of dimensionality reduction. They transform high-dimensional, sparse graph representations, like adjacency matrices, into compact, dense vectors. This not only saves computational resources, but also often improves model performance by distilling essential information and reducing noise. Furthermore, embeddings act as a sophisticated form of feature engineering. Instead of manually crafting features for each node, e.g., node degree, clustering coefficient, embedding algorithms automatically learn relevant features from the graph structure itself. These learned features are often more expressive and capture latent relationships that are difficult for humans to identify. Practical applications. The ability to represent graph components as vectors opens up a vast array of practical applications. 1. Node classification, predicting the type or category of a node. For example, identifying spam accounts in a social network, classifying the function of a protein in a biological network, or categorizing articles in a citation network. The embedding of a node becomes the input feature for a classif. 2. Link prediction, predicting the existence of a future or missing link between two nodes. This is crucial for friend recommendations in social networks, drug target interaction prediction, or predicting new scientific collaborations. This can be done by calculating the similarity between the embeddings of two nodes. 3. Community detection, identifying groups of nodes that are more densely connected to each other than to the rest of the graph. By clustering node embeddings, natural communities within the graph can be discovered. 4. Graph visualization. High-dimensional embeddings can be projected into 2D or 3D space using techniques like T-SNE or UMAP, allowing for visual exploration of complex graph structures and the relationships between nodes. Nodes that are structurally or semantically similar will appear close together in the visualization. 5. Recommendation systems. Recommending products, movies, or content based on user-item interaction graphs. Embeddings can capture user preferences and item characteristics. 6. Anomaly detection. Identifying unusual patterns or outliers in graph data, such as fraudulent transactions or network intrusions, by looking for nodes with embeddings that are distant from typical clusters. In summary, graph embeddings are a cornerstone of modern graph machine learning. They provide a powerful mechanism to transform complex, irregular graph data into a structured, numerical format that is readily consumable by a wide range of machine learning algorithms, enabling the extraction of valuable insights and the resolution of challenging real-world problems. Representations and embeddings. Understanding how to represent and interpret the relationships within a graph is fundamental to applying machine learning techniques to network data. Unlike traditional tabular data, where features often exist in a Euclidean space, graph data requires a different conceptualization of similarity and context. Defining similarity and context in graphs. In conventional machine learning, similarity between data points is often measured by their spatial proximity in a multidimensional feature space, typically using metrics like Euclidean distance. For instance, two data points are similar if they are close together in a scatter plot. However, in graph structures, similarity goes beyond mere spatial distance. It's about how nodes are connected, their roles within the network, and the paths that exist between them. Two primary graph-theoretic notions of similarity are crucial. 1. Topological proximity, hops/path length. This refers to the shortest path distance between two nodes. Nodes that are few hops away are considered more similar. 2. Probabilistic proximity, random walks. This captures the likelihood of reaching one node from another through a random traversal of the graph. Nodes frequently co-occurring in random walks are considered similar, reflecting shared structural roles or contexts. Let's explore these concepts in more detail. Hops and path length. The simplest measure of similarity in a graph is the shortest path distance, often referred to as hops. A hop represents traversing a single edge from one node to an adjacent node. The shortest path between two nodes is the minimum number of hops required to travel from one to the other. Mathematically, for an unweighted graph $g equals v(e$), the shortest path distance $d u v between two nodes $u v backslash and v$ is the minimum number of edges in any path connecting $u$ and $v$. If no path exists, $d u v equals backslash empty $. Consider a social network. Two individuals are similar if they're direct friends, one hop, or friends of friends, two hops. The fewer hops, the stronger their direct or indirect connection, implying a higher degree of similarity. Similarly, in a citation network, two papers are similar if one cites the other, or if they are co-cited by a third paper. To illustrate, let's represent a simple graph and calculate shortest path distances using the code snippet library in Python. Code is not spoken. To get code, please see the link in description or bio. This code snippet initializes a basic graph with 5 nodes and 5 edges. It uses code snippet, a powerful Python library for graph creation and manipulation. We define the nodes and edges, then add them to an undirected graph object. This graph can be visualized as code is not spoken. To get code, please see the link in description or bio. Now, let's compute the shortest path between two nodes. Code is not spoken. To get code, please see the link in description or bio. Here, code snippet dir. CDLY calculates the minimum number of hops. For nodes A and D, the shortest path is code snippet, which is 2 hops. For A and D, the shortest path is code snippet, also 2 hops. While shortest path length provides a clear measure of direct or immediate relatedness, it only captures one aspect of similarity. It doesn't account for the diversity of paths or the broader structural context surrounding nodes. For instance, 2 nodes might have the same shortest path length to a third node, but one might have many more alternative routes, indicating a richer, more robust connection. This is where probabilistic proximity becomes valuable. Probabilistic proximity and random walks. Probabilistic proximity defines similarity based on the likelihood that 2 nodes will be visited together during a random traversal of the graph. This concept is particularly powerful because it implicitly captures higher-order connectivity patterns in the neighborhood or context of a node. Imagine starting at a node and randomly picking an adjacent edge to move to the next node. Repeating this process creates a random walk. If 2 nodes frequently appear together within these random walks, or if one node is likely to be visited shortly after another, they're considered probabilistically proximate. This approach is analogous to how word embeddings, like word2vec, work, where words that frequently appear in similar contexts, e.g., king, and queen, are embedded closely in vector space. In graphs, random walks define these contexts for nodes. Simulating random walks. A random walk starts at a given node, and, at each step, randomly chooses one of the current node's neighbors to move to, continuing for a specified number of steps. By performing many such walks, we can build a statistical understanding of node relationships. Let's implement a function to simulate random walks and then analyze co-occurrence. Code is not spoken. To get code, please see the link in description or bio. This function code snippet takes a graph, a starting node, and a desired walk length. It iteratively selects a random neighbor at each step until the walk length is reached or the current node has no neighbors. This forms the basic building block for understanding probabilistic proximity. For example, a walk of length 3 might result in code snippet or code snippet. Now let's simulate multiple random walks to derive co-occurrence probabilities. By running many walks, we average out the randomness and reveal underlying structural relationships. Code is not spoken. To get code, please see the link in description or bio. This second part of the code simulates many random walks. For each starting node, it performs code snippet random walks of code snippet. It then iterates through each generated walk and counts how many times any two distinct nodes appear together within the same walk. Higher counts indicate stronger probabilistic proximity. This statistical approach helps capture the context of nodes, where nodes that frequently share contexts, i.e., appear in the same random walks, are deemed similar. For our small graph, we might see pairs like code snippet, code snippet, code snippet, code snippet having high counts due to direct connections, and code snippet or code snippet having moderate counts due to indirect connections. Types of random walks. The basic random walk described above is a simple random walk, where the next node is chosen uniformly at random from the current node's neighbors. However, various modifications exist, each designed to capture different aspects of similarity. Biased random walks. These walks introduce probabilities that favor certain types of neighbors or directions. For example, in node 2vec, a biased random walk allows for a trade-off between exploring the local neighborhood, breadth-first search-like behavior, and traversing further away from the starting node, depth-first search-like behavior. This allows the embedding to capture both local and global structural information. Self-avoiding random walks. These walks are constrained not to visit the same node twice within a single walk. This can be useful for discovering unique paths or understanding flow in networks without cycles. Restart random walks. These walks have a probability of returning to the starting node at each step. This emphasizes the immediate neighborhood of the starting node, making it useful for local community detection or person. Alizade recommendation systems. The choice of random walk strategy directly impacts the type of similarity captured, influencing the resulting node embeddings. From graph structure to embeddings. The ultimate goal of defining these graph-based similarity measures is to transform the complex, discrete structure of a graph into a more tractable, continuous, and dense vector representation called an embedding. These embeddings are low-dimensional vectors where similar nodes, as defined by hops or probabilistic proximity, are mapped to nearby points in the vector space. Why are embeddings necessary? Machine learning algorithms typically operate on numerical feature vectors. A graph, with its arbitrary connectivity and varying number of neighbors, is not directly amenable to these algorithms. Embeddings provide a way to featurize nodes, enabling tasks like node classification, predicting a node's label, e.g., identifying fraudulent accounts in a transaction network. Link prediction, predicting if an edge should exist between two nodes, e.g., recommending friends in a social network, or predicting future citations. Clustering, grouping similar nodes together based on their network roles or attributes. Visualization, projecting high-dimensional embeddings into 2D or 3D for visual inspection of network structure and relationships. Algorithms like Node 2vec explicitly leverage random walks to generate node embeddings. Node 2vec trains a skipgram model, similar to Word 2vec. on sequences of nodes generated by biased random walks. Nodes that frequently co-occur in these sequences, i.e., are probabilistically proximate, will have similar embeddings. Graph neural networks, GNNs, on the other hand, implicitly learn embeddings by aggregating information from a node's neighbors through multiple layers, effectively capturing structural and feature-based similarity. It's important to note that purely topological similarity, based solely on graph structure, might not always be sufficient. For many real-world applications, nodes also possess attributes or features, e.g., age, profession for a person, keywords for a document, chemical properties for a molecule. These features, combined with the structural information, provide a richer context for defining similarity. GNNs are particularly adept at integrating both structural and feature information to learn more comprehensive embeddings. Transductive versus inductive learning for graph embeddings. A critical distinction in graph embedding methods is whether they are transductive or inductive. This distinction relates to how well the learned model can generalize to unseen data. Transductive learning. Transductive learning refers to models that learn embeddings for a fixed set of nodes in a given graph. The learning process observes the entire graph during training, and the embeddings are specifically tied to those observed nodes. Characteristics. Fixed graph. The model is trained on a complete, static graph. All nodes are known at training time. Node-specific embeddings. Each node in the training graph gets a unique embedding vector. These embeddings are directly learned for each node. No generalization to new nodes. If a new node is added to the graph, or if the model needs to make predictions on a completely different graph, the entire embedding process often needs to be rerun or significantly adapted. The model does not learn a general function to generate embeddings. Implications. Computational cost. Retraining or recomputing embeddings for dynamic graphs, where nodes/edges change frequently, can be computationally expensive and time-consuming. Limited adaptability. Not suitable for scenarios where the graph structure evolves rapidly or where predictions are needed for unseen nodes. For example, if a new user joins a social network, a transductive model cannot immediately provide an embedding for them without retraining. Examples. Traditional matrix factorization methods for graphs, e.g., spectral embedding. Early versions of DeepWalk and Node2Vec, when applied strictly to learn embeddings for a fixed set of nodes. While Node2Vec can be extended for inductive tasks by learning an embedding function, its core formulation is often presented as transductive. Inductive learning. Inductive learning, in contrast, refers to models that learn a mapping function that can generate embeddings for any node, including nodes not seen during training, or even nodes in inter. New graphs. The model learns to capture general patterns of connectivity and features that are transferable. Characteristics. Generalizable function. The model learns a function $f, \text a node's local neighborhood and features, \right arrow \text embedding $. This function operates on the structural patterns and attributes of a node's local connections. Handles new nodes/graphs. Can generate embeddings for newly added nodes or for nodes in completely new graphs without full retraining. This is because it learns how to generate embeddings, not just what the embeddings are for specific nodes. Focus on local neighborhood aggregation. Typically achieves generalization by learning how to aggregate information from a node's local neighborhood. Implications. Adaptability. Ideal for dynamic graphs, real-time applications, and situations where the model needs to be applied to different, unseen networks. For example, in a recommendation system, new items or users can immediately get embeddings. Scalability. Can be more scalable as it doesn't require storing embeddings for all nodes. Embeddings are computed on the fly. Robustness. More robust to graph changes and missing data, as it relies on local patterns rather than global graph structure. Examples. Graph neural networks, GNNs, like GraphSage, GCN, GAT. These models learn parameters that define how information propagates and aggregates across nodes and edges, allowing them to compute embeddings for any node based on it. Local computational graph regardless of whether that specific node was part of the training set. The fundamental difference lies in what is learned. Transductive methods learn specific node representations, while inductive methods learn a generalizable function to compute representations. For real-world applications involving evolving networks or the need to generalize to new data, inductive methods are often preferred. Conceptual mapping to probability space. The ideas of hops and especially random walks inherently map graph structures into a probability space. When we talk about probabilistic proximity, we are essentially defining a probability distribution over the likelihood of visiting one node from another, or the likelihood of nodes co-occurring within a certain context. For example, a random walk generates a sequence of nodes. This sequence can be thought of as a sentence, where nodes are words. The probability of observing a node code snippet, given a node code snippet within a certain window, is analogous to word co-occurrence probabilities in natural language processing. By training models, like skipgram in Node 2vec, to predict these co-occurrences, the model learns to embed nodes such that their proximity in the embedding space reflects their probabilistic proximity in the original graph. This transformation into a probability space allows us to apply statistical and machine learning techniques that are well suited for probabilistic data, ultimately enabling the creation of dense, meaningful node embeddings. Transductive and inductive methods in graph learning. Understanding the fundamental distinction between transductive and inductive learning paradigms is crucial for selecting appropriate graph embedding methods and interpreting their generalization capabilities. These paradigms dictate how a model learns from data and whether it can make predictions on previously unseen data. Transductive learning. Transductive learning focuses on making predictions for a specific, fixed set of data points that are available during training. The model directly optimizes its output for these known data points. It does not learn a generalizable function that can be applied to new, unseen data. Core principles of transductive learning. In a transductive setting, the model has access to the entire graph structure and all node features, if any, during the training phase. The goal is to produce embeddings or predictions for only the nodes present in that specific training graph. If a new node or edge is introduced, the entire learning process often needs to be rerun or significantly updated for the model to make predictions for the new data. Node 2vec is a transductive method. Node 2vec, N2V, is a prime example of a transductive graph embedding method. It learns a low-dimensional vector representation, embedding, for each individual node in the graph. The algorithm explores the graph structure using biased random walks and then uses a skipgram model, similar to Word2vec, to optimize these embeddings, such that nodes that co-occur in random walks have similar embeddings. Consider the following conceptual representation of how Node 2vec assigns embeddings. Code is not spoken. To get code, please see the link in description or bio. This conceptual code snippet illustrates that a transductive method like Node 2vec, after its complex optimization process, effectively creates a fixed, pre-computed lookup table or dictionary of embeddings for every node present in the graph during training. The code snippet dictionary holds a specific vector for each specific node. Computational cost and scalability of transductive methods. A significant drawback of transductive methods is their computational cost and lack of scalability when dealing with dynamic or large graphs. Memory constraints. For a graph with code snippet nodes and embeddings of code snippet dimensions, storing all embeddings requires code snippet memory. For very large graphs, millions or billions of nodes, this can quickly become prohibitive. Time complexity of reoptimization. If the graph changes, e.g., new nodes are added, existing nodes are removed, or edges are modified, the entire embedding process often needs to be rerun or significantly updated. This is because the optimal embedding for a single node depends on its global position relative to all other nodes in the graph. Recomputing all embeddings from scratch can be extremely time-consuming, making transductive methods impractical for frequently evolving graphs. Imagine a social network where new users join every second. With a transductive model, every new user would necessitate re-embedding potentially the entire network to incorporate their presence, which is clearly unfeasible. Code is not spoken. To get code, please see the link in description or bio. This demonstrates the key limitation. Transductive models do not inherently know how to generate an embedding for a node they haven't seen during their initial, exhaustive training phase. Inductive learning. Inductive learning, in contrast, aims to learn a generalizable function or mapping from input data to output predictions. This learned function can then be applied to new, unseen data points that were not part of the training set. Core principles of inductive learning. In inductive graph learning, the model learns a set of parameters, weights, that define a transformation. This transformation takes a node's local structural information and its features, if available, as input and produces an embedding or prediction as output. The crucial aspect is that this transformation is generalizable. It doesn't depend on the specific identity of a node, but rather on its properties and local neighborhood structure. Graph neural networks, GNNs, as inductive methods. Graph neural networks, GNNs, are the quintessential example of inductive graph embedding methods. Instead of learning an embedding for each node, GNNs learn a function that can compute an embedding for any given node based on its features and the features of its immediate neighbors. The core mechanism enabling this generalization is message passing. A GNN layer typically involves 1. Aggregation. Each node gathers, aggregates, information, messages from its direct neighbors. 2. Combination. The aggregated information is combined with the node's own features to update its representation. This process is repeated over multiple layers, allowing information to propagate through the graph and enabling a node's embedding to capture information from its multi-hop neighborhood. The parameters, weights, learned during this aggregation and combination process are shared across all nodes, making the model inductive. Code is not spoken. To get code, please see the link in description or bio. This code illustrates how a GNN layer operates. It takes node features and the graph's adjacency structure as input and, through learned linear transformations and aggregations, computes new embeddings for all nodes. The key is that the code snippet itself is a function, not a lookup table. Generalization to unseen data with GNNs. The inductive nature of GNNs allows them to generalize to new nodes or even entirely new graphs that were not part of the training data. Code is not spoken. To get code, please see the link in description or bio. This code demonstrates that the code snippet, the learned function, can process the new node's features and its connections within the updated adjacency matrix to compute an embedding for it without needing to retrain the entire model. This is the power of inductive learning. Trade-offs and practical scenarios. Choosing between transductive and inductive methods depends heavily on the characteristics of your graph data and the requirements of your machine learning task. When to use transductive methods, e.g., Node 2-vec, deep walk, static, fixed graphs. When a graph structure is largely unchanging and new nodes are rare or non-existent, e.g., a historical citation network, a fixed protein-protein interaction network. Deep analysis of existing relationships. When a task requires highly accurate embeddings that capture the global structural role of each specific node within the known graph. No generalization needed. If you only need predictions for the nodes already present in your dataset. Example scenario. Analyzing a historical social network, e.g., a specific period of Twitter data, to identify communities or influential users within that fixed dataset. Here, the goal is to fully leverage the complete graph structure for precise embeddings of existing users, and the ability to generalize to future users isn't a concern. When to use inductive methods, e.g. GNNs like GCN, GraphSage, GAT. Dynamic graphs. When the graph structure changes frequently, with new nodes and edges appearing regularly, e.g., online social networks, e-commerce recommendation systems. Generalization to unseen data. When a model needs to make predictions for nodes or subgraphs that were not present during training. This is critical for tasks like spam detection, new users, fraud detection, new fraudulent entities, or recommending new products. Scalability. For very large graphs where storing individual embeddings for all nodes is infeasible or where recomputation is too slow, GNNs often use sampling techniques, like in GraphSage, to scale to massive graphs. Leveraging node/edge features, GNNs can naturally incorporate and learn from rich attribute information associated with nodes and edges, which is often crucial for real-world applications. Example scenario, fraud detection pitfall. Imagine a fraud detection system that identifies fraudulent accounts based on their network connections. If a transductive model is used, it can only identify fraud patterns among the accounts it was trained on. New fraudulent accounts or new types of fraud involving previously unseen connections would be completely missed, as the model has no mechanism to generate embeddings or predictions for them without retraining. An inductive GNN, however, could learn the characteristics of fraudulent behavior and apply that learned function to new, unseen accounts and their connections, potentially identifying emerging fraud. The contradiction of node 2vec with feature concatenation. The idea of N2V with feature concatenation appearing under inductive embeddings can seem contradictory, as node 2vec itself is transductive. This apparent contradiction highlights an important distinction. The inductive capability comes from the downstream model, not from node 2vec itself. Node 2vec generates static, transductive embeddings. However, these embeddings can then be used as features for a subsequent machine learning model, e.g., a simple multi-layer perceptron, MLP, a random forest classifier, or a logistic regression. If this downstream model is trained to learn a mapping from these N2V embeddings plus other node attributes to a prediction, and if this downstream model is designed to generalize, then the overall pipeline can behave inductively for the prediction task. For instance, you might 1. Use node 2vec to generate embeddings for all nodes in your training graph. 2. Concatenate these N2V embeddings with other raw node features, e.g., user age, location, past activity. 3. Train an MLP classifier on this combined feature set and corresponding labels. When a new node appears, 1. You cannot use node 2vec to get an embedding for it directly without retraining or a complex extension. This is the transductive bottleneck. 2. However, if you have other inductive features for this new node, like its attributes that the MLP can process, and if you have a way to generate a placeholder or zero-vector N2V embedding for it, the MLP might still be able to make a prediction based on the inductive features. This scenario is usually less effective because the N2V part of the features is missing. More commonly, if node 2vec embeddings are used in an inductive context, it implies that the N2V embeddings are pre-computed on a fixed training subgraph, and then the downstream task, e.g., node classification, is performed by an inductive classifier that uses these fixed embeddings along with other features to generalize to new nodes. The generalization capability for new nodes then comes from the other features and the inductive classifier, not from node 2vec's ability to embed unseen nodes. Hybrid approaches and extensions. While methods are typically categorized as purely transductive or inductive, research explores hybrid approaches. Inductive extensions for transductive methods. Some techniques try to make methods like node 2vec more inductive by learning functions that map random walk statistics or local neighborhood structures to embeddings, rather than optimizing individual node vectors. For example, methods that learn a mapping from ego networks to embeddings. Scaling inductive methods. GNNs like GraphSage explicitly incorporate sampling techniques to scale to massive graphs, effectively learning generalizable aggregation functions without needing to process the entire graph structure at once. Pre-trained embeddings plus inductive models. As discussed with N2V, pre-trained transductive embeddings can serve as rich input features for an inductive downstream model, combining the benefits of both. Ultimately, the choice between transductive and inductive methods depends on the specific problem. the nature of the graph data, and the required generalization capabilities. Summary of terms related to transductive embedding methods. Understanding the landscape of graph embedding methods requires precise terminology. This section clarifies key terms often used interchangeably or with subtle distinctions. Shallow methods and encoders, particularly within the context of transductive graph embeddings. This builds upon the fundamental understanding of transductive and inductive learning paradigms, providing a more refined vocabulary for discussing graph machine learning systems. Shallow methods in graph embeddings. In the broader field of machine learning, shallow models typically refer to algorithms that do not employ deep, multi-layered neural networks for feature learning or transformation. Examples include linear regression, support vector machines, SVMs, and traditional decision trees. These models often rely on handcrafted features or simpler, direct mappings from input to output. In the context of graph embeddings, shallow methods refer to approaches that directly learn a low-dimensional vector representation, embedding, for each node. Crucially, they achieve this without relying on complex, multi-layered neural architectures that iteratively transform and aggregate features from a node's neighborhood. Instead, these methods often optimize an objective function based on statistical properties, random walks, or matrix factorization of the graph's connectivity. The embeddings themselves are often the primary learned parameters. Char. Characteristics of shallow graph embedding methods. 1. Direct embedding learning. The goal is to learn a vector $v_i / math r $d for each node $i such that these vectors preserve certain graph properties, e.g., proximity, structural equivalence. 2. Lack of deep architectures. They do not typically use deep neural networks with multiple hidden layers to map raw node features or the adjacency matrix to embeddings. The learning is more about optimizing the embedding vectors directly. 3. Transductive nature. Most classic shallow graph embedding methods are inherently transductive. They learn embeddings for the specific set of nodes present in the training graph. If new nodes are added or the graph structure changes significantly, the entire embedding process usually needs to be re-executed or substantially retrained. They do not learn a generalizable function to map any arbitrary node into the embedding space. Concrete examples of shallow graph embedding methods. Deep walk, one of the pioneering shallow methods. It learns node embeddings by performing truncated random walks on the graph to generate sequences of nodes. These sequences are then treated like sentences in natural language processing, NLP, in an algorithm similar to Word2Vec, e.g., skipgram, is used to learn embeddings that maximize the probability of co-occurrence of nodes within a certain window. Consider a simple graph represented by an adjacency list. Code is not spoken. To get code, please CTH. A link in description or bio.python. Import torch. Import torched NN as NN. Import torch.nn.functional as F. A simplified GNN layer, e.g., GCN-like aggregation. Class GCN layer, NN, module. Def__, init__, self and features out features. Super GCN layer, self init__. Self.linear equals NN. Linear features out features. Bias equals false. Weight matrix W. Def forward self node features adj matrix. Step 1. Aggregate features from neighbors. Simplified A at X. In a real GCN, this would involve normalized adjacency matrix. Aggregated features equals torch.mapmul. adj matrix node features. Step 2. Transform aggregated features. Output features equals self.linear aggregated features. Return output features. Code is not spoken. To get code, please see the link in description or bio.python. A simple GNN encoder using the GCN layer. Class GNN encoder, NN, module. Def__, init__, self, in_features, hidden features, out features. Super GNN encoder self underscore init underscore self.gcn1 equals GCN layer in underscore features hidden underscore features. Self.gcn2 equals GCN layer hidden underscore features out underscore features. Def forward self node underscore features adg underscore matrix. Pass through first GCN layer, apply activation. H1 equals f.relu self.gcn1 node underscore features adg underscore matrix. Pass through second GCN layer to get final embeddings. Embeddings equals self.gcn2 h1 adg underscore matrix. Return embeddings. Example usage conceptual. No underline nodes igual a 5. Feature underscore dim equals 10. Node underscore features underscore example equals torch.ran. Number underscore nodes, feature underscore dim. Adan underline matrix underline simply igual torch.ranging 0, 2. Num underline nodes, ponto F. Load, binary adjacency. adg matrix underscore example equals adg matrix underscore example. Torch.dag underscore embed, torch.diagram. adg matrix underscore example. Remove self loops for simplicity. Encoder equals GNN encoder. Feature underscore dim 16, 8. Input features hidden dim. Output embedding dim. Node underscore embeddings equals encoder. Node underscore features underscore example. adg underscore matrix underscore example. Print f node embeddings shape. Node underscore embeddings dot shape should be number underscore nodes output underscore embedding underscore. Code snippet GNN encoder code, snippet encoder code, snippet underscore features code, snippet to underscore matrix code, snippet underscore embeddings code, snippet code, snippet graph autoencoder code, snippet GNN encoder can be embedded within a larger architecture. The GNN part is still the encoder, but it's trained end-to-end to serve a reconstruction task. Distinguishing key terms, transductive methods, shallow methods, and encoders. These terms describe different aspects of graph machine learning models. Transductive methods refer to a learning paradigm where the model is trained on and makes predictions for a fixed set of data points. It doesn't learn a generalizable function that can be applied to new, unseen data. In graph embeddings, this means embeddings are learned for specific nodes in a given graph, and recomputation is needed for new nodes. Shallow methods refer to a class of models that achieve their goal without using deep, multi-layered neural networks for feature learning. Many, but not all, shallow graph embedding methods, like deep walk node 2 vec line, are transductive because they optimize embeddings for specific nodes in the training graph. Encoders refer to a functional component or concept that transforms raw input data into a lower dimensional representation. GNNs are a prime example of encoders for graph data. While shallow methods produce embeddings, representations, they are not typically referred to as encoders in the same architectural sense as GNNs, which involve learnable, compositional functions. Common misconceptions and nuances. 1. Shallow does not automatically mean transductive. While many traditional shallow graph embedding methods are transductive, the terms are not synonymous. A shallow model, e.g., a simple linear model, could be trained inductively if it learns a general mapping from features to output that can apply to new data. However, in graph embeddings, the methods we call shallow almost always operate transductively due to their reliance on global graph structure for optimization. 2. Not all methods that produce embeddings are encoders in the GNN sense. Shallow methods like deep walk produce embeddings. These embeddings are representations. However, they don't involve a separate encoding network that takes raw node features and iteratively transforms them. Instead, the embeddings are the parameters learned directly from the graph structure, e.g., through skipgram on random walks. GNNs, on the other hand, are explicit encoders that learn a function to map features and structure to an embedding. Relat. Ion chip summary, conceptual diagram. Imagine 3 overlapping but distinct sets. Transductive methods. This large set includes all models that operate on a fixed data set. A significant subset of these are shallow graph embedding methods, e.g., deep walk, node 2 vec line. These are typically transductive. It can also include GNNs when they are trained in a purely transductive setting, e.g., standard node classification where the entire graph is known during training and inference, and no new nodes are expected. Inductive methods. This set is distinct from transductive methods. The primary examples in GraphML are GNNs. Encoders. This is a functional concept. GNNs are powerful encoders, capable of learning inductive representations. Graph autoencoders, GAEs, explicitly use GNNs as their encoding component. Shallow methods produce embeddings, which are representations, but they don't typically contain an explicit encoder architecture in the neural network sense. Practical scenarios in method selection. Understanding these distinctions is not merely academic. It informs the choice of method for real-world problems. When to prefer a shallow, transductive method. Very large, static graphs. When the graph is enormous and unlikely to change, and computational resources for training deep GNNs are prohibitive. Shallow methods can often provide good embeddings faster. Focus on structural proximity. If the primary goal is to capture similarity based purely on connectivity patterns, e.g., who is connected to whom, or who shares neighbors, and rich node features are less important or absent. Baseline performance. To establish a quick and efficient baseline for downstream tasks before investing in more complex deep learning models. Limited data. When the amount of labeled data for supervised GNN training is very scarce, unsupervised shallow methods can provide useful representations. When to prefer an inductive GNN-based encoder. Dynamic graphs / new nodes. When the graph is evolving, or the model needs to generalize to unseen nodes or entirely new graphs. Rich node features. When nodes possess meaningful features that need to be incorporated and propagated through the graph structure. Complex relationships. To capture multi-hop dependencies and highly nonlinear relationships within a graph. Transfer learning. When pre-trained encoders need to be fine-tuned for various downstream tasks or applied to different but related graphs. In essence, shallow transductive methods are often computationally efficient and effective for static graphs, where structural similarity is key. In contrast, GNN-based encoders offer superior generalization capabilities and the power to leverage rich node features, making them suitable for dynamic and complex graph learning tasks. N2V, random walks across graphs. Node 2 vec, N2V, is a powerful algorithm for generating node embeddings that builds upon the fundamental idea of random walks. At its core, N2V aims to learn a mapping of nodes to a low-dimensional feature space, where nodes that are structurally similar in the graph are mapped to nearby points in the embedding space. This process relies heavily on intelligently designed random walks to capture diverse structural information about the graph. The foundation, unbiased random walks in deep walk. Before diving into Node 2 vec's unique contributions, it's helpful to understand its predecessor, deep walk. Deep walk introduced the concept of learning node embeddings by treating sequences of nodes generated by random walks as sentences and applying natural language processing, NLP, techniques, specifically the skip-gram model. In deep walk, random walks are unbiased. This means that from any given node, the probability of moving to an adjacent neighbor is uniform. If a node has code snippet neighbors, the probability of transitioning to any one of them is simply code snippet. This uniform sampling strategy captures a general sense of node proximity and connectivity. Consider a simple graph. Code is not spoken. To get code, please see the link in description or bio. An unbiased random walk starting from node code snippet might look like code snippet. Each step is chosen randomly from the current node's neighbors. Node 2 vec is innovation, biased random. ALX. Node 2 vec enhances deep walk by introducing tunable biases to the random walk process. These biases allow the algorithm to explore different notions of node similarity. 1. Homophily. Nodes that are part of similar communities or have similar attributes are considered similar. This often implies a preference for breadth-first search, BFS, like exploration. 2. Structural equivalence. Nodes that occupy similar structural roles in the graph, e.g., all hub nodes or all leaf nodes, are considered similar, even if they are far apart. This often implies a preference for depth-first search, DFS, like exploration. N2V achieves these biases through two key parameters: code snippet, return parameter, and code snippet, in-out parameter. These parameters control the probability of transitioning to the next node based on the previous node visited, allowing the random walk to dynamically adjust its exploration strategy. Understanding the code snippet, return parameter. The code snippet parameter controls the probability of immediately revisiting the previous node in the walk. Code snippet. High code snippet makes it less likely to return to the previously visited node. This encourages the walk to move forward and explore new parts of the graph, avoiding backtracking. Code snippet. Low code snippet makes it more likely to return to the previously visited node. This can cause the walk to get stuck in local neighborhoods, repeatedly traversing back and forth between two nodes. Code snippet. The probability of returning to the previous node is proportional to its degree, similar to an unbiased walk, if code snippet is also 1. Example scenario for code snippet. Suppose a random walk is at node code snippet and just came from node code snippet. The next step is to enable code snippet of code snippet. Code is not spoken. To get code, please see the link in description or bio. If code snippet is code snippet, i.e., returning to the previous node, the transition probability is influenced by code snippet. Understanding the code snippet in-out parameter. The code snippet parameter controls the probability of moving towards nodes that are farther away, DFS-like, versus nodes that are closer, BFS-like, to the previous node. Code snippet. High code snippet biases the walk towards local exploration, BFS-like behavior. It's less likely to venture far from the previous node's immediate neighborhood. This helps capture homophily. Code snippet. Low code snippet biases the walk towards global exploration, DFS-like behavior. It's more likely to move to nodes that are further away from the previous node, exploring new parts of the graph. This helps capture structural equivalence. Code snippet. The probability of moving to neighbors is proportional to their degree, similar to an unbiased walk, if code snippet is also 1. Example scenario for code snippet. Again, a walk is at node code snippet and just came from node code snippet. The next step is to enable code snippet of code snippet. Code is not spoken. To get code, please see the link in description or bio. If code snippet is code snippet, returning to previous influenced by code snippet. If code snippet is a neighbor of code snippet, same distance from code snippet as code snippet influenced by code snippet. If code snippet is not a neighbor of code snippet, further away from code snippet influenced by code snippet. The probabilities for the next step from code snippet to code snippet are calculated as follows, unnormalized. If code snippet. If code snippet is a neighbor of code snippet, but code snippet. If code snippet is not a neighbor of code snippet. These code snippet values are then normalized over all possible next steps from code snippet to determine the actual probabilities. Mimicking deep walk. A common misconception is that setting code snippet and code snippet mimics deep walk. This is incorrect. To mimic the unbiased random walk behavior of deep walk, both code snippet and code snippet should be set to code snippet. When code snippet and code snippet, all code snippet values become code snippet, meaning all neighbors of the current node code snippet have an equal unnormalized probability of being chosen, effectively resulting in an unbiased random walk. Generating biased random walks in code. Let's illustrate how these parameters influence walk generation using a small graph. We'll use the code snippet library to represent the graph, but implement the biased random walk logic ourselves to highlight code snippet and code snippet. First, we set up a simple graph. Code is not spoken. To get code, please see the link in description or bio. This code creates a basic graph with 8 nodes and 8 edges, which we can use for demonstrating random walks. Walk logic with code snippet and code snippet. The core of Node 2-Vex random walk is the calculation of transition probabilities. We need to consider the previous node, code snippet, the current node, code snippet, and the potential next node, code snippet. Code is not spoken. To get code, please see the link in description or bio. The code snippet function calculates the relative attractiveness of each neighbor based on its relationship to the code snippet and the code snippet and code snippet parameters. The code snippet function then uses these calculated probabilities to stochastically choose the next node in the sequence. Running this code multiple times will show how the different code snippet and code snippet values influence the types of paths generated. For instance, with code snippet, walks tend to stay within the immediate neighborhood of code snippet and code snippet or code snippet, while with code snippet, they are more likely to branch out to code snippet, code snippet, code snippet, code snippet, code snippet. From random walks to embeddings, the skipgram model. The random walk seq. Instances generated by N2V are not the embeddings themselves. Instead, they serve as the input for a word embedding model, typically the skipgram model from Word2Vec. This is the shallow neural network component that converts sequences of visited nodes into numerical embeddings. The role of skipgram. The skipgram model's objective is to learn word representations, in our case, node representations, such that words that appear in similar context have similar embeddings. When applied to graphs, words are nodes. Each node in the graph is treated as a word. Sentences are random walks. Each random walk sequence, e.g., code snippet, is treated as a sentence. Context is neighborhood. The context of a target node code snippet is defined by the other nodes that appear within a fixed size window around code snippet in the random walk sequence. The skipgram model works by trying to predict the context nodes given a target node. For every target-context pair, the model adjusts its internal weights. The hidden layer weights of this shallow neural network, after training, become the low-dimensional embeddings for each node. Conceptual walkthrough of skipgram training. Imagine a random walk sequence. Code snippet with a window size of 2. One node, A. Target, code snippet. Contexts within window code snippet. Skipgram trains to predict code snippet given code snippet. 2. Node B, first occurrence. Target, code snippet. Contexts, code snippet within Y. Now, skipgram trains to predict code snippet given code snippet and code snippet given code snippet. 3. Node C. Target, code snippet. Contexts, code snippet. Skipgram trains to predict code snippet given code snippet. 4. Node B, second occurrence. Target, code snippet. Contexts, code snippet. Skipgram trains to predict code snippet given code snippet and code snippet given code snippet. 5. Node D. Target, code snippet. Contexts, code snippet. Skipgram trains to predict code snippet given code snippet. Through this iterative process across many random walks and many target context pairs, the model learns embeddings where nodes frequently appearing in similar contexts, i.e., structural neighborhoods captured by random walks, will have similar vector representations. Preparing data for skipgram. The raw random walk sequences need to be transformed into target context pairs suitable for skipgram training. Code is not spoken. To get code, please see the link in description or bio. This code demonstrates how a single random walk sequence is broken down into multiple target context pairs. These pairs are then fed into the skipgram model for training. The code snippet parameter determines how many nodes on either side of the target node are considered part of its context, connecting random walks to node similarity and context. The beauty of Node 2-Vec lies in its ability to capture different facets of node similarity through its biased RAN. DOM walks. Homophily. When code snippet, BFS-like, the walks tend to stay within local neighborhoods. This means nodes that are directly connected or are part of the same tightly knit cluster will frequently appear together in the same random walks. When these co-occurrences are fed into skipgram, The resulting embeddings will group together nodes that share similar local connectivity patterns or are part of the same community. This aligns with the idea that similar nodes connect to similar nodes. Structural equivalence. When code snippet, DFS-like, the walks are encouraged to explore further out from the starting node. This allows the model to identify nodes that might be topologically distant but share similar structural roles, e.g., both are bridge nodes or both are peripheral nodes connecting to a central hub. If two nodes, code snippet and code snippet, are both gatekeepers between different parts of the graph, random walks might encounter code snippet and code snippet in similar structural contexts, even if they're not directly connected. The embeddings will then reflect this functional similarity. The random walks, therefore, provide a probabilistic sampling of a node's neighborhood structure. The more frequently two nodes appear in each other's context within these walks, the higher the probability that their embeddings will be close in the vector space. This effectively translates the probability of encountering node B from node, a core concept fro, in previous sections on representations, into a concrete algorithmic process for embedding generation. Best practices and considerations. Walk length. Longer walks capture more global structural information, but also increase computational cost and might dilute local context. Shorter walks focus on immediate neighborhoods. Number of walks per node. Generating multiple walks from each node ensures a robust sampling of its neighborhood and context. More walks lead to more training data for skipgram, potentially better embeddings, but also higher computational cost. Embedding dimension. The size of the embedding vectors, e.g., 128, 256 dimensions. Higher dimensions can capture more information, but increase model complexity and risk overfitting. Window size for skipgram. This parameter defines what constitutes context in the random walk sequences. A larger window captures broader context, while a smaller window focuses on immediate neighbors. Hyperparameter tuning, code snippet. Code snippet, the most critical aspect of N2V. These parameters should be tuned based on the specific graph structure and the desired notion of similarity, homophily versus structural equivalence, for the downstream task. Common pitfalls. Disconnected components. If a graph has disconnected components, random walks cannot traverse between them. Nodes and separate components will not have their contexts mixed, and their embeddings will reflect only their isolated component structure. Sparse GRA. PHS. In very sparse graphs, random walks might struggle to capture sufficient context, leading to less informative embeddings. Parameter sensitivity. The code snippet and code snippet parameters are highly sensitive. Incorrect tuning can lead to embeddings that do not accurately reflect the desired type of node similarity. Experimentation and understanding the graph's properties are crucial. Computational cost. Generating many long random walks on large graphs can be computationally expensive. The skipgram training itself also requires significant resources. Message passing as deep learning. Graph neural networks, GNNs, represent a fundamental shift in how deep learning models process structured data. Unlike traditional multi-layer perceptrons, MLPs, that operate on fixed size, flat input vectors, GNNs are designed to directly ingest and learn from graph structure data. The core mechanism enabling this capability is message passing. This paradigm allows information to flow and be transformed across the graph's topology, mimicking how information might spread in real-world networks. At its heart, message passing views each node in a graph as an information processing unit that communicates with its direct neighbors. This communication happens iteratively across multiple layers of a GNN, allowing nodes to gather information from increasingly distant parts of the graph. The message passing process within a single GNN layer can be broken down into 4 conceptual steps for each node: collect, aggregate, transform, and update. The message passing paradigm: collect, aggregate, transform, update. Let's delve into each step in detail. For any given node $v$, and considering its neighbors $u in $n,v$, where $n,v$ denotes the set of neighbors of node $v$. Step 1. Collect, or send messages. The first step involves gathering information or messages from a node's immediate neighbors. A message from a neighbor $U$ to node $V$ typically consists of the neighbor's current feature representation, $H_U $L from the previous lay. $El$. Additionally, messages can be enriched by incorporating features associated with the edge connecting $U$ and $V$, $E_UV$. Consider a graph representing books, where nodes are books and edges represent books often bought together. Each book node might have features like code snippet, code snippet, code snippet, and code snippet. When a node, book A, collects messages from its neighbors, book B, book C, it's essentially gathering the feature information of those related books. For example, if book A is trying to understand itself better based on its neighbors, book B sends its features, code snippet. Book C sends its features, code snippet. The message is simply the information available from the neighbor, which will then be processed. Step 2. Aggregate messages. Once node $V$ has collected messages from all its neighbors, these messages need to be combined into a single, fixed-size representation. This is crucial because a node can have a variable number of neighbors, and neural networks typically require fixed-size inputs. An aggregation function achieves this. Common aggregation functions include sum aggregation, sums the feature vectors of all incoming messages. This captures the total collective information from neighbors. It's sensitive to the number of neighbors, meaning nodes with more neighbors will likely have larger aggregated values. Mean aggregation averages the feature vectors of all incoming messages. This captures the average characteristic of the neighborhood. It's robust to the number of neighbors, making it useful when you want to avoid features being dominated by nodes with high degrees. Max aggregation takes the element-wise maximum across the feature vectors of all incoming messages. This captures the most salient or prominent feature across the neighborhood. It's useful when you want to identify dominant characteristics rather than an average. The choice of aggregation function can significantly impact the resulting node embeddings. If you're classifying books by their primary genre, code snippet aggregation might highlight the most prevalent genre among neighbors. If you're predicting overall popularity based on neighbor popularity, code snippet or code snippet might be more appropriate. Let's illustrate conceptually with a simple example. Suppose node code snippet has two neighbors, code snippet and code snippet, with feature vectors code snippet and code snippet. Sum, code snippet. Mean, code snippet. Max, code snippet. Step 3. Transform messages, message function. Before aggregation, or sometimes after, the individual messages, or the aggregated message, are transformed. This step typically involves applying a small, learnable neural network, often referred to as the message function or message transformation function. This function projects the neighbor's features, and potentially edge features, into a higher dimensional or different feature space, allowing the model to learn complex interactions and patterns within the messages. This is where the concept of many small neural networks at the level of individual nodes comes into play. While conceptually each message might be processed by a distinct small neural network, in practice, the parameters of this transformation function are shared across all nodes and edges in the graph. This parameter sharing is crucial for scalability and generalization, allowing the GNN to learn universal rules that apply regardless of the specific node or its position in the graph. For instance, a linear layer, effectively a single-layer neural network without activation, is a common choice for this transformation, learning a weighted combination of incoming features. Step 4. Update node representations, update function. The final step is to update the central node $V$'s own feature representation, $H_V$L+1, using its previous representation, $H_V$L, and the newly aggregated and transformed messages from its neighbors. This is handled by an update function. The update function combines the node's existing knowledge with the new information gathered from its neighborhood. A common update mechanism involves concatenating the node's current features with the aggregated messages and then passing this combined vector through another small neural network, e.g., an MLP or a simple linear layer followed by an activation function. In other GNN variants, the update function might resemble gated recurrent units, GRUs, or long short-term memory, LSTM, cells, allowing for more sophisticated information flow and memory retention. Conceptually, the update step can be represented as $$L plus 1 equals \text update $L \text aggregate \text transform $L underscore v \text for you \nv where $v is the feature vector of node $v at layer $L $L is the feature vector of neighbor $u at layer $L $E underscore UV are the features of the edge between $U and $V $text transform is the message function, e.g., a linear layer. $text aggregate $. Is the aggregation function, e.g., sum, mean, max. $text update $. Is the update function, e.g., concatenation followed by an MLP. This iterative process of message passing allows information to propagate across the graph, enabling nodes to learn representations that encode both their local neighborhood structure and global graph properties. GNN layers as hops, the receptive field. Each GNN layer performs one hop of message passing. This means that after one layer, a node's representation incorporates information from its immediate neighbors, one hop away. After two layers, it incorporates information from its neighbor's neighbors, 2 hops away, and so on. This concept directly relates to the 6 degrees of separation analogy. Just as any two people on Earth are theoretically connected by a short chain of acquaintances, each additional GNN layer expands a node's receptive phi, ELD, exponentially. With $L layers, a node's embedding will reflect information from nodes up to $L hops away. For example, a one-layer GNN allows a book node to learn from its directly related books. A two-layer GNN allows the book node to learn from books related to its related books. This exponential scaling of the receptive field is powerful, but it also presents challenges. Deep GNNs, many layers, can lead to oversmoothing, where node embeddings become indistinguishable as information diffuses too widely, losing local specificity. This is a common pitfall that GNN architectures aim to mitigate. Simplified message passing implementation, from concept to code. To solidify the understanding of message passing, let's first look at a conceptual pseudocode for a single message passing step. This will illustrate the operations at a high level before we see how GNN libraries abstract them. Conceptual pseudocode for a single message passing layer. Imagine we are computing the new features for a single node code snippet in a graph. Code is not spoken. To get code, please see the link in description or bio. This pseudocode outlines the core logic. In a real implementation, code snippet, and code snippet would be implemented using tensor operations and learnable parameters, typically within a code snippet. Connecting to PyTorch Geometric, GCNCONV. Modern GNN libraries like PyTorch Geometric, PYG, abstract these complex message passing operations into easy or use modules. For instance, the code snippet layer, commonly used in graph convolutional networks, GCNs, encapsulates the entire message passing process for a specific GCN variant. Let's see how a code snippet layer maps to our conceptual steps. Code is not spoken. To get code, please see the link in description or bio. This code demonstrates how code snippet streamlines the entire message passing process. The code snippet module contains the learnable parameters, weights, and biases that are shared across all nodes. When code snippet is called, it efficiently computes the message passing for all nodes in parallel using optimized sparse matrix operations. Implicit versus explicit embeddings. In the context of GNNs, the output of each hidden layer, code snippet, for every node $V is an embedding. These embeddings are implicit in the sense that they're not the direct, final output of the entire model, like a classification score. Instead, they are rich, learned representations of the nodes that capture their structural and feature-based context within a graph. These embeddings can then be used as input to a final prediction head, e.g., a linear layer for node classification or a decoder for link prediction. This contrasts with some traditional deep learning models where embeddings might refer to explicit lookup tables, like word embeddings in NLP, that are fixed or learned independently before being fed into the main network. In GNNs, the embeddings are dynamically generated and refined through the message passing process itself, reflecting the unique position and neighborhood of each node in the graph. Understanding graph embeddings. Graph embeddings are low-dimensional vector representations of nodes or entire graphs that preserve essential structural and semantic information from the original graph. The primary purpose of these embeddings is to transform non-Euclidean graph data into a Euclidean space, making it compatible with standard machine learning algorithms. This transformation serves several critical functions. Dimensionality reduction. Complex graph structures, which can be high-dimensional and sparse, are compressed into dense, continuous vectors. This makes computation more efficient and can mitigate the curse of dimensionality. Feature engineering. The learned embeddings can directly serve as powerful features for downstream machine learning tasks, such as node classification, link prediction, or community detection. They encapsulate information about a node's neighborhood, its role in the graph, and its relationships with other nodes. Data visualization. By reducing the graph structure to 2D or 3D embeddings, complex networks can be visualized, revealing clusters, outliers, and structural patterns that might not be apparent in the raw graph data. Transductive versus inductive learning in graph embeddings. A fundamental distinction in graph embedding methods lies in their learning paradigm. Transductive versus inductive. This difference dictates how well a method can generalize to unseen data, which is crucial for real-world applications where graphs are often dynamic or partially observed. Transductive learning, Node 2vec, N2v. Transductive learning methods like Node 2vec, N2v, operate under the assumption that the entire graph is known and fixed during the training phase. N2v learns a unique, fixed embedding for each node present in the training graph. The core mechanism of N2v involves performing biased random walks on the graph to generate sequences of nodes. These sequences are then treated like sentences, and a word 2vec, like model, e.g., skipgram with negative sampling, is used to learn node embeddings such that nodes appearing close in random walks have similar embeddings. Strengths of N2v. Simplicity and computational efficiency. For static, smaller to medium-sized graphs, N2v is generally less computationally intensive than GNNs for generating embeddings. Its reliance on random walks and established word embedding techniques makes it relatively straightforward to implement and optimize. Effective for static graphs. When a graph structure is fixed and unlikely to change, N2v can provide robust embeddings that capture local and global graph topology effectively. Weaknesses of N2v. Lack of generalization. Transductive nature. This is the most significant limitation. If new nodes are added to the graph, or if the graph structure changes significantly, N2v must be retrained from scratch to generate embeddings for these new or modified nodes. It cannot generate embeddings for unseen nodes. No integration of node. Features. N2v primarily relies on the graph's topology. It does not inherently incorporate or leverage node-level features, e.g., user attributes, document content, during the embedding process, which can be crucial for many real-world tasks. To illustrate, consider a simple graph representation in Python. Code is not spoken. To get code, please see the link in description or bio. This code snippet defines a simple static graph using the code snippet library, which is commonly used for graph operations in Python. N2v would learn an embedding vector for each of these specific nodes, 0, 1, 2, 3, based on their connectivity. Code is not spoken. To get code, please see the link in description or bio. This conceptual function highlights that N2V processes the existing nodes in the graph to produce their embeddings. If a new node were added to code snippet later, code snippet would not be able to produce an embedding for it without being rerun on the updated graph. Inductive learning, graph neural networks, GNNs. Inductive learning methods, primarily graph neural networks, GNNs, learn a function that maps a node's features and its local neighborhood structure to an embedding. This function can then be applied to any node, including those not seen during training, or to nodes in entirely new graphs. The fundamental operation in GNNs is message passing. Each node iteratively aggregates information, messages, from its neighbors, transforms its own features, and updates its R. Representation. This process allows GNNs to learn complex patterns of connectivity and feature interactions across multiple hops in the graph. Strengths of GNNs. Generalization. Inductive nature GNNs can generate embeddings for unseen nodes or entire new graphs without retraining. This is because they learn a generalizable aggregation and update function, not fixed embeddings for specific nodes. This makes them suitable for dynamic graphs where nodes are frequently added or removed. Integration of node features. GNNs naturally incorporate node-level features, e.g., text, images, numerical attributes, into the embedding process. This allows them to capture richer semantic information beyond just graph topology. Superior for complex and large graphs, due to their ability to learn hierarchical representations through multiple message-passing layers and integrate diverse features. GNNs are generally more powerful for complex relational reasoning and scale better to very large graphs, especially when node features are informative. Weaknesses of GNNs. Complexity and computational cost. GNNs are more complex to design, train, and optimize compared to N2V. Their iterative message passing mechanism can be computationally intensive, especially for very dense graphs or graphs with high-degree nodes. Data requirements. Effective GNN training often requires a sufficient amount of labeled data for supervised tasks and rich node features to learn meaningful representations. Smoothing. A common challenge where, after many layers of message passing, node embeddings can become too similar, losing their distinctiveness. Here's a conceptual representation of how a GNN might process node features and graph structure. Code is not spoken. To get code, please see the link in description or bio. This sets up the basic inputs for a GNN layer, node features, and the graph's adjacency matrix. Code is not spoken. To get code, please see the link in description or bio. This code snippet demonstrates the essence of message passing, aggregating information from neighbors, code snippet, and then transforming it, code snippet. The output code snippet are the learned representations. The key is that this code snippet can be applied to any set of node features and adjacency matrix, making it inductive. Comparative performance and strategic choice. The choice between N2V and GNNs hinges on the specific characteristics of your graph data and the requirements of your machine learning task. Feature/method node 2vec, N2V, graph neural networks, GNNs. Learning type, transductive inductive. Generalization poor, cannot generalize to new nodes/graphs. Excellent, can generalize to new nodes/graphs. Input graph topology, adjacency matrix, graph topology plus node features. Mechanism biased random walks plus word. 2vec, like model message passing, aggregation plus transformation. Computational efficiency higher for static, smaller graphs lower. More complex, iterative, requires GPU for large graphs. Complexity relatively simple to implement and use more complex to design, train, and optimize. Adaptability to dynamic graphs low, requires retraining. High, can learn to process evolving structures. Information captured primarily structural, semantic from features and relational patterns. When to choose N2V. Static, smaller graphs. If your graph is relatively small and its structure doesn't change frequently, N2V offers a simpler and computationally efficient way to obtain robust topological embeddings. Computational efficiency is paramount. For applications where quick embedding generation on a CPU is critical and the transductive nature is acceptable. Purely topological information, where the task primarily relies on the structural similarity of nodes, e.g., identifying communities based solely on connections, and node features are not available or not highly informative. When to choose GNNs, dynamic graphs. When new nodes are frequently added or the graph structure evolves over time, GNN's inductive capabilities are indispensable as they can generate embeddings for unseen data without full retraining. Larger and complex graphs. For graphs with many nodes and intricate connections, especially when node features are rich and informative, GNNs can capture deeper, more nuanced relationships. Leveraging node features. If node attributes, e.g., text, images, numerical data, are crucial for the task, GNNs can seamlessly integrate these features into the embedding process, leading to more powerful representations. Generalization to new tasks/graphs. When a learned embedding function needs to be applied to entirely new, unseen graphs or different parts of a very large graph. Sophisticated relational reasoning. For tasks requiring a deep understanding of multi-hop relationships and interactions between nodes and their features. Practical applications of graph embeddings. Graph embeddings are versatile and find applications across various machine learning workflows, transforming complex graph data into actionable insights. Feature engineering for machine learning. One of the most common and powerful applications of graph embeddings is to use them as input features for conventional machine learning models. By converting nodes into dense vectors, tasks like node classification, link prediction, and clustering can be performed using standard algorithms. For instance, in a node classification task, e.g., classifying users into different categories based on their social network connections, the learned embeddings for each user node can be fed into a classifier. Code is not spoken. To get code, please see the link in description or bio. This sets up the embeddings and conceptual labels ready for a CL. Ossification task. Code is not spoken. To get code, please see the link in description or bio. This code snippet shows how graph embeddings, once generated, are treated as tabular features and used to train a standard machine learning classifier like logistic regression. This process allows complex graph relationships to inform predictions in a straightforward manner. Graph data visualization. High-dimensional graph embeddings can be projected into a lower dimensional space, typically 2D or 3D, for visualization purposes. Techniques like T-distributed stochastic neighbor embedding, code snippet, or uniform manifold approximation and projection, code snippet, are commonly used for this. Visualizing embeddings can reveal clusters of similar nodes, identify outliers, and provide intuitive insights into the graph's underlying structure and the effectiveness of the embedding process. Semi-supervised learning. Graph embeddings are particularly powerful in semi-supervised learning scenarios, where only a small fraction of nodes have labels. By leveraging the graph structure, embeddings can propagate label information from labeled nodes to unlabeled ones. The learned embeddings inherently capture relationships, allowing a model to infer labels for unlabeled nodes based on the proximity and similarity of their embeddings to labeled nodes. This is often achieved by training a classifier on the embeddings, where the classifier learns to distinguish between classes based on the embed. ING space.